Should I start? Okay, thank you. Great, yeah, thank you very much for having me. I'm Jacob, I'm at MIT. I mostly work on natural language processing, but what I wanted to talk about today, which I think is especially relevant to the audience of this workshop, is a slightly different question, which is not how do we sort of build better systems for working with language data, but how do we use language data into support of other kinds of machine learning problems, and especially robotics problems. So I want to start with a very big question, which is the question of how people learn. And one of the sort of distinguishing features of human cognition is the ease with which we acquire new skills and new concepts. And we do this in a bunch of different ways, right? When we are lying in the crib, before we even have the ability to control our inner environment, we learn a lot by just sort of compressing what's happened to us before and trying to predict what's coming next. Once we gain the ability to interact with our environment, we learn a lot from exploration and from trial and error. Once we understand a bit about the social context in which our decision-making takes place, we learn a lot from the other agents around us, right? We sort of learn that we are surrounded by skilled teachers who know how to do things we don't know how to do, and who can communicate things to us by, via gestures, via pointing, and so on and so forth. And finally, we use all of these things to learn language. And once we learn language, we learn a huge amount about the world via language. And it's the last of these things that I really want to focus on today. The number of things that we learn about the world, the number of skills that we acquire from language is really enormous. We acquire factual knowledge, like the causes of the First World War. We acquire procedural knowledge, how to bake a cake, right? Even knowledge that extends our understanding of language itself via things like definition, and in some cases, explicit rules of grammar and things like that. Now, of course, our ability to do this, to learn from language, rests on all those other kinds of learning that we were looking at on the previous slide. But once we learn language, it's really our most important tool for acquiring many of the complex skills that we acquire during adulthood, right? I would guess that many of us who are in the room right now got here by doing things like reading papers and talking to colleagues and attending lectures and learning how to do what it is we do via language. And so it's, the ability to learn from language, and maybe more importantly, the ability to represent things that we've learned in linguistic forms is one of the main things that separates us from all of the other learning systems that nature has ever produced. And these kinds of interactions, right, between sort of language learning and representation show up in all kinds of unexpected places. And so to sort of set up this talk, I want to take a very brief detour through one of my favorite psychology experiments. And the setup for this experiment is as follows. We're going to build some sort of rectangular room with clearly distinguished long and short walls, and we're going to paint one of those walls blue. So every corner in this room, right, is uniquely distinguished by whether the long wall is on your left or your right, and whether you can see the colored wall or not. And what we're going to do is we're going to take some sort of rewarding stimulus, depending on the particular subject of this experiment, and we're going to hide that stimulus away in one corner of the room. And the basic experiment that we're going to run is we're going to place some agent in this room. We're going to let them find the reward. We're going to disorient them, and then we're going to see if they can find it again. Now, if you do this experiment with rats, rats are not great at this. A little less than half the time, they do the right thing, and otherwise they go to the wrong corner of the room, or they just give up altogether. And the conjunctive aspect of this goal location turns out to be really important. If you just need color information or just need sort of size information to figure out where the reward is, rats do just fine at this task. You can run the same experiment with preverbal infants, and they're actually even worse, right? They're sort of equally split between these two wrong corners, more or less ignoring color. You can do this experiment with, sort of normal human adults, and unsurprisingly, people get this right almost all the time. But if you take those same people and you hijack their language abilities by giving them what's called a verbal shadowing task, and you ask them to repeat some sort of prose passage out loud, they start behaving like rats or like preverbal infants. And this effect seems to be specific to language. If you give people cognitively demanding shadowing tasks that don't involve language, you don't see the same effect. And some evidence that sort of language here is specifically implicated in our ability not just to understand what people are saying, but to actually represent complex goals or complicated plans, even for tasks that on the surface don't have anything to do with language at all. Now, all of these other kinds of learning that we looked at before correspond to sort of big established research directions. They have their own textbooks, they have their own conferences. It's really just in the last couple of years that the community has started to take seriously the possibility that language needs to be a sort of first-class part of this picture, and that it might need to sit alongside all these other kinds of learning when we think about how to build agents that are sort of generally capable of acting in the world. That's one of the reasons I'm super excited about the workshop and super excited to be here, is that, you know, this is sort of where this kind of work is happening. And so what I'm going to be talking about today are a couple of examples of work from my own group in this sort of general area on using language as a tool for supervising the learning of robot representations, or I guess supervising sequential decision-making problems in a general way, even when there's not sort of at the end of the day language as an input-output. So I'm going to start by doing a sort of deep dive into one project from our group from about a year ago that I think provides a nice framework for thinking about the whole sort of space of ways in which language might interact with these kinds of robotics tasks. And then I'm going to talk about some possible future directions and other ways we might go from here. Cool. So let's dive right in, starting with this project on learning reusable skills from natural language supervision. And this is work done by Patricia, who's actually also one of the workshop organizers today. So, right, I sort of briefly flashed cooking as an example, and really it's kind of a canonical example of a family of skills that we learn, at least in part, from natural language guidance, right? We learn to cook not by watching a million silent videos of people baking cakes on YouTube, but by looking at maybe a couple of demonstrations accompanied by really rich supervision in linguistic form. And if we're going to do big, complicated things like cooking in the real world, then we're going to need to, start with even simpler manipulation tasks in household environments, finding our way around, moving objects from one place to another, and things like that. So here's an example from the Alfred environment, which I suspect many people in this room are familiar with, which is a simulation environment designed to do things like this. Good. So how hard are tasks in this environment, right? How hard is it to do something like clean a bowl or put a slice of tomato on the kitchen counter? We're mapping from images into what turns out in this case to even just be a discrete action space. This feels like the sort of thing that should be straightforward to do with modern machine learning techniques. But if we take 20,000 demonstrations from this environment, we just train some fixed deep network policy to map from an instruction and an image to a next action, this actually doesn't work at all. Now, why might this be? Well, even these simple tasks have a lot of moving parts. Right? At the low level, we need to be able to recognize objects and plan paths between visible locations. And at the high level, we need to be able to reason about long-term consequences of these low-level actions. So even something as innocuous as, put a slice of tomato on the counter requires finding the knife and grasping it and finding a tomato and slicing it and grasping it and moving it to the counter, setting it down again. And this is quite complicated, right? And so if you think about how to learn and how to represent tasks like this, this kind of intermediate structure, right? The notion that there are a bunch of high-level actions that you need to get you from the start to the end here is super important. So how might we build a model that can reason about this high-level task structure? And maybe more importantly, how might we learn such a model from kinds of data that we actually expect to be able to collect in the world? So unsurprisingly, the most effective procedures that we've had historically for these kinds of problems look something like this. We start by building one model that explicitly decomposes our high-level goal into a sequence of these sorts of high-level skills or actions, and then have another model for executing each of these actions and executing these high-level actions and translating them into low-level actions. There's a huge literature on sort of hierarchical policy architectures that work this way, but they all require a ton of work. Right, they require you to either formalize your entire domain symbolically and engineer some kind of symbolic planning mechanism, or to predefine some sort of fixed inventory of skills that your agents can be able to execute, collect an additional set of demonstrations for some sort of learned planning model that maps goals into sort of sequences of just those skills that your model already knows about, and then collect supervision for the implementation of each of these skills. And so as a result, a lot of these methods just don't scale either to sort of complex perception and action or to really complex goal spaces. So how might language help us do better at these kinds of problems? And if we think back to our sort of rat experiments at the beginning of this talk, the sort of key insight here is that language gives us a powerful tool for reasoning about and representing behavior. It can do things like tell us what features of a demonstration are salient and likely to generalize to new states. And it gives us a sort of flexible and compositional representation language for encoding goals and encoding and sort of reasoning about plans. And so we're going to operationalize this intuition by building a model that looks a little bit like this. Given some sort of high-level goal, we're first going to generate a sequence of natural language subgoals, and then from each of these subgoals generate a sequence of low-level actions. And notice that, right, this is essentially the same picture as I drew on the previous slide for these sort of classical approaches, but it actually differs in a couple of important ways. The first thing to notice here is that because each of these high-level actions are just natural language descriptions of subtasks or subgoals, the set of possible actions that the system can execute is itself open-ended and compositional. And so unlike in sort of most of these symbolic approaches where we have to commit to a fixed action inventory up front, here the space of action that this agent can take is in principle as expressive as natural language itself. The second thing to notice here is getting supervision for which of these skills we use is actually quite easy. Instead of having to teach a human supervisor some kind of specialized demonstration language or planning language, we can just ask people to describe steps that accompany a sort of high-level plan or that accomplish some high-level goal. And finally, the last thing to note is that both our plans and our goals are strings. And so planning is just conditional text generation. And what this means is that if I have a really good model for conditional text generation, if I have a really good model of the relation between strings and strings, this is a way of learning a lot about how to plan without any sort of grounded action level data at all. And so what this means is that if we have access to good models of text, this is going to help us generalize maybe to new goals, even where we don't have any low-level demonstrations at all. So to say this one more time, right, language is going to do three things for us. It's going to give us a flexible representation language for the skills that our model is going to operate over. It's going to give us an easy way of collecting supervision for this model in the first place. And it's going to give us a way of leveraging corpus data, sort of existing sources of supervision, to accomplish new goals. So how do we actually train this model? We're going to start by doing something very simple, which is just take an existing data set of demonstrations for these tasks, and just get annotations for these demonstrations in the form of natural language. Now, this could, in principle, actually be a pretty expensive form of supervision to collect, right? We have to sort of get a bunch of skilled annotators to go in and label these things for language. So we're going to make an even stronger assumption that we actually have only a little bit of this natural language supervision and a bunch of unlabeled demonstrations to go along with them. Again, things to note here is that this is just free-form language without a guarantee of consistency in how things are described across or even within tasks. We're assuming that we have no information about the correspondence between these instructions and individual pieces of action sequences. We just have sort of recipes unaligned here. And most importantly, we're assuming that we have this data only at training time. We are not doing, or we're not training a model to sort of detailed instruction following of low-level instructions. At the end of the day, we just want to go from these high-level goals to low-level actions. And we're just going to have this language at training time to sort of scaffold that learning process. Okay, right. So to say this one more time, here's what we have when we train. We have our environment, we have goals, we have demonstrations, and we have a few of these instructions. In other words, we have something that looks like a latent variable problem, right? That on our annotated demonstrations, the correspondence between these plans and the low-level actions is latent. And on unannotated demonstrations, on most of our data, the plans themselves are latent variables. And we need to infer what these look like along with all of the parameters of our model. So to learn, we're going to need to fill all of these missing things in jointly, again, with the parameters of both a sort of planning policy and an acting policy themselves. So here's a way of sort of drawing schematically all of the things that we need to learn, right? Our sort of language model planner that generates these sequences of subgoals, our skill implementations, and all of the missing things. I'm not going to talk too much about learning in this model today, but very briefly, we can do this via map-inf by just alternating between fighting hard assignments to subtasks, hard assignments to alignments, and then hard assignments to these parameters that maximize the complete likelihood of all of our demonstrations, annotated and unannotated, under this low policy. And we're going to do this by coordinate descent, just by sort of alternating between aligning pieces of demonstrations, relabeling these aligned chunks, and then updating model parameters to fit these other variables. And we call this overall approach SLQ, or semi-supervised skill learning with latent language. Yeah, I think in the interest of time, I'm going to skip over all the learning details. I just want to call out this one because it's really sort of fun algorithmically. Once you've fixed your alignments, and once you have a fixed set of model parameters, then the inference problem that you're trying to solve here actually looks like inference in a hidden Markov model, but where the state space for that hidden Markov model is the space of all possible natural language descriptions of subgoals. And so, you can't use your standard forward-backward. There's some fun things we do with learned inference algorithms here. If you're sort of algorithmically inclined, this is actually a really sort of juicy piece of the learning problem that I think you could do in a much more sophisticated way than we have. Good. So what is math, right? What happens when we run this learning procedure on a big data set of mixed annotated and unannotated demonstrations? Well, at training time, we get something like this. Here's something that we started out with as an unannotated demonstration, and this approach was able to successfully segment it into reusable pieces and label each of those pieces with what turns out to be an accurate natural language description of the subgoal that's being accomplished in that step. So this model is able to use sort of labeled demonstrations to infer the latent structure of unlabeled demonstrations. And having done so, you can then sort of execute these new plans successfully at test time by what happened? Sorry, is it visible? Looks like it's visible again. Sorry about that. Anyway, once we've sort of done the right thing at training time, we can generate natural language plans for ourselves at test time and then execute these in the environment with our low-level model. So, in terms of evaluations, again, don't want to spend too long on this, but when we evaluate this sort of normal behavior cloning method end-to-end, like we saw on that first slide, it doesn't work at all. And when we use this SLQ method, even with a very small fraction of the data set, we're able to do both, comparable to what was at the time we published this state of the art for other end-to-end methods, and maybe most excitingly here, able to do actually a lot better than models that are conditioning on these detailed descriptions of action sequences at test time. And so the sort of plans that this model is able to generate for itself and able to infer for itself at training time are actually better plans than humans are able to write when you ask them to do that from scratch. And so that's quite cool. To give us a sort of finer grained look at what's going on here, we have some ablation studies. Here we're looking at a subtask level success rate rather than overall success rate. So that's why these bars are all higher. And so on the subtask evaluation, behavior cloning gets an accuracy of 27%. Using just, again, 10% of annotations in the data set, we do substantially better than that. And most excitingly, we actually do almost as well as if we had annotations for the entire training set. And so this sort of semi-supervised procedure that we talked about is very effective at filling in those missing plans and does, again, nearly as well as we could do if we had those plans at training time provided for the entire training data. Finally, a really important aspect of this approach, as we said before, is the use of corpus data. And so, we have that chunk of the model that we talked about as a language model planner. For all of these experiments, we initialize that model, and actually the low-level model as well, using a GPT-2 language model. And this turns out to be super important for the kinds of results that we see here. If you initialize those planning models from scratch, instead of using GPT-2, you do significantly worse on this task. Good. So let's revisit now those three things that language was supposed to do for us in accomplishing the goals and in getting these results that we just looked at. The first was to make it easy for collecting supervision, right? And here we were able to train this hierarchical policy with nothing but unaligned free-form natural language descriptions. The second had to do with the representations that we learned. And here we have actually an agent architecture that gives us a sort of library of reusable skills indexed by natural language strings. And once you have this library, you can use it for use all of these things for interacting with the environment. And in contrast to the way that we usually think about skills in symbolic approaches, or more generally in sort of options policies and skill learning approaches, right? The set of skills that this model has, while discrete, is open-ended and compositional and extensible. And the third reason, again, has to do with generalization. So predictive models of text know a ton about the world just by asking, sort of state-of-the-art language models that we have right now to fill in missing words and sentences. You can recover information about perceptual properties of objects, about tools that you need to accomplish sort of various kinds of high-level tasks, common sense information about environment layouts and environment dynamics, and lots of other things. I don't want to overstate, right? We know that these models are not perfect, and some of their sort of knowledge, to the extent that that's even the right way of thinking about it, is wrong, but they contain way more knowledge about how the world works than we can possibly hope to get from any data set of demonstrations on sort of, some fixed platform in some fixed environment, as long as we ask for that knowledge in the form of text. And so if we think back to this model architecture that we had before, right, this top part of the model, again, is just a model of the relationship between text and text. And if we can implement this with something that's been trained on language data, we can generalize in the ways that language tells us to generalize. And so we can do this with the model architecture that I just showed you. And here are some examples of generated plans for goals that are outside the training distribution. And we can go outside the training distribution in a bunch of different ways. We can do, sort of operations on groups of objects that we've only ever done on single objects at training time. That's the top left corner. We can do actions in orders that we've never seen them done, sort of compositional generalization by reordering steps of subplans. And maybe most excitingly, we can generalize even to sort of novel kinds of objects and novel kinds of actions. So the word rinse can appear anywhere in the Alfred training set. And nevertheless, if you tell this model as a high-level goal, rinse some tomatoes, it knows that rinsing is something that happens in the sink, and it's able to generate for you a high-level plan that involves navigating to a sink before you do the rinsing. Cool. To sort of wrap up this section before we move on, I also want to put this work in a little bit of perspective. Obviously, sort of around the time we started doing this, there was a bunch of other interest in language and robotics, and I think that this framework actually provides a nice way of thinking about a lot of the other sort of things that are going on in general in this language and robotics space. So first off, we were extremely inspired and took a lot of good ideas from work that had been going on in kind of the RL community on reinforcement learning and planning in text-based environments where your actions are strings even at the lowest level, your observations are strings even at the lowest level. And there was a lot of work there showing that you could use sort of big corpus data to do well in these specific interactive environments. And in some sense, the sort of key motivating idea here is just how do we scale that up to things that involve sort of real perception or real action. And after we published this work, and really, just a couple of months after we published this work, so obviously sort of all going on in parallel, there were a bunch of people that said, hey, if you do this with even bigger language models than GPT-2, you can get even crazier kinds of generalization, and you can be even, even more data efficient in some surprising ways. And a lot of this work was saying, what happens if the low-level sort of action-taking problem is just solved for you? You know what the action inventory is. You just need to figure out how to chain your high-level actions together. And it turns out that language models, even language models with no training at all and just sort of clever prompting, are very, very good at doing this. And, so you can think about a lot of the work that's gone on since then on building sort of deeper hierarchies over natural language strings as more refined versions of the same approach, right? Where you have sort of high-level planning and mid-level planning all happening in string space. And then at some point, somebody's just giving you an inventory of low-level actions, and you don't have to worry about learning those at the low level. And lastly, it's been exciting to see a bunch of other people in the community get interested in the sort of semi-supervised version of this problem, where you have a little bit of language and a lot of real-world interaction. And so this sort of general framework, I think, provides a nice way of thinking about that. Now, I want to make it very clear, right? The point of these slides is not to suggest that everything else that's gone on is a special case of these model. A lot of this, what's interesting about this other work actually has to do with if you have a pre-trained inventory of skills, how do you sort of figure out the initial conditions and termination conditions for those skills and make them play nice with your language model planner. But I guess what I would say is if you're sort of working in this general like language and skill learning space, this is a nice sort of framework for thinking about all the different ways in which we could use different kinds of supervision for learning different kinds of representations. Cool. And it turns out that actually several pieces of this architecture are really important, and like learning your own alignments and being able to reason about those alignments in a discrete skill set rather than just going from sort of strings to more detailed strings to low-level actions turns out to be important. And so I haven't talked too much about the modularity as a necessary piece of the story, but it really is. Good. I'm realizing that I'm running out of time, so I'm going to go very fast through the last couple of slides here. There's been some other cool follow-up work here, even not just from our group. Here's a work using this sort of general framework to do not instruction following, but one-shot imitation learning from demonstrations. And this, I think, really drives home the notion that language is a useful form of supervision, even when you don't actually have language as an input to your task, right? So once you've used language at training time to structure your skill inventory, to structure your prior over sequences of actions, you can use that even when what you're trying to do at the end of the day is learn from a demonstration or interpret and generalize a particular demonstration. You can also take this basic framework and port it to a bunch of other problem domains that actually don't look like robotics at all. And so we've used very similar models also for inductive program synthesis tasks. And, again, a sort of point here is that this is a way of thinking about language as a general way of shaping task representations when the sort of feedback that you get for those tasks is relatively poor. Good. To summarize this section, we talked about how to train a hierarchical policy that reasons over sequences of high-level skills parameterized by natural language strings. We showed that we could train these models very sample efficiently by treating these natural language plan descriptions as latent and inferring task structure and demonstrations jointly with model parameters. And it works. You get out models that are competitive with things that have much stronger supervision and models that generalize in sort of crazy ways to out-of-distribution goals. Okay, I have like 5 minutes before I have to leave for my next thing. So maybe I will actually skip the second section of this talk and pause for questions here before I have to drop off. But, I guess like very briefly, the one thing that I do want people to take away from this talk is that we've been sort of talking about this top layer as a language model planner. Everybody else now has been talking about this top layer as a language model planner. Language models are terrible planners. Please don't use them. Please don't throw away, sort of decades and decades of research on how to actually solve the hard inference problems involved in long-range reasoning and low-level reinforcement learning problems. And I think like the important research challenge here is figuring out how to take the knowledge that lives in language models and combine it with the inferential toolkit that we already have and know that we need for solving really, really difficult sequential decision-making problems. But yeah, I will very sadly skip over all this other stuff and wrap up there. So thank you very much for your time.
Okay, great. Cool. Yeah, so hi, I'm Jackie. I'm a research engineer at DeepMind, and I'll be presenting Gato on behalf of our co-authors listed here. But Conrad, who's the first author, is also in the room there with you. Hopefully, I can't see him, but he'll help with any Q&A as well. So this talk will be a technical deep dive. We'll begin by talking about the model, the architecture we used, the training setup, and how we process data. We'll discuss different data sources we use for training and for fine-tuning. And we'll present results in distribution, out of distribution with few-shot learning and robotics results, since this is CoRL. And finally, I'll show some visualizations of attention masks and embeddings. So some of this work was added in our TMLR publication, which has some basically added content from the initial archive submission. So Gato is a multimodal, multitask, and multi-embodiment generalist policy, or agent. The same network with the same weights can play Atari and other games, caption images, chat with a human, stack blocks with a real robot arm, and more. It decides what to output based on its context. So let's take a look at how Gato was designed to implement all these capabilities. We need to serialize different modalities such as image, text, and proprioceptive values to convert them to a unified format so they're compatible with a single input to our model. We serialize continuous values differently depending on if they're observations or actions. Observations are first mu-law encoded before discretizing floats into integers. Actions skip the mu-law encoding since our environments already have bounded actions by design and are directly discretized. These integers are used as keys to lookup vectors in the learnable embedding table. Finally, observation and action embedding vectors are concatenated together, and local positional encodings are added to them. Multiple environment time steps are processed in this way and concatenated to form a trajectory, which is used as training data. To calculate these local position encodings, we assign a local position index to each observation embedding vector. These position indices are used as to look up learnable position encodings, which are added to the observations. We do not add local position encodings to actions. To serialize images, we convert each image into a series of non-overlapping 16 by 16 patches. Each patch is processed by a ResNet, which produces the embedding vectors. We add patch positional encoding to these embedding vectors and concatenate them with actions. In this example, the action is already a discrete integer, so we directly retrieve its vector. Patch position encodings are similar to relative position encodings, but they operate in 2D since they are used to process images. First, we normalize the patch position by the image size. We then quantize the normalized position into a vocabulary size, which is 128, but it's a hyperparameter, so it can vary. We use it to index into a table of learnable position embeddings. During training, a random index is uniformly sampled from the quantized position, while during evaluation, we deterministically take the mean rounded to be an integer. Once we retrieve a row column position encoding from the table, we add it to the ResNet token embedding. We use a sentence piece tokenizer to convert text to tokens and lookup embeddings. This is identical to how most transformer-based language models process text. So finally, tying it all together, here's an example with image and text observations and discrete actions, which is the setting for Atari. Actually, not for Atari. This would be like a text augmented Atari. All of these observation embeddings are concatenated first before being concatenated with action embeddings, and so on and so forth for each time step to form a full episode sequence. Gato uses a standard decoder-only transformer with some differences. We apply a layer norm before the attention layers, use relative position encodings, as described, GEGLU activations, and stochastic depth during training, which means we drop out transformer attention layers. We train on mini batches that mix data from different multimodal data sources. We found it was very important to carefully tune the sampling weights for the various training data sets. Data from each source is serialized as described before being concatenated into the mini batch. Gato is trained to predict discretized actions from observations. To create training targets, we right-shift the input data and mask out observations. This is because image serialization generates position encodings, but not tokens, so we can't directly predict image targets. We train Gato to minimize the negative log likelihood of the training targets, which is a standard formulation common for transformer language models. After training, we can run Gato on in and out of distribution test data and live environments. If desired, we can prepend a fixed prompt to the model's context window. If the prompt is used, at the beginning of each episode, we take the first observation, which is concatenated to the prompt. We obtain the first action from the model and the second observation from the environment. And the first action and second observation are appended to the first observation as we continue to sample actions. So now I'll talk about data sets that we use for training and fine-tuning. So Gato uses large and diverse data sets for pre-training. Here, we've aggregated them into three broad categories: simulated control tasks, vision and language data sets, and real robot tasks, which is its own special category for this venue. We collected data for simulated control tasks by training a state-of-the-art RL agent and recording the data it produced while learning the task. For vision and language, we use standard data sets that cover a range of tasks such as image classification, text generation, and image captioning. Simulated control tasks contain environments with visual observations, proprioceptive features, or text instructions, or some combination of those modalities. In total, our data sets contain 62 million episodes and almost 1.5 trillion tokens. Wow, I just skipped to the end. Sorry about that. So we also train on a wide variety of vision, language data sets, ImageNet, massive text, which was the same data set used for DeepMind's Gopher language model, and vision language tasks, data with associated tasks such as captioning and visual question answering. We also constructed several out-of-distribution few-shot data sets for control tasks, and I'll present the results for those in a moment. So to do so, we selected the best scoring 2,000 episodes per out-of-distribution task, and we hierarchically subsampled a series of data sets from those of decreasing size using 3 distinct seeds. So the subsampling ensures that for a single seed, all episodes in the smaller set will be present in the larger sets. So now we'll present our results and analyze Gato's performance on in and out of distribution tasks. We evaluated the model on over 600 simulated tasks, the RGB stacking benchmark for real-world robotics, and we qualitatively evaluated its image captioning and dialogue capabilities. The slide takes a while. There we go. This plot shows the number of in-distribution tasks where Gato's performance exceeds the score of the expert who gathered the data. Gato exceeds the expert on 50%, exceeds 50% of the expert's score on 75% of the tasks. The model that produced these results is the canonical 1.18 billion parameter Gato. We analyzed the benefit of scaling the number of parameters and the amount of data by plotting the number of tokens processed against the mean normalized score. So the x-axis in the previous slide is now the y-axis. We trained 79 million, 364 million, and 1.18 billion parameter variants of Gato, the canonical variant, and observed that this biggest model has the best performance for the same number of tokens seen in training. To understand Gato's ability to generalize to unseen environments, we evaluated it on 4 holdout tasks, each from a different domain. For each task, we fine-tuned Gato on each few-shot subset in order to understand how well Gato can adapt to new domains. And we used gradient-based supervised learning and not prompting. The smallest 364 million parameter variant was used for the sake of saving compute. We compared fine-tuning the model trained on all of the in-distribution data to several baselines. The no-control data baseline is pre-trained on data from text and image only, but no RL episodes. The same domain-only baseline is pre-trained on data from the same domain as the holdout task, and from scratch baseline has no pre-training and is only trained on the holdout data. These are the fine-tuning results for cart pull swing up from the DeepMind control suite from state, so no pixel observations are present. Including data from other domains adds a significant benefit compared to training on control suite tasks. For MetaWorld assembly, the inclusion of other data in the MetaWorld domain is important, and adding all control data gives a small boost in the 10 to 100 episode regime. This task and the previous one don't require any pixel or language processing, so it makes sense that the no control baseline does poorly, since it only includes image and language data, which is useless here. The DM Lab apple foraging task, where the task is to pick up all of the green apples, includes pixel observations, so the no control data baseline appears to be useful for learning visual priors. Finally, there is no real benefit for pre-training for Atari boxing, because essentially all of our baselines do as well as the scratch baseline. We hypothesize this is because this is so visually distinct from the other games and tasks in the training data set. Next, we'll show how Gato performs on the real-world robotics tasks. We evaluated Gato on the RGB stacking robotics benchmark. The goal is to stack the red object on top of the blue one in the presence of a distractor green object for a variety of different shapes. There are 2 tasks, skill mastery and skill generalization. Skill mastery is a simple in-distribution test, so the train objects are the same as the test objects, which are a set of 5 different triplets. Skill generalization is an out-of-distribution test, so the robot is trained on a wide variety of object shapes that are not included in the test set. And the test set is just the same as the skill mastery set. The Sawyer robot typically runs at 20 Hertz, otherwise control starts to degrade. So naively running the 1.18 billion parameter model on the existing setup is much slower than this real-time rate. So we devised some improvements to run Gato on the robot. We sampled the 5 action tokens in parallel instead of sequentially to reduce the overhead of sampling. We reduced the attention context of our model to the lowest possible value. And importantly, we used faster GPUs. After optimizing for speed, we evaluated Gato on the skill mastery benchmark on the real robot. We matched the performance of the BCM baseline from the original RGB stacking paper. For the more difficult object groups like group 1, we underperformed the baseline, and for groups 3, 4, and 5, we exceed the baseline. We then moved to skill generalization. So we actually had to train a new Gato on different training data from the more diverse skill generalization dataset. And then we tested the benefits of scaling the model first in simulation to see if it was worth running such a big model. The RGB stacking paper provides 2 baselines, behavior cloning and critic regularized regression, both trained on 5,000 episodes. The largest model can outperform BC with just 1 demonstration, match expert performance with 10, and get close to the CRR baseline with 100 demonstrations and more. The results transfer to the real robot pretty well. You can see the initial zero-shot performance is around 45%, and that goes up and reaches expert performance with as little as 10 demonstrations. In addition to the RGB stacking tasks, we tested Gato's generalization capability on a novel task where the goal is to stack the blue object on the green object. In all of the pre-training data, the robot stacks the red object on the blue object. So this is a sort of an in-domain transfer challenge with color variation. We fine-tuned Gato on 500 teleoperated demonstrations of the blue on green tasks collected with SpaceNav, augmented that data with some simulated data with doing the blue on green tasks, but with a different object set. And we achieved 51% success rate evaluating this in the real robot. In addition to its achievements on these tasks, Gato has rudimentary natural language capabilities. On the left, we show Gato prompted to caption images, describing the first several held out images from the MS COCO validation set without any cherry picking. On the right are samples from prompting Gato as a dialogue agent. Usually Gato replies with a relevant response, but it is often superficial or sometimes factually incorrect, which could possibly be improved with further scaling, better data, or more sophisticated interventions. We made visualizations to qualitatively understand how Gato processes information from different domains. This slide shows a t-SNE clustering of Gato's embeddings at layer 12, halfway down the transformer depth. Each data point is colorized by the task of the embedded observation. Tasks from the same domain cluster together with some interesting outliers. For example, multimodal massive web is an image and text dataset, so it overlaps significantly with massive text, the text-only dataset, but it also has some overlap, interestingly, with the RGB stacking tasks. To understand what Gato attends to, we took the transformer attention weights at layer 0 and visualized self-attention over the corresponding image patches. Gato attends to salient regions of the image, such as the robot embodiment, character belonging to the player, the score in Atari, and tools like the ball in Breakout and Pong, or the blocks in Robotics. Attention could be useful for diagnosing certain generalization issues. For example, why does the robot attend to the green block if it's not relevant to the task, which is red on blue? Finally, in the spirit of transparency, if I have time, I'll go over some of the limitations and discuss future work. So Gato requires a large-scale expert data set, but this is a known limitation of offline imitation learning, which are really meant to be complementary to other techniques. And additionally, if we can work a bit more on the generalization capabilities, this is kind of bootstrapping an expert data set in order to generalize to new tasks. The context length is limited to 1024 tokens, which is quite small, especially when image observations are pretty large. So we can only fit a partial trajectory as a prompt, which is why we had to use gradient-based fine-tuning. The context length is even more limited when we have to run in real time for the robotics tasks. So we'll need to somehow solve fast inference for large models in a more principled way if we want to scale to even larger model sizes. Thanks all for listening, and I'm happy to take your questions. But definitely post them in the chat because I can't really hear the room, or ask Conrad directly.
All right. So can everyone hear me successfully?
Yes.
Okay. So thank you for the introduction. I'm going to talk about learning grounded language and doing language-based HRI and simulation, and how work in this area touches on a lot of different spaces in human-robot interaction and robotics generally. And this talk is not a deep dive. It's a high-level overview of some work in the grounded language learning space. So I'm going to be talking about building robots that use language, and specifically grounded language, to interact with people. I think we all know that it's important that robots that go in human spaces be able to interact adaptably, but our current robots aren't terribly flexible. We're still pretty bad at novel or dynamic needs. And my goal is to have robots that can depend on instructions and information from the people around them to overcome that. And as you'd imagine, this is pretty multidisciplinary. It needs robots and natural language and human interaction. And since the goal is specifically for robots to deal with dynamic environments, it also requires learning. There's a lot to say in this space, but in the talk, I'm going to touch on 3 high-level topics. treating language grounding as a shared embedding problem, how important actual speech is in our robot interactions, and how we're starting to address some of our data problems by using learning and simulation. So here we're considering and testing grounded language as an interactive collaborative problem. So that is, we say that a robot understands language if it does what a user intends. And we focus on the language part of human-robot interaction because it has a lot of advantages for that field. It's concise, it's intuitive, it's pre-existing, and of course, it's adaptable to a wide variety of situations. And when I say grounded language here, I'm talking specifically about language that refers to and has meaning in the context of the sensed, perceived world around the robot, which is not the only way people use that particular term. And one of the things to note here is that language grounding is very much a multifaceted problem. There's no one thing that's going to be the silver bullet approach. And a variety of approaches are critical for solving different pieces. So that includes deep learning, geometric methods, large models, and information theoretic approaches. I'll talk briefly about some recent work that tackles a subset of those problems and then come back around to simulation. So one way to think about grounded language is that it's a sort of a shared embedding problem. In that sense, language and percepts or sensory inputs both refer to some real thing in the world. It might be an object or a type of action or a task, but it's something that's mediated for a person by the language that they're using and mediated for a robot through its ability to sense the world. And that conceptualization is useful because we know a lot about different ways of discovering and using shared embeddings. And the first learning example I'm talking about, rather than just relying on the existence of that shared embedding, involves learning to approximate it directly. One way of handling shared embeddings is manifold alignment, where featurized language and sensor data are treated as projections of some underlying manifold in a non-observable space. So the goal is to find the functions that approximate the manifold. That can be done using deep learning methods, but it can also be considered as a geometric analysis problem. That means you can learn alignments between heterogeneous data sources, where you're learning a projection of data to an embedding space where intraclass distances are smaller than interclass distances. While you can use deep metric learning to learn these projections, our intention is that the learned metric and embedding capture the semantics of the paired data. We want to use data from heterogeneous domains to learn metric embeddings. So for example, in language, if somebody refers to, if we're talking about objects, if somebody refers to something as a tomato while gesturing to it, so the robot knows to direct sensors to it. And more specifically, we want to learn two embedding alignment functions that map sensor inputs and language data respectively to a shared representation space. And we do this using triplet loss, which is a function that directly encodes the idea that samples from a common class be closer in some shared embedding, while forcing dissimilar samples to be farther apart. So we're learning functions that map percepts and languages to a shared higher dimensional space. And specifically, triplet loss tries to minimize the distance between an anchor point, which here is the perceptual inputs of an object, and an associated sample in another modality, which here would be the language describing that object, while maximizing the distance between the anchor point and a negative point in the other modality, such as the description of an unrelated thing. And the learned embedding should then hopefully look something like this, where language is near the things it describes and far from things that aren't the thing it describes, far from language describing other things. And that approach works, not only in producing embeddings that can be visualized and show substantial overlap. So here I've plotted some randomly selected classes in a vision and language space so that you can see that they're in sort of the same position, but also in performance on a series of object selection tasks based on following instructions. So here, using triplet loss methods, which are the orange and blue lines, substantially outperforms deep CCA approaches that we tested. So far I've been talking about using some specific methods that we've got to learn grounded language from a combination of text and mostly visual sensors. But real human language is extremely contextual. When we're understanding language, we take a lot of factors into account, like gesture, non-visual sensors. And one of the big ones critically is when we envision talking to robots, we really envision talking, not typing. So in the next section of the talk, I'm going to talk about some of the work we're doing on language grounding for multimodal inputs, and specifically for speech. In practice, spoken language is a difficult problem. Even leaving aside the questions raised by back and forth dialogue, spoken language is much messier. But when we talk about deploying robots in human spaces, speech is really the modality we're envisioning. And automatic speech recognition is not the answer. Not only does it fail often, it's also been widely shown to perform less well on different voices, including women's voices and people who aren't native speakers of Midwestern English, people outside a fairly narrow age range, and so on. So if we don't want to deploy agents that perpetuate existing inequities in technology, we need a better approach. Here's an example of a different way that spoken language can present problems compared to simple sort of text-based data.
Meaning objects seeming like vegetables. This one is cucumber.
And you can see when you ask somebody to describe things using spoken language, you get something that there's quite a lot going on compared to something like this, which is what you get when you ask people to type things. And as I said, one of the typical approaches is to use automatic transcription, but that doesn't always work out well. In one of our data sets of spoken language, we found that transcribed text was usable about 67% of the time, which is not bad, but it's not really sufficient for language understanding purposes. So just to give an example of why we don't want to rely on speech-to-text models, here's a sample spoken description we got from a crowdsourced worker when asked to describe this object.
White decorative plate.
So here the worker said a white decorative plate, which is relatively clear to us because we can see the object the worker is describing. However, when we put that into Google's speech-to-text API, we get an utterance that has nothing to do with the object that we're trying to ground the language out for. And that's largely because standard text-to-speech doesn't have any mechanism for taking the physical context the language is grounded in into account. Whereas what we really want is something where the grounding model can take both the speech itself and the sensor inputs about the objects in the environment into account when trying to understand what the person is trying to convey. But spoken language is just another sensor input, and it can be handled similarly, at least in theory. Given that I've been describing relatively general learning approaches, it should be possible to learn groundings that directly connect speech to other perceptual data without using any intermediate textual representations. And of course, one of the problems is there are relatively few data sets designed for this particular problem, with both speech and sensor data that includes depth and things like temperature as well as images. So our initial data set Gold, which we call Gold, has about 16,000 spoken descriptions and 16,000 typed ones. And the spoken descriptions include automated transcriptions, just for comparison purposes. So these sound files can be used as direct inputs to the manifold alignment learning systems I described. And we tested this a few different ways against several baseline mechanisms for encoding speech. But the main takeaway was that learning directly from raw speech using state-of-the-art speech encodings outperforms learning from transcribed speech using the same encodings. That's not strictly surprising, since transcription is a lossy version of the spoken descriptions, but it dovetails nicely with the need for speech as a better robot interaction mechanism. And I want to emphasize here that we're using featureized speech to do language grounding directly without going through any kind of textual language. Now, since handling speech as percepts is partly desirable so we can handle differences introduced by speaker variants, in order to more fully understand the nature of the data we're considering, human annotators went through all the speakers in the data set and annotated individual voices with information about the speaker, including whether they spoke with accented English, the level of hoarseness and creak present, which are characteristics a voice can have, and perceived gender, as well as information about the sound files they produced, such as how much microphone distortion was present. Because if one of the goals is to understand communication regardless of the speaker, this information helps provide insight into whether we're doing that effectively. And we found that the transcribed data did in fact perform less well for some user characteristics, such as non-native English speakers, but the speech-based model suffered less performance degradation for accented speech. And this implies that learning directly from speech has the benefit of generally reducing the performance bias towards specific subpopulations. We hope a larger data set will produce statistically improved results for other traits. And once we have speech as an interaction modality we know how to work with, it foregrounds another question, which is how do we handle the wide range of modalities robots sometimes have access to? That is, we have access to multiple kinds of sensors of different sorts, but also multiple human input modalities. And I'm claiming that speech is preferred over typing, but sometimes it's easier to pull out a phone or sit down at a computer, depending on the task. So how can we take full advantage of these sources of overlapping information, some of which may not be available at any given time? And our answer so far is to essentially extend the idea of geometric loss that I was talking about earlier by combining it with something called supervised contrastive loss. So we define a distance-based loss function that can be used for an arbitrary number of modalities. Standard triplet loss can't be used for more than 2 modalities and isn't robust to sensor ablation. Our goal is to create a loss function that can handle an arbitrary number of modalities referring to objects in the environment, both in terms of sensors in the robot platform and in terms of different human input modalities, such as speech and text. And to address this issue, we use pairwise distance optimization for all data points. So here's a high-level overview of that approach and the distances used in the geometric alignment loss with 4 modalities. And here, the gray arrows indicate pre-trained models that are frozen, while the black arrows show 3 fully connected layers that are trained. Orange rectangles are negative embeddings and green rectangles are positive embeddings, while dashed lines indicate distances to be maximized and dotted lines indicate distances to be minimized. So in a similar sense to doing language grounding with manifold alignment, we try to bring together all the modalities referring to a particular linguistically denoted concept while separating them from other things with other descriptions. And we show this approach here in green. This is the mean reciprocal rank on a held out test set for the downstream task of object retrieval. That is a task where you say to a robot something like, hand me a syringe, and it has to do the right thing given a set of objects. So here, red is self-supervised contrastive learning, which is prone to overfitting. Orange is supervised contrastive learning, and blue represents a simpler geometric alignment approach. And at a high level, we see that the multimodal approach converges to about the same fairly high level as supervised contrastive learning, but it converges faster by a factor of about 5. It's also remarkably robust to ablating modalities. So if you drop out one or another sensor or drop out speech or drop out text, you get extremely similar curves. And here's another projection of embeddings of 10 randomly selected classes of objects using EMMA. And each modality is separately projected into a 3-dimensional space. So here, each RGB and depth image is associated with several language descriptions, which is why we've got denser plots for text and speech. And you can see that EMMA successfully encourages all 4 modalities to live in a common manifold, allowing accurate retrieval even when modalities are missing. So I've been discussing mechanisms for grounded language learning that are very flexible. We can swap in different learning approaches, different language models, and even different modalities for human input. But that flexibility makes the approaches I'm describing very data hungry. And it's already difficult to collect data for human-robot interaction. You have the difficulties of running human trials, but you also have to have a running robot that's performing consistently, which isn't always easy for large N trials. And it's even harder if you want to collect data like speech in a variety of settings, because it's not easy to just haul the robot into a hospital room, for example. So I'm going to talk about some work that's intended to make that process more scalable. Simulation to reality is the whole area in robotics of learning things in simulation, then applying the learned models to real physical problems. And it's difficult to apply for human-robot interaction problems because the robot needs a simulated person to learn from or someone in virtual reality. And that's the idea I'm going to talk about, using virtual reality settings to accomplish learning. Broadly, the goal here is to build a simulation environment where humans and robots can engage in robotically realistic interactions. And a lot of the time in HRI, the goal of simulation is to learn more about the human side of these interactions, for example, by training a person in robot use. But our goal here is actually the flip side, to have a robot learn from the interactions using simulated sensor data and real input from people in the VR setting with it, most notably including spoken language interactions. And this is an example of a setting where speaking is easy, but typing is hard. We're working with this interface where real people can interact with virtual agents, either using a cave setting or off-the-shelf commodity hardware like gaming headsets. And this makes it a lot easier for a variety of people to engage remotely. Meanwhile, the agent is receiving simulated perceptual data, as in the middle image here, along with the person's speech and motions. So this way, the entire interaction can be performed remotely and then stored and replayed using different models for the robot's sensing capabilities as needed. And when what the robot has learned is then transferred to the real robot in the physical world. The way this simulator is built, it's essentially a combination of Unity to do rendering of the environment for both the person and the robot, and a combination of ROS and Gazebo for actual robot control. And one of our design goals was not to need to write separate code for the robot in the simulator and in reality. So it's key to note that as far as the robot is concerned, it's receiving sensor input and conducting actions, and no part of the robot system knows or cares which setting this is happening in, which is good because the ultimate goal is to be able to go back and forth between virtual and real settings seamlessly. And the fact that we're doing all the simulation in Unity has significant advantages for fast prototyping. It means we're able to use a variety of sources for scenario development. So this scenario is the main dining hall at my institution with a lot of individual objects that can be interacted with, like if the robot is being given sequential instructions for collecting a meal for someone. And here the picture on the right is a picture of the actual dining hall. So you can see that the simulation is fairly detailed. There are also a lot of other places to draw from. This is an indoor scenario from AI2 Thor, which is a set of interactive environments from AI2 developed specifically for embodied AI work, containing some 120 indoor scenarios and thousands of assets. And we're focusing on making the sensor inputs for the robot accurate because people are already really good at seeing something in virtual reality and saying, oh, I'm obviously in a kitchen, and continuing to act accordingly. So broadly, the experiment we're currently running is one in which people are asked to describe a variety of objects in the environment, then asked to instruct the robot through the process of performing a task with them. Here, that's packing a lunch. And when we've collected data from people doing this, the next step is to set up approximately the same setup in a physical environment. And it doesn't need to be exactly the same setup, just something similar, and see how well the robot can follow instructions for that task without additional training. And that physical transfer work is currently underway. Then we can iterate on improving the simulation where it's necessary. And of course, all of this depends on using the learning methods that I described in the first half of the talk. And one of the things we're working with in that experiment is the fact that labeling the object a person is referring to is a kind of supervision we don't want to deal with in real deployments. We need to understand, as people do, we need to understand when people are talking from modalities like gaze and gesture, what they mean when they say, for example, this is a first aid kit, or put the tomato in this basket. When people are talking about a variety of objects, we don't necessarily want the robot to prompt them for each object. So one of the studies we're doing is trying to understand how we can use gaze and head pose to understand what people are referring to when they give us grounded language about objects. And the first thing to try here, the naive approach, is to consider the vector of someone's pose and how it intersects with objects. And here we're using point clouds obtained from a Kinect in both simulation and reality, and just asking what the angular distance is between the gaze and the points that comprise the objects, where the shortest distance is assumed to be what the person is looking at. So here the blue bars represent ground truth, the time that we know that a person is actively describing particular objects. And it's possible to see a relationship between the pose and the ground truth object, but this naive approach turns out to be messy, because people move their heads and eyes quite a lot when they're interacting with someone or something like a robot. So we then, and it's worth noting here that we can use the same experiments because everything that happens in simulation is captured. So we never need to rerun experiments with a new set of participants or anything. We then shift to using an existing Bayesian approach where we try to take into account the previous point that was being looked at And the idea is that each candidate object accumulates interest from the gaze until one of the possible targets reaches some threshold, where we're using Bayes to estimate the posterior. And this prior makes targets that have been looked at in the preceding time more likely to be chosen. So it functionally just smooths out the noisy gaze data we saw previously. And we can see that applying this approach gives a cleaner idea of where the participant is looking, and that by and large, the calculated target for what a person is talking about overlaps pretty well with the ground truth. So from that, we can conclude that we can hopefully use people's gaze and head pose to understand what they're referring to when they say something like, "This bread is for making a sandwich." And the real question is, how well can we learn the ground language about objects using just head pose to label the specific object that a person is describing? So for learning, we use the learning over speech method described earlier. And here we're using mean reciprocal rank, which is a measure to evaluate systems that return a ranked list of answers. And we perform reasonably well on an object retrieval task in which somebody says something like, "Place the apple in the basket." And the system has to use the learned model of language to correctly identify the task from a set of alternatives. And I note here that the objects on which we perform poorly, which are the apple and the mug, are comparatively smaller and somewhere in the middle of a cluster of objects. So it's intuitively more difficult to determine what's being looked at. And while that work is relatively successful, it's not quite as interactive as we'd like to see. We want to know whether the robot can engage in a more direct interaction with a person in both virtual reality and reality. We're pushing a lot of our language-based experiments into a makerspace setting, which has the advantage that there are a lot of different kinds of interactions and tasks that can occur. So next we consider a small-scale joining task in which a person and a robot are working together to build a simple circuit using conductive putty. And a lot of the time in shared manipulation tasks, we have the human and the robot working in a shared workspace and maybe doing some handoff, but not directly working on the same objects at the same time. So we're exploring not only how well our simulated and real duo here can build the circuit, but how well the actual virtual environment is working for understanding the robot's capabilities and for how people find the interaction. And here the interaction is actually flipped, and the robot is providing grounded instructions to the human using language, asking for components and asking the person to move the blocks around rather than focusing on human speech. And we find that very broadly speaking, from the human's perspective, the tasks were really pretty similar, even though one was in a mostly unfamiliar virtual reality setting and one was working with a, again, mostly unfamiliar actual robot. Most people found the physical setting more comfortable, but other than that, the reactions of our pilot group of participants, it was about 20 people, was surprisingly consistent, which hopefully means that the human data we're collecting in the VR setting will translate well to the physical world. So I've talked about learning from grounded language and learning to perform tasks from grounded language, and some about using simulation to extend the reach of HRI experimentation. There are a lot of directions to take this work in future. For one thing, we want to extend the meaning of language grounding. So grounding right now means observable state, and the semantics of groundable language are much richer than that. If somebody says to a robot something like, "I'm lost," it's not solely a declarative statement. The correct answer isn't to be like, "Okay, now I understand that you are lost." The correct response is to say something like, "Where are you trying to go?" But that's grounded in an understanding of the idea of physical locations. And there are a lot of people working on this kind of language implication, but it's still not a popular topic in grounded language. Meanwhile, there's a robust conversation happening in the machine learning community about bias and discrimination in learned systems. And part of what we're working on is finding ways to collect more broadly representative data and learn from data in broader ways, in the interest of bringing some of the ideas from those conversations into the HRI and language space. Broadly, learning grounded language is a complicated space that has a lot of associated components and, draws on a lot of fields being worked on by a lot of very talented people. And all of the work in this talk was done with a large set of talented collaborators and students who get credit for a tremendous amount of the work here. So I hope this has given you a bit of an overview of the work we're doing in this space, and I'd be delighted to take any questions. Thank you.
Thank you, Cynthia. Okay, if you have some questions, you can just tell me. I'll give you the microphone, and Ted's also going to write it in the chat.
No question in the chat.
Oh, okay. You can also
Speak it up.
yeah. So you mentioned about thank you very much for your very impressive talk. And I have a question about the audio. So the audio indeed is a very interesting, is a very important representation. But I think there are some questions for especially for object learning. For example, like once we talk, we speak a bunch of words instead of just phrases for that object expressions. So, so there will be some issues for like a conversationality. So if I said, give me some hot tea and bread, so how can we run this kind of like conversational instructions? I can compose a lot of objects in one single sentence and a single audio. So I think how do you think about how do you handle this kind of problem?
Okay, so I think I understood most of that with the help of the question in the chat. So insofar as I understood it, generally speaking, compositionality of language grounding is a significant issue that we've dealt with in a variety of ways, having to do with separating out and parsing language to try to identify individual components. And here we're just talking about something like objects. So if you say something like, give me some hot tea and bread, then we want to break that down into 3 elements. We want give, we want tea, and we want bread. And that's not a problem that's specific to audio. People do that when they're doing typed text or transcribed text as well. And we use some fairly standard natural language parsing approaches to try to address finding the elements of language. But yeah, generally speaking, if people are talking kind of nonstop and doing sort of complex continuous language and compositional language, then we run into problems with subdividing it and figuring out what is associated with what, that we're hoping to partly address with things like gaze and gesture, to sort of, which are some of the modalities that humans use to kind of work out what people are saying when they're going through a number of things compositionally or in sequence. It's not in any sense a solved problem, but it's not really a problem that's specific to audio either.
Thank you.
I don't know that that's a very satisfying answer. It boils down to we're working on it, but.
Yeah, sure. I was wondering if you have any insights of how to use to speech, like the tone of the speakers and yeah, etc.
Is it possible to repost that? How do we use rich information like tone, etc. in audio? Yeah, understanding things like prosody and tone is a really interesting question, because as you say, speech is a lot richer than text. There's a lot of sort of multimodal information and meta information. And broadly, I think my goal is to treat those as input modalities, find actual featurizations of them and add them into this kind of multimodal learning where, I mean, we're handling combinations of speech and text and different sensor inputs. I think adding prosody or adding any kind of general rich additional signal in language as something that we can retrieve via features and use as part of the multimodal inputs as an additional mode has a lot of promise. That's how I would tackle it.
Thank you.
Great, thank you, Cynthia.
All right. So it is my great pleasure to introduce our next speaker, Dieter Fox. He has pioneered many contributions to probabilistic state estimation, RGBD perception, and machine learning in robotics. He's a professor in the Department of Computer Science and Engineering at the University of Washington. And since 2017, he's also a senior director of robotics research at NVIDIA, where he's bridging academic and industrial robotic research. Yes, please, Dieter, the floor is yours.
All right. Thank you. I just want to make sure I'm not muted anymore. Hi, everybody. Thanks a lot for inviting me over. I think this is a really exciting topic and, of course, a very hot topic going on right now. So what I want to talk about is just some topics, 2-3 projects related to how we use language for robot manipulation tasks. And I think I'll leave plenty of time, hopefully, for discussions. So I have till, what was it, 1:45 total, is that correct? Or 10:45 a.m., is that correct?
Yeah, that's right.
All right. All right. So there are different aspects on how you can use language in robotics, right? One is, for example, you can use language to provide you maybe some kind of higher level common sense reasoning. Another aspect is we need to actually ground language to things that the robot can actually then perform in the real world. And also, as Cynthia, for example, showed, I think really nicely, is that language can also be used very well in kind of a very interactive setting, right? Where you're not just setting up a task for the robot, but you're actually kind of talking to the robot as it's executing a task. And I'll give also one brief examples from a project we did in NVIDIA recently on that topic as well. But first, let me start with how we can use these large language models, for example, to provide kind of higher level reasoning, structure, and context for robotics task solving. I'm sure everybody has seen a lot of this recent work using LLMs for robotics kind of task planning. Very well known, for example, also the SEIKEN work coming from Google Robotics, the Socratic models. And before that, I think typically how we used these LLMs was just kind of to embed some language input and then use these embeddings, for example, to align them with visual information using models such as CLIP or so. And what's new about these kinds of models is where we're actually using language really for kind of higher level reasoning to do things that typically in robotics we used to do using explicit planning and explicit modeling of the environment. The problem with these existing, let's say, for example, task and motion planning system has always been that, of course, you need to explicitly model everything, right? And if we want to move robots into more open-ended environments, into real-world settings, then, of course, they should at least be able to do reasonable things, even if you give them a task that hasn't been beforehand fully specified. And that is where the power of these large language models really come in. So the notion is really leverage common sense knowledge. And the most recent work has really also gone on taking advantage of this prompting mechanism for large language models, where you provide some kind of input prompt context for the system, and then the system more or less just uses its, let's say, probability distribution over text in order to expand that and that example that you're giving, or that partial text that you're giving, in order to generate a complete portion of text. Recently, this, of course, has even been expanded to generating code, Python code, and things like that. There is the work here, the code as policies, is some very recent work on doing this. And I want to talk about one project we did over the summer at NVIDIA that was kind of in parallel to that is using kind of a very similar notion of that. And this is the prompt work. Ishika, I think she did an internship with us over the summer, and she also has a poster in this workshop. So if you have any follow-up questions or so that I might not be able to answer, so feel free to please talk to her, because she's the one who really did this work. But the idea is that, again, we want to use these large language models, not just to give kind of a language description of common sense reasoning, but actually to generate code. So we want to take advantage of these recent developments. And the advantage of generating actually explicit Python code is that it can be, some people argue it can be understandable by humans, but I think we're talking about a specific class of humans here. But also what's important is that this kind of structured code system is, of course, much closer to something that can be executed on a real robot. A while ago, we actually did a work with Cynthia, who just gave the presentation before me, where we used categorical combinatorial grammars in order to do reasoning about robot execution and grounding language. And there's some interesting connections here with this line of work as well. What's different about ProgPrompt from some of the previous work, for example, if you think about work like SayCan or so, where the language model is used to generate more or less kind of all possible future worlds, so all possible actions the robot could execute, and then feedback from the environment or from the perception system or the learned policies is used to figure out which of these make most sense, reasoning jointly about the generation and then the discrimination among these. Here, what we wanted to do is we wanted to actually prompt the language model to constrain the things that it generates by already taking into account what are the things that are actually possible in this environment. So we use Python constructs, like we importing statements to provide a list of skills that the robot can actually execute. We can also reason about the things that are visible or that are present in the world using lists in this description, and also using assertions in order to provide the system with some abilities to reason about or generate things like pre and post conditions of certain actions when they are applicable in the real world. So what I'll do is I'll just give you an example for how this works. The cool thing is this is more or less just using an off-the-shelf model. So, and Ishika and Vals should correct me, but it is my understanding that there was no real learning in that sense involved, right? It's just kind of finding out what is a good way for prompting these LLMs in order to get the results that we want. So there was learning on the humans to figure out how to prompt these models. So how it works is as follows. So first we need to generate this kind of prompt context for the model. And in this case, we have first provided with the kind of actions that are available to the robot or to the agent in the environment, objects that are there, like whatever, garbage can, salmon, microwave, things like that. Then we give it an example task, like throw away lime, where we explicitly write down what would be the sequence of actions and what is the structure of the code that we would like to see. It turns out that providing actually comments for the code helps the language model to more explicitly reason about that. And then we just say, okay, the next task is microwave salmon. I'm not sure how many people would actually want to microwave salmon, but that's one of the tasks that is given in this environment. And now we'll just feed that to the LLM, and it spits out a plan that looks like this. Okay, where again, it now writes out the definition of this function microwave salmon, and it actually the steps it's providing are extremely reasonable. First, you walk to the kitchen, find the microwave. There's these different constructs. So there's again, it generates comments in let's say natural language. It generates actions that the agent should execute. And again, these actions are taken from the list that we provide in the prompt, so that the system doesn't reason about things that the agent cannot perform. Assertions help us to use state feedback about what is the current state of the world in order to execute certain tasks. For example, if you want to open the microwave, you first need to assume that you're close to the microwave, otherwise you can't even reach it, things like that. And then also, there are, of course, let's say recovery actions or conditionals that say, well, if you don't have the salmon in your hands in this example, for example, then you first got to find the salmon and then grab the salmon. Okay. And then as we're executing that task, so the idea is that we now go into, this is a simulated world. This is an example from, it's called virtual home. Okay. And then we want to execute a certain task. And then what the environment provides is the current state of what the agent sees about the environment. So for example, it says, well, you see that the microwave is open and you have salmon in your hand. Okay. And we're also using the LLM to check how the environment state maps to the assertions that are written down in the program itself. So here we're showing, for example, an example for how an observation from the environment, like what you see, what you have, connects to assertions about the state of certain objects. Okay, and then we can feed into the LLM another semantic state that is now the actual one given by the environment, and the LLM tells us, well, in this context, assert that the microwave is opened, which is the state that we need for the plan execution, is correct, and we can then go to the agent and actually execute it in the environment. Okay, so again, in this case, the LLM said, given what the semantic state of the environment is, microwave is open is true, and therefore the next action should be put the salmon in the microwave. Okay, we can now execute that and feed that back to the environment as the next action that the agent executes. Okay, and this is then what it looks like. Imagine if the microwave was closed, then the LLM would have said the assertion is false, and then it would have gone into the different branch of the execution and then opened the microwave, and that would have been the next state. Okay, so this is how the language model on the one hand side is prompted to generate plans, but also to figure out which of the assertions and assumptions in the plan executions are true and how to match that to the environment. So this is something that is new compared to a lot of the previous work, where again we can tell the LLM what's possible so that it only generates possible things, and also we can provide state feedback to the system during execution. Here's an example of what it then looks like. Execution is microwave salmon. The salmon looks it's actually boxed in kind of a package, but that is how it's being phrased in that environment, virtual home. So open the microwave, has the salmon in the right hand, puts the salmon in the microwave, and then stands there, thinks a little bit, I guess, closes the microwave, presses the button on, presses the button off, opens the microwave, and has the cooked salmon in the hands. Okay, and it turns out that the system actually, the good thing is here in this case, the grounding with the environment itself is pretty simple because it's given directly by the virtual home environment itself and the agent. But compared to previous work that was done, I think, by Peter Beal's team on using language models for decision making, they achieved 0% success rate on these longer term complex tasks. And we are now with this model going up to 34% success rate. Here's one example on also doing this on the real robot. It's, I assume we all agree, it's a pretty simple task, which means, for example, in this case, sort the fruits on the plate and the bottles in the box. And we provided certain actions like grab and put in. And we also provide the observations for detecting the different objects. And then we just feed that to the LLM, and the LLM generates the program, the task sequence that should be executed. So in this case, then it says, okay, first put the banana in the plate. And then there's another fruit, the strawberry. And finally, bottles in the box. There's one bottle there, puts it in the box, and there we go. Okay, so this is kind of just showing that with the appropriate grounding that you can get in the real world, this can be executed actually in the real world. Okay, so this is an example for, I think, how these LLMs can be used very well for, let's say, higher level reasoning, common sense knowledge kind of reasoning. The key limitation, I think, here is really that grounding this in the real robot perception and execution system, first of all, typically is still done manually, but at the same time also that actually the really hard part is how do we get well-grounded skills and policies that the robot can execute. Towards this idea of grounding language in real-world actions, I want to briefly talk about some work that Mohit actually did. I'm sure some of you have heard about the clipboard work and also the more recent extension to perceiver actor. And here, I think the real notion is that we're going to use language not so much to generate plans and do longer term reasoning, but really kind of to convey what the robot should do, kind of through a description of the task or the goal. But also, I think in this case, what's important is that it kind of provides language, the language provides context during demonstration of a task, so that the robot can learn multiple tasks with a single network. That was one of the main ideas behind this clipboard work. And that was very much inspired by Andy Zhang's great work on the transporter networks. I'm not going to go into any details here, but the idea of this is kind of, you have a top-down view, you have a 2.5D action space where it's about XY position of the gripper and an orientation. And you look at tasks that can be specified by, let's say, where you should move the gripper or the suction cup in order to achieve a certain task. So it's kind of pick and place setting, which is actually very relevant in many also industrial tasks. The key limitation of the original transporter network was really that there were no semantics, which means you could you would give it demonstrations, but there was no generalization beyond the demonstrated task, which means the network had to really be trained on every single task independently. The goals were just provided as images to the robot. So we wanted to see how we can combine that with language and thereby really extend the application scenario for this. And that brought up, of course, CLIP, which, as we all know, learns embeddings for images and words that are coupled, that were coupled in the training phase through captions. But the nice thing is that it kind of generates embeddings for these that are kind of connecting visual information with semantic word information. Not going into the architecture, at this time there were like this two-stream architecture where there was a transporter net stream and then a so-called semantic stream that used the CLIP encodings both for the language and for the images. I think by now there's been follow-up work, for example, on extending this, for example, to even map to, for example, CCGs or the Weimar work, where they're using transformer networks in more complex settings with more explicit language reasoning. But this was kind of the first attempt at this, and the results actually worked really well. Again, assuming that most of you have seen this, these are different kinds of tasks that Mohit then set up on a real robot. What's exciting about this is that this works actually from very few demonstrations on the real robot and not only in simulation, where mostly what you have to specify is to, for example, the stacking task. If you want to put the blue block on the yellow block, you specify where the gripper has to go to pick up the blue block, and then you tell it where it should drop the blue block in order to put it on the yellow block. Okay, here's just some examples how this then works.
Put the orange block on the blue block.
And again, this worked robustly. What's interesting is that from the language, we got two key things. One was we were able to train a single network on all these tasks. And that takes advantage of the fact that the language during the demonstrations helps the system to disentangle the different tasks, right? And learn kind of a single network that can then is conditioned on the language input as well. Another advantage that we got out of this is that sometimes we saw that the network was able to reason about, for example, new color combinations that haven't been seen in a certain task. So there was some transfer of information from one task to another. Okay, I'll actually skip these in the interest of time. Sweeping here, this is, I always like this as a roboticist because of the precision. So picking up these cherries requires you to pick it up at the stem so that you don't squeeze it. And the architecture was able to actually do this pretty fine-grained manipulation here. Here were some results on the RL benchmark. And you can see this is the score on some of these RL bench tasks. Where left would be if you only use the transporter networks, but without language, of course, there's often, it can only guess what might be the task actually. If you just use the clip network, you get 76%, 76, I think, score percent success rate. If you train clipboard on every task independently, 85, and we get actually a slight improvement by training a single network on all the tasks. So, which is nice because usually what you see is that multitask systems do not perform as well as single task systems. But in this case, again, we get some transfer across tasks. Okay. So one of the key limitations of this work was that it's kind of this 2D reasoning, which means top down, X, Y, and orientation. So in his paper here at CoRL that Mo is going to present, I think, you said Saturday, New Zealand time, is perceiver actor, which is the idea of moving all of this to 3D, and of course, more, let's call it modern transformer architecture, where here's the idea. I'll just give you very quick ideas. This is kind of the perceiver actor network where the input is, the key is the scene is represented as a 3D voxel space. These voxels have a 1 centimeter resolution. Okay, so we have 100 by 100 voxel by 100 voxel cube, which is a meter by a meter with 1 centimeter resolution. These voxels are then encoded into these patches, where each patch represents a 5 by 5 by 5 centimeter cube. So that results in input to the transformer network of 8,000 of these tokens, voxel tokens, or patch tokens. And these are then fed together with the language encoding into the transformer. So we have a pretty good number of patches, 8,000 patches in this case. The idea in architecture is very similar to vision transformers, just that in this case it's 3D rather than 2D. And then in order for efficiency reasoning, we use a perceiver I/O architecture, which does cross-attention within the latent space. So we have, in this case, 2,048 latent vectors that are during training initialized randomly, but then they are learned end-to-end as part of the training. And then the system outputs at the 1 centimeter resolution, 64-dimensional features for each grid cell in this voxel space. And each of these features then is fed into an MLP such that the output is, for example, for each grid cell, whether that is the next gripper pose, kind of like a heat map over the 3D space, this is XYZ, whether the gripper should be opened or closed, the 3D orientation of the gripper at that position, which is discretized into 5-degree resolution in the 3 orientations, and then also whether by moving there, the robot should avoid collisions or not, because if you want to pick something up, then you actually don't want to avoid collisions, okay? And all of this is, again, then fully trained end-to-end, where the input is a voxel map and the output is where the robot gripper should go in the 3D space. Let me just give you one example here. On the left is you see the real scene. On the right, you see the voxelized scene. And this red dot that you see above the tomatoes here, that is kind of, let's say, the heat map over the output of the transformer that says this is where the gripper should go. And on the right side, you will also see a visualization of the gripper pose, which now represents the full 3D position and orientation of the pose that the system outputs as the next target for the gripper. And once it reaches that, we feed the next voxel space into the transformer, and now it generates a new pose for the gripper, and the robot moves to that one and then closes it in order to pick up the tomatoes, because the task is to put the tomatoes in the top bin. Okay, and this can be done repeatedly. The nice thing is it has some of this kind of closed loop notion, and because the reasoning is done fully in 3D, that is also, for example, robust to changes of the camera position and things like that. Okay, I think you get the idea here. Here's an example, now doing this in the real world. Press the hand sign. And so in this case, what it kind of does is more or less like you can almost imagine like object detection or tracking, right? Because it just needs to figure out where that is. But you can see different elevations can be handled because it's a full 3D reasoning system now. And also you can see the gripper orientation is not always just top down, but it's sometimes really coming from the side and things like that. All right. And the results, talk to Moit, look at the paper. Of course, it's better than the previous state of the art, which was the 3D conf network by James and others on the RL bench. And we're now getting 43% success rate on these specific tasks that require full 3D or 6D reasoning. Just one quick example. How much, I just want to very briefly go through this. Is that okay with the organizers? And that is just, it's related also to the work that Cynthia presented, where I think it's about how can we kind of real time give feedback or guidance to the system rather than just specify a certain task. So this is work that we did with Pratyusha, who was an intern at NVIDIA also last year. And for example, in this case, imagine you want the robot to move the fork into that mug here, but you want it not to move it over certain objects because they might be too brittle or fragile or something like that. So how can we then give guidance to this? And there's, of course, also work on using a typical approach is inverse reinforcement learning for this. Here we used a slightly different approach where the idea is that during motion generation, if we just look at this component here, is what we're trying to do is, of course, we're trying to do optimization of a cost function when we try to generate the trajectory for the robot. And there is, in this case, there are the different components such as what is the typical cost like if you want to move to a certain location, the standard trajectory generation cost. We also have to take into account collisions. There might be choice limit costs. And in this case, we also have language condition costs that give you kind of additional guidance for what should be optimized. And in this case, this is done by, it's kind of also a top-down system where imagine you take as input a top-down view on this scene, and then the language input is also go to the left of the blue colored can. And then we say as output would be some trajectory like this, where the different colors indicate kind of the cost to go in order to reach this position to the left of the colored can. Okay, and here's some kinds of different information we can encode in this. For example, go to the top of the bleach or move behind a certain object. Also, costs like move faster can be encoded in this way, or things like do not go near the dangerous bleach, which then imposes a high cost, of course, on top of the bleach, but lower cost in other spaces. And these costs are then combined with the original motion generation costs. And then we're using MPPI, model predictive control, in order to do motion generation, taking that into account. So on the left, you see the original motion of the robot. And on the right, you can see the motion now taking that additional cost into account where we want it to not move over the span, for example. Okay, so this is just one example. Here's another one, like how the robot should move first to the bleach bottle and then execute a different task. So this is just one example of a different use of language, right? Which is more real time and how we can use it to adjust policy executions. So let me come to a summary. So I think it's really exciting, these LLMs, of course, because they are really useful for providing this high-level reasoning and plan generation knowledge. I think, of course, there's various open problems in this whole domain, right? First is, how can you ensure that the thing that the language model provides or the plan can even be really executed on the robot, or that it's safe and things like that. So I don't think there's been a lot of work on that. And that, of course, is going to be a very important aspect. One other thing, I think a caveat we should all be very aware of, that in the end, they give us high-level context, but from my perspective, actually, The really hard task about robotics is executing those things in the real world, which we could call here the grounding problem, right? So for example, when you look at the SECAN work, where they use the language model for some sort of planning in these environments, but then actually in order to train the skills that are necessary to execute it, they had to generate 68,000 teleoperations and 276 additional autonomous executions on real robots with behavior cloning in order to train these skills. So I think overall at this point, the main effort is really still on the robot skill learning rather than actually the planning level that the LLMs provide to us. But I think as we get better and better at the skill stuff, this will become more and more relevant. And then, as I said, different uses for language models are for task specification and to provide context for demonstrations, and also kind of for execution. And with that, I'll thank you for your attention.
Thank you for the great presentation. Are there any questions from the audience maybe for Dieter? Yep. There's one.
Anyway, yeah. I just have a quick question because between clipboard and I think the receiver actor, I assume one of them is using this 2D input. The other one, you guys use voxel like 3D representation. I'm curious to find out like how does using a voxel like representation changes the whole dynamics of ultimately getting a robot to do its thing.
Ooh, the audio was not so great. I heard that there's something with perceiver actor regarding the voxel representation. I didn't understand.
I'm just curious. In the second case, perceiver actor, you guys have basically throwing this 3D voxel representation as part of the pipeline. So I was just wondering how does that compare to the early work of using clipboard?
Yeah, he's asking about 2D versus 3D representation. Like, how does this affect the learning?
How it affects it? Well, one difference is that training is slower. It's more memory intensive, right? Because you have these 3D voxels that you have to encode, and then as far we did some checking on the execution and training, and I think actually the transformer part itself, the perceiver part itself is pretty efficient, but the encoding of these voxels takes quite some while. So we're looking into maybe more efficient representations for that. But I think it's important that we do have representations that explicitly have some notions of 3D reasoning in them, because what we see a lot is when you look at some of these deep RL benchmark kind of environments, is that, for example, the camera pose is identical between training and testing. And when you reason about identical train test camera poses, that lends itself very well to overfitting to just 2D reasoning. And I think for robotics tasks, we have to make sure that we're actually reasoning about 3D stuff. So I think this is a pretty major step forward in the capabilities of the system.
Thanks.
And I'll let also, of course, Mohit chime in, because I guess he's in the room even.
Yeah. Is there any final question for Dieter, or shall we move on? Yeah, one last question, quick question.
Thanks for a great talk, Peter. I have a question about what you think the future looks like for connecting language and actions. Like you mentioned, with SECAN, we sort of connected language and action by sort of training all this, pre-training all the skills, and then using an LLM to kind of plan over these skills. But do you think the future will be more of like learning a continuous state where language and skills sort of share the same space to sort of better understand what we should be doing, to better understand how language sort of connects with actual behaviors on the robot?
I think that hopefully, I believe first of all, language is going to be super useful for robots acting, not only like interacting in the same space, but even you could even imagine industrial settings where you're trying to teach or train a robot to do a certain thing. And if you annotate that additionally with language, that's just a a very succinct way sometimes for providing information, right? Like saying something like, oh, and wait for 10 seconds after you did this, or something like that, right? So I think at this point, again, one of the key bottlenecks is that our robots aren't actually that great at executing these kind of skills. But as we're making progress there, I think also the training and the connecting of the language with these actions are going to be easier and easier, and you can train that in the real world together with the robot.
Okay, great. Then let's thank again Dieter for a great talk. It's a pleasure to introduce our next speaker, Jen Oh. She's an associate research professor at the Robotics Institute at Carnegie Mellon University, where she works towards creating robots that can coexist and collaborate with humans in shared environments while continuously learning to improve themselves over time through training, exploration, and interactions. And we're looking forward to your.
Thanks for having me. Sorry about the background noise. So yeah, I'm very excited to talk about our recent work on using multimodal inputs for robot painting. So, okay. And this work is done by many students and other collaborators, so including Jim McCann, and heavily led by Peter. Peter is my PhD student, and Jishan, Bib. So today's talk, I will mainly focus on some of the work that Peter has done and Jishan and Bib were leading, and all the other students were also collaborating. So, okay. So let me first kind of make the connection from my previous work, which was done on navigation and how that translates to painting domain. So the language used in robot planning in navigation was direction following. So when we hear direction, something like navigate to the building behind the car, imagine you are given this command, then even without any visual perception, we can start kind of planning because we can imagine the space. So the language actually specifies the semantic goal. So using this language as a guidance, here's a robot. You can see maybe there is a car somewhere, and then there is a building that is behind the building. So this is kind of imagine the space, and then we can kind of have an initial plan. And of course, whenever you go to a new location, this actual path will change. So that's when visual perception is needed, or other kind of sensing to understand the current context. So in this case, if you're kind of standing there, the robot is there, and see a partial object, which looks like a car, and then using the language again to hypothesize the space, but more aligned with the current context. So this is language grounding. Okay, so how do we do kind of similar work for painting? So let's say someone says, hey, I want to paint Albert Einstein is dancing. Okay, so we as a human, we can kind of visualize this image like Einstein. We know how he looks like, and we also understand the meaning of dancing. So again, the language kind of specifies the semantic goal, like maybe high level, kind of an abstract goal, which can be translated into a really diverse visual representation. So these are some of the examples. Okay. So in this case, so where the vision comes along here is there has to be a visual feedback, because painting is like a continuous process. So you take actions and then observe the canvas and then optimize again towards this semantic goal. So there is a planning going on, taking this visual feedback over the canvas state. So it's a planning problem where the states are defined in terms of like how the canvas is changing, and the actions are the brush strokes. Okay. So you see this now common parts. Okay, so and then I'm gonna introduce the Frida system. So we designed this Frida to promote human creativity. So meaning that we are not really interested in creating an AI or robot. It is an artist itself. I mean, that has also separate meaning, but for our research, our goal is to help human creativity. So it's personally motivated. So this would be a great tool for people like me who wanted to be an artist, but wasn't born with the skills. So so toward that goal, we designed the Frida to paint what we humans want to paint. So how do we do that? Is supporting multimodal interface. So natural language description is like a good way. And then we can also provide the sample images or sound, or gesture, many other things. Okay, so so just to compare with just the AI generated artifacts. So everyone is familiar with DALL-E and other like very cool tools. So, but the artist is like, it's not just the purpose of art is not just to create pretty pictures. So we believe that there is a social message or something that people care about. So these are kind of prompts that I wanted to use to generate art. These are the topics that I care about. And then when I use the same this prompt on DALL-E, these are the images I get. And I can tell these are very high fidelity images. The image quality look good, but the contents are not something that I can resonate with. So with the Frida, I can maybe generate the contents that are more aligned with what I was thinking about when I look at the news and what's going on around the world. Okay. All right. So, and on the robotics research side, this is very interdisciplinary area, and people think this is like maybe outside the robotics topics, but surprisingly, it involves a lot of core research problems in robotics. So one is computer vision and perception, and then learning and control, how to use the robot arm and the hand to do the brush strokes. And then the planning part, which I explained, and the planning is something that I'm going to talk a little more in this talk, and then also how to address the sim to real, simulation to real gap. This is another core research challenges that we are working on in this problem. And then also supporting shared or human-robot collaboration, or it can be seen as a shared autonomy. And then the last topic is responsible AIs. Because we are generating these contents, we'd like to be more aware of the potential benefits or possibly negative side effects too. Okay, so let's look at what has been done in this space. So people have seen a lot of great results recently done by these giant companies. These are amazing results, but these are virtual generation, meaning that these can be printed, but not painted. So painting requires some planning there. Okay, so there are some planning-based approaches as well, including one of our work. But these ones, we didn't use the brush stroke primitives that are realistic enough. So when we actually use a robot to paint these outputs, the results didn't really look good. So for the brush stroke modeling, there's actually a lot of work done in graphics communities. So the very, very high fidelity, good quality simulation. But again, it is in simulation. So the sim to real gap is real in this case. And then there is a very recent paper that was published. So they used the real robot, but they painted on an iPad. So I'm going to kind of put it in between sim and real because it's not really the real painting using paint. And then also the quality of the output, they're decent, but yeah, again, it's not really realistic. And then there was another pretty recent work, Dream Painter. So they really tried to reduce the gap between simulation and real. So the gap has been reduced, but in a kind of a strange way. So they can only paint something like this. So like very restricted style with the pen. Okay. And then finally, there is very, very engineered solutions that produce very high quality paintings, but these are highly engineered approaches and not generalizable outside their studios, and they are sold at a high price. Okay, so Frida is a more general framework for doing the robotic painting. And one of the earlier approach that we tried was a constraint-based one. So there was a paper using reinforcement learning to generate a sequence of brush strokes. And when we saw this paper, we kind of translated into the real robot and we got this. So the issue was their brush strokes were very, very unrealistic. So for instance, some of the earlier strokes are huge. So it is like occupying, like with one brush stroke, it's kind of changing the color of like half of the canvas kind. So it didn't really close the gap between sim and real. So what we first did was constrain the simulation environment. So the idea is a little bit similar to the Dream Painter. So added some brush constraints. So because back then we were using this $200 robot, so Peter got it during pandemic. So it was the pandemic project. But adding some of the constraints, we were able to generate better painting, but still the sim to real gap was huge. Okay, so the next approach is really having a closed loop system. So starting with the artist's intention. So this is the semantic goals. So like in an earlier example, I used the language. So we could use language description or other sketches or other types of inputs to express what we want to paint. And then there is a robot that's actually taking actions to achieve this goal. So there is a planning aspect. And then there is a visual feedback through camera input. And this is continuous planning process, just like in navigation. So there is an initial plan, but you continuously replan because you collect new information from the environment as you move on. So it's exactly the same thing that's happening. And then for that purpose, we use a simulation a lot. And then there is a challenge to deal with. So how to address this sim to real gap. So there wasn't the basic idea is using the real data to improve the simulation environment to reduce the gap. So the idea is we use the term used in other robotics field, the real to sim to real here. Okay, so that's the general like high level overview of the system. And then I'll explain a little more on the sim to real gap side. Okay. Okay. So the one of the contribution here is to coming up with a differentiable simulation environment by using this very simple representation for the brush strokes. So this is, by the way, some place that we can maybe do even better. Okay. And because it's a differentiable environment, we can also use other operations to augment the space. So use the naive approach could be used a lot of like data, training data to improve. And that's how it was done in a previous work, existing work. And our approach is utilizing other types of differentiable operations to augment this data set. And also during the test time, we use this. So basically, the idea is to get these sample brush strokes to train this param2 stroke model, and then put it on the canvas, and then use this rigid transform to put it in the right place, and then add the color, and then finally render onto the existing canvas. Okay, and then this is the key, one of the key results showing the sim to rear gap. So these are kind of examples of the brush strokes and how they vary depending on according to their length, bend, and thickness. Okay, so here this example kind of shows how the existing simulation, like something like a DPG, which we used for our previous work too, like you can see the difference between the real stroke and the DPG type. It's very much simplified. And then Frida is brush stroke simulation resembled much better with the real one. So, okay. And then also there are some noise in the data, but it also the Frida simulation can handle something like glare pretty well. And then there are other more examples of these results. So these are qualitative results, but we also have quantitative results to measure the difference in the number. But I think qualitative examples really illustrate the results very well. Okay, and then so this is a another kind of sample example to show how this improvement in the simulation environment changes the final output. So this is Peter's friend, by the way. So using these prior existing work directly mapped to the painting was the first one. And then using the constraint-based approach, we got a little better. And then finally using Frida, the simulation is close to the prior work here. And then the real version, which was the real painting, is pretty close to the simulation and the original input image. Okay, and then the second part is supporting this multimodal input. So there is a usage of languages. And this part, I'll just show you some of the results. And here, what Peter tried was using different types of feature, the loss functions. And one thing that we want to argue is when even given a like photograph like input image, what people want is not a printed copy. So because there is a printer, we don't need another printer, which is more expensive like robot printer. So what we want is, given this image, we want the artistic version of this this input image. So based on that assumption, we tried this feature space loss we believe is more matching better with the semantic goals. So quickly, if you compare these two images, the original one and the L2 loss, which is just pixel by pixel difference, the texture matches much better than this one. But based on the user study, these feature space loss results were much better, much more preferred by the audience. So the meaning that's more pronounced in the feature space, we believe it's matching better with the semantic goal. Okay, so this is a quick results based on the Amazon Mechanical Turk responses. So the majority of people prefer the semantic matching. Okay, and then these are some of the examples of the different modalities that we have tried. So like how do we do the painting of a Harbin milk with this type of style image? Okay, and then this is another style image for the same prompt. And then another example, so portrait of a robot artist in 2 different styles. And then this is another one that can take the sketch to specify the composition of the output. And then this is the style image. So 2 soldiers from different countries dancing. So using this composition, and then this was the final painting. Okay, so there are a lot of the future directions that we are working on, but for the sake of time, I will briefly mention the work that we are also doing on the handling the data bias. So a quick question to the audience. So given these 2 rows of images, which one do you think look more American? Like, so yes, we can think about it, but we did some kind of mini user studies. So by the way, these results are a little bit preliminary, so we will have a more concrete results for the paper we are preparing. But based on the preliminary study, the generic stable diffusion generated images are basically very similar to the images that are customized for American culture. So stable diffusion was trained using 2.3, 2.5 billion text to image pairs. And it seems apparently all of those data points are mainly about America. So so when we wanted to customize for different countries, what we first tried was just adding simply like in a country name. So we tried many different countries and then found that there are some problems. So these are kind of preliminary results that we are showing. So the generic stable diffusion given the same kind of prompt, and then this one is our approach for customized for America, and then for these 2 rows, people found no difference, and then we also included like 5 more different countries, and these are our results. And then I will show you some other examples we found. So this is kind of the work that we are currently working on to address cultural bias in the data. And one thing that we tried was the baseline using just appending in Japan, in Korea, in Nigeria, in China at the end of the prompt. There were several issues. So in Korea example, for instance, these costumes are not Korean. So they look maybe a little bit more like a Japanese or some other culture. And also for in Nigeria, this is the prompt is a family is eating together, and this image looks like it's from maybe 50, 60 years ago. So people are all sitting on a dirt floor, eating on the floor. And then this is an image of China, and then Chinese people found this image very offensive because they look very stereotypical Asian people. So, and then when we used our approach, which is a culturally aware stable diffusion, we got the correct custom and also look at how modernized the images are. So this is a quick improvement. Okay. So the idea is fairly simple. So right now, the current approach is just fine-tuning using a very small set of priming images and also doing the same thing for the text support. So what we are doing as a kind of project is to build this small data set. It's not going to be giant. We don't have the resources to do so, but we can create small mini data set for every country and every different types of culture to be able to generate this priming effect on any of the existing very powerful the models like Stable Diffusion. So this is the new data set that we started creating as a project. Okay. And then finally, this is kind of a teaser. So we are having a lot of fun with the robot painting. So we are now doing in sculpting in 3D. So sculpting is becoming really the core robotics technical problems because it is deformable object manipulation, a lot of controlling and tool manipulation and whatnot. So, okay. So I'll leave it at that and then take any questions.
Thank you very much for the talk. Okay, we have time for some questions from the audience. So maybe in the chat question from online. No.
No questions?
Okay, I can maybe ask a question. So your the works you have shown, they are really impressive with the painting, and one can see that it consists of several sub problems like the brushing, the low level control, the sim to real gap, the evaluation, if the generated artistic drawings are good. So which one of these sub problems is currently like the biggest, the hardest, or which you think if you could solve this would enable you to make a big leap in your research?
That's a good question. I mean, there are just so many of the issues. So like the one that we are still working on is reducing the sim to real gap. So what we tried was a huge improvement from the previous model, but it's still not perfect. And also, I don't know if you have seen our robot carefully. The current robot doesn't have a hand. So the robot, the brush was just attached to an arm. So if we can do a more maybe dexterous manipulation or better control, there are many different types of brush strokes that maybe robot can try. So robot's skill, the actual skill set can also grow. That's a kind of maybe even a new research direction that can be taken. And then also paint. Right now we are modeling everything in 2D, but even the painting can be seen as a 3D. And a paint is a kind of a deformable object that is very in between like liquid and solid. So how to understand that better is a kind of a key challenge to produce a really good output. And then one of the challenges that you mentioned is evaluation. So how do we know, like qualitatively, we can say this looks better, but in order to publish a paper, we need quantitative results. So we can do something like a user study, but is that that's very, very expensive. And whenever we generate, we need to ask people's assessment, people's opinion. So evaluation itself on the creativity and also the quality of like artistic output is a difficult one. And then also the quality control, the data bias is a heavy thing because our models are really relying on these models trained on a really, really large data set that we do not have control over. So that's why we are creating this mini data set to do some control over that. And then for the visual challenge and perception task, we are really doing the minimum right now, but that's the whole new area, how to, especially when we move to the 3D space, even painting over 3D structure, you need to do a lot of a different perception and also understanding. Okay.
Nice, thanks. That sounds super interesting. A lot of work to do, a lot of papers to publish. In interest of time, we will move on now with our first panel discussion. We are lucky that I think all our invited speakers so far will be joining remotely. And this panel will be moderated by Stephanie Telex. I think I have pin now everybody, right?
Can you do that sort of in everyone?
At Spotlight?
Yeah, that should.
1 second, almost got it. Peter. Yeah. Cynthia. Is Jacob also there? All right. Okay. Yeah. I think everybody's there. So Stephanie, go ahead.
Awesome. Hey, everybody. It's super exciting to be virtually here. And thanks to the organizers for organizing a really great workshop. So why don't we start with brief introductions from each of the panelists, and then I'll ask some provocative questions, and we can hopefully have some really interesting discussions. And I'm Stephanie Telex. I'm a professor at Brown University. I work on language and robots. Cynthia, why don't you go first?
Cynthia, I'm an associate professor at the University of Maryland, Baltimore County. I think everybody here works on language and robots. I work specifically on language grounding, and I've been working a lot lately on speech.
Awesome. Jackie?
Yeah, I'm Jackie. I'm an RE research engineer at DeepMind. I presented the work on Gato. I have a robotics background and have become, as like a growing interest, have an interest as well in like fairness and ethics in AI generally, including language and interpretability and analysis.
Awesome. Dieter? You're muted. You're muted.
Yeah, sorry, I was muted. Hi, I'm Dieter, faculty at the University of Washington, and also half-time at NVIDIA. I'm interested in robotics, but also language and robotics. So
awesome.
I think that's it.
Jean?
Hi, I'm Gino. I'm an associate research professor at the Robotics Institute at Carnegie Mellon, and I work on navigation and creative AI. So I use language for navigation for some time, and I'm still interested, but now I'm doing the language for the painting and other creativity stuff a little more.
Awesome. Really enjoyed your talk.
Yeah,
Jeff.
Hi, so I'm Jeff Clune. I'm faculty at the University of British Columbia and the Vector Institute. I love all things AI. I've been working on it for a while. I like, AGI and open-endedness, trying to create algorithms that learn forever. Some algorithms that we call quality diversity algorithms, AI generating algorithms, so algorithms that try to bootstrap themselves up to AI or AGI. I was recently at Uber AI Labs and then OpenAI, and now at the places that I mentioned. And so I'm really excited about this discussion and to see all the awesome work that's happening and taking advantage of large models and specifically language models and hybridizing that with the cool work in deep RL and robot learning.
Awesome. And Elaine?
Hi, I'm Elaine. I am currently a young investigator at the Allen Institute for AI in Seattle. And by the end of this month, I will have received a PhD from Cornell University. And next summer, I'll be joining UC Berkeley as an assistant professor. I'm not really a roboticist, but I have a lot of interests in it. Just I haven't worked directly on robotics. My interests are coming from like NLP, so language grounding, language use and interaction, learning algorithms for continually learning through interaction with human users, some other things like semantic parsing and so on. And my talk is, I think, yeah, it's later today.
Awesome. Okay, so I wanted to ask a question to start off that my group has really been wrestling with lately, which is, it seems to me that there's kind of like two high-level approaches to understanding natural language commands for robots. So one is what I'm going to call the say-can approach, which is somehow going from English to a different, smaller, formalish representation of meaning. And the say-can, Google say-can paper, it's about like the sort of planning space of the robot. Sometimes people go from English. We do a lot of English to LTL, English to Padiddle, the planning language. Whatever that language is, that formal, smaller robot-ease language. So that's like sort of option one. Then the other sort of high-level thing approach is sort of to really embrace the deep Kool-Aid and try to imagine the way I've been saying it to my students is like say that English is its own best representation and we don't need any kind of robot ease. We basically want to go from like language to torques, and somehow capture the thing that just does end to end, English to making the robot go off and do stuff. And I, at the beginning of the debate, I was about 80-20 that we needed robot ease, and now I'm about 60-40 that we need to do that, and maybe the doing it all end to end is going to work out. So I guess I really wanted to ask Cynthia and all of you, but Cynthia is kind of my buddy. So like I'll throw it to her first, but I'd love to hear this room's takes on that question.
So that's an interesting question for me because I started off doing the one and have migrated more and more to the other, more and more to the kind of end-to-end system. And I think the trouble with going to robot ease as an intermediary is there has to be some concept of what that language looks like, what you're defining it to be, that has the potential, I think, to limit what you can understand, to limit what you can do with language. That said, I'd be really interested to know if maybe some of the other panelists have ideas on how we can combine those. Because it's very often the case that it shouldn't be a one or the other question. It's very often the case that we can find ways to use pieces of two approaches together. So, yeah,
Jeff,
that's sort of a non-answer.
Jeff has his hand raised.
Yeah.
Yeah, Jeff, go answer.
All right, I'll jump in. I think panels are most interesting when people take extreme positions. And in this case, I'm not doing it just for the sake of argument. I really believe it. So I'm 100% zero on this question, with the 100% being that we should go all in on English to torques. For many years now, I've been kind of giving talks in which I point out what I think is just the most clear and undeniable trend in machine learning, which is that hand design pipelines get void to entirely learned pipelines as we have more compute and data. We saw that originally with vision and language features. We're increasingly seeing that with architectures, learning algorithms themselves, optimizers, et cetera. And I think the best thing that we can do is get out of the way. And if you ask me to solve a problem this year, I would use robot ease. But if you ask me to work on research that I think is true path and is going to lead to really impressive robots, you know, as fast as possible in the order of like 5 to 10 years, like what is the long-term path? Then I think it's working with directly from language to the torics. And that's true for a couple of reasons. One is that language is what separates us from the rest of animals. It gives us compositionality and all the combinatorics, generalizability, planning, replanning. It's a beautiful representation. And so it's got all of these, you know, amazing hierarchical properties. You can operate at very abstract high levels and describe not all, but many low level things. You know, eventually you just kind of do stuff without thinking about it in words. But mostly it's a great representation for all of the reasons. And that's one main reason to like it. And then the other reason is because we have the data for free in the world. Humans know how to describe stuff. They often do describe stuff. Later on, I'm going to be giving a talk on video pre-training where we take YouTube videos, we learn from them. You can also take the captions, the closed captions of people talking while they're doing things, feed that into the model, and it learns how to just directly go from language to actions. And so the data is there and it's the right solution in any way, which is why evolution gave it to us. And so I'm just a firm believer that the faster we commit, like doing research on that is going to be the research that ultimately is the foundation for what's really coming and is going to change the world in robotics.
Awesome. Jackie, you want to weigh in?
Yeah, it's a bit of like playing devil's advocate for me as a representative of the Gato approach. But I will say, you know, there are a lot of real concerns from a safety perspective of the end-to-end approach. You know, we lack all of the tools for interpretability. Or many of the tools. It's a growing field for these kinds of models to understand like explanations of what the robot is doing and why it did it. And we also we have to kind of be a bit clever about building it in safety and designing kind of the action spec of the robot to be limited, or the environment to be limited. And this gets harder with robotics, right? Like to constrain the system for physical safety. A huge problem comes in when you have like a semantic mismatch from the language instruction and what happens in practice when there's this kind of ambiguity of language. Like that's something that we need to understand about English or any other language as an input mechanism, is that it has ambiguities and it's like a living entity, and that is going to create concerns, just like how we have, you know, ambiguity in instructions that we give each other. There will be ambiguity in the instructions that we give to robots.
Awesome. Dieter, you want to?
Yeah, I fully agree with Jeff, of course, that ultimately doing all of this end-to-end is going to solve it. But in the 100 years between now and then, I would bet on 500.
No, 10, 5 or 10, not 5, not 100. 10,
okay,
maybe.
in the immediately foreseeable future, I think there's still. I think we still need to think about how to break down tasks, right, or break down components of these systems, so that just for practical purposes, often, so that we can maybe train them individually and recomposition them for new tasks and things like that. I have not seen any of these systems to really scale to being like super useful for robust robot tasks, to be honest, right, in the real world. I think, again, we see many pretty cool demos, but then in the end, it always boils down to what can your robot do in the real world? And then being a little bit off often means the difference between success and failure, right? Like when we read ChatGPT, I'm totally blown away by this, right? As I think virtually everybody else is. And it's absolutely amazing. It's kind of, you feel like, oh my God, here we are, right? But even then, it gets things wrong, obviously, right? And I think it will be much more obvious if you try that to just control your robot with something that has that level of reasoning. So I believe that clearly we still need to go for learning more structured systems. And the nice thing is, compared to, let's say, 20 years ago, when we had this dichotomy between high-level discrete planning and reasoning and symbols, and down here we have our robot skills and stuff like that, that now with deep learning and transformers, we have this joint embedding space that kind of can build the glue between these different levels of reasoning. But again, I think we need to provide some structure and guidance for these systems to learn stuff that scales to real robot things.
Yeah, so as a roboticist, I'm very sympathetic to that position. And I know I'm supposed to be neutral as the panelist, but I wondered also if Jean or Elaine would like to weigh in before we kind of loop back to Jeff.
Sure. I mean, to me, I'm kind of staying quiet because I think we need both. So, like, let's say this is not about language and like robot task. If there are two things to map, then if we have enough data, somebody will figure out that mapping function. So it's not a huge surprise, but the amount of data we have for this particular domain, language and task, how much data are we talking about? Like, and what kind of tasks? Like, is it complex task, or like what is the simplest, like the definition of instruction that is covered in this data space? And if it's very simple command, I guess there has to be a higher level intelligence that can compose into more complex concepts or the tasks so that it can be maybe connected together. So that's one thing that I've been kind of thinking about. And then the other one is a lot of this data is done by humans or other robots. And, you know, there's a YouTube video we always watch to learn how to cook and how to do things, but we can only capture very, very abstract knowledge from doing so. So there is something definitely we can learn. Like I think I learned how to cook pasta or things like that. But when I actually do it, that's a different story. So the two, I guess maybe end-to-end learning can be used to maybe capture some of the abstract knowledge, but how to translate that into the actual like embodied system that can master that skill or actually accomplish the task. Maybe that's a separate question.
Yeah, I almost think I hear consensus that, like, in the short term, you want that more structured representation, but in the I think the disagreement is how long is the long term. But then, like, you know, in the end, the less structured approach maybe is going to win. One of my students put it in a way that struck me, which is to say that the robot ease approach is a local maxima in the space of research. And we need to jump out of the local maxima, which might cause us to need to sacrifice performance as we figure out the way. Elaine, did you want to chime in?
Yeah, sure. So I guess, like, one thing that I've just been thinking about, going a bit back to Jackie's point about sort of like guarantees and to some extent like safety and interpretability and stuff, I think, you know, one thing that I kind of foresee is like very interesting to think towards would be, you know, we get a lot from these continuous representations and these like relations that are large, deep networks are learning that we really don't have control over, that those are very useful. We know that for representation learning. Of course, we can't do like interpretability on top of that in any sort of guaranteed way. So one thing that I'm thinking about is like, can we post hoc like extract structure from these systems so that we then do have like interpretable and like interpretable systems that do provide guarantees? Could we like synthesize some kind of robotics out of the models that we're learning and then use that instead of the full end-to-end system? So that's sort of like maybe what I'm thinking about, like best of both worlds. I think to some extent, there's also this issue that I feel like when we're talking about language, one of the things that makes language so interesting to me is that it can express not the most common or normative things, but like the long tail, right? And that's something that, like, if I'm thinking about like long tail activities that we want robots to do, or long tail situations that we might appear in, I worry that I think there's this sort of like really high level philosophical trade-off between having structure that we define and like correlations that we learn. Because if we're learning correlations from a large amount of data, we're just going to be learning basically this like argmax over normal behavior. We're not going to be able to capture these like really out there scenarios that we, like as humans, we generally can learn to adapt to very quickly if we find ourselves in those scenarios. But on the other hand, if we're relying on structure, maybe the structure that we create could express these long tail scenarios, but only if we allow the structure to support them. So there's sort of this like trade-off that I have been thinking about a little bit. So those are just 2 thoughts on this, I guess.
Cool. Yeah, I just wanted to highlight another theme that I think I've heard is the safety angle. Like maybe with the more structure, it's easier to make promises about what the system can and can't do. But then with the less structure, you have a chance at the long tail. One of my favorite examples is referring expressions, like to the left of and to the right of, and like you have to stick the frame of reference in there, and GPT-3 is not doing that. There's no sense of space in there. And we wrote this paper where we put it in there manually and annotated it, and it was just obviously wrong. Like it's just not right. Like we should not be annotating all that stuff. We should have it somehow learn it end to end. Jeff, I know you've been waiting, so do you want to react to any of that?
Some of what I wanted to ask, I was actually just going to sneak in a quick question to people, but it's been addressed a little bit. So maybe I'll mention something else, which is I'm curious what people think about the interpretability question in terms of humans. Do we consider humans interpretable? Like, I don't know how Dieter's brain does its thing when it's making breakfast. And the best, I don't know what my doctor, like why they really make their decisions. In fact, one of my favorite experiments of all of human psychology is you show 2 paintings to people on a computer screen and you said, you get to take one of these home. We'll like go get the poster out of the back room. Which one do you want? And they say, I want that one. And they say, okay, why did you choose? And then you switch them. And then some huge fraction of people will give you a long protracted explanation for why they chose the thing that they didn't choose, why they made the decision they didn't make, which just shows us how good we are at inventing post hoc explanations that sound interpretable when they're not really. Which is a long way of saying that, if we're happy with the human level of interpretability, which is pretty good, but not perfect, my doctor can give me an explanation. Maybe it's true, maybe it's not. Why won't the same thing work for robots? They can just explain to us what they're doing. My guess is that probably the level of performance in these black box neural net models will vastly outstrip the Robotics models. And so we'll end up using the powerful stuff that we get a like human level-ish interpretability on versus these like less performant models that we know exactly what's going on because we force them through these kind of bottlenecks where they have to have interpretable gateways. I'm just curious what people think about that.
Yeah, so like the difference between you and Dieter is that you don't know every single thing Dieter has seen in his lifetime. Right? Like we have access to the training data. We have an opportunity to like build better interpretability mechanisms or tests. Whereas with humans, our brain structure is something that's evolved over thousands of years. And, instead of something that was designed and then trained over data that, we collected. And we also—
So you aren't happy with human level interpretability. You want to do better. That's what I'm hearing.
Yeah, I think we can do better. Yeah.
Okay, cool.
And maybe to chime in here also is, I actually agree with Jeff that I think we're often overdoing it, right? In the sense of that we're expecting these machines that we can fully inspect what they're doing, why they're doing that. Of course, once they have really strong reasoning capabilities and they perform extremely well, maybe then they can get away with this kind of higher level explaining of why they're doing things. I guess the problem is just that at this point, they're committing so many stupid mistakes that we are kind of more in a debugging mode, right? We're really just trying to figure out, okay, what went wrong here? And for that, I think having this introspection into the system can just help still, right? Quite a bit. But I also agree again that I think we're always saying, oh, these machines do this, do that. But from humans, we seem to expect almost less, right? In that sense.
Cool. Jean, and then I'll
Yeah.
start taking
Yeah,
questions.
I just wanted to share another like preliminary results from a completely different domain in aviation. So we did some user study with the real pilots, like how they assess the other pilots' performance. And it was like Turing test kind of a setup. So it was sometimes AI and sometimes human. And what we wanted to find out from that was like what people care, like what are the important things. And initially we thought that naturalness or, interpretability, things like that would be important. But the most important thing that people care is the competence, like how well they perform. And surprisingly, performance actually includes predictability, like predictable behavior. So if they are unpredictable, then it's not a good performance. So I think it is a little bit related to this interpretability. So like if we can understand what the robot is doing, or if it's predictable, then maybe it is more accepted in the environment, and maybe safety is the same thing. So if we know the performance is better than human, like we know it's always like 98% accurate or like high performing, then even if there is no interpretability, there is some trust that we are building because we know the expected performance, and also like have an expectation and also kind of a way to predict what is going to happen. So I don't know what other people think.
Awesome. So do you have any questions in the room? I see there's one in the chat.
Yeah.
So I'll read that one. So so he's asking whether we can have a single end-to-end model that can use language not just for control, but also for many other things. So explaining decisions from control to language, asking for help, searching for missing information online. Cynthia, you want to start?
Eventually. I don't think that's necessarily, I think we can look at some of the existing large models that can do a wide variety of things as a proof of concept to say, yes, we can understand language at the level where we perform different actions and different sort of categories of actions and responses depending on the inputs. But to parrot something Dieter said a minute ago, as long as we're kind of in debugging mode for a lot of those, for the individual tasks being listed out there, I don't think it makes sense to try to build systems that can do everything. That just makes the process of building systems that can do those individual things robustly that much harder. And ultimately, I think we'll be looking at systems that have a lot of different capabilities built in, rather than necessarily a single system that uses a single technical approach to do all the different things. I mean, that's how complex systems often work.
That's something like I reacted to, like reading the Seikan paper and stuff, is like there's this giant language model that can do everything. Like it solved it, right? Like we never would have thought, I never would have thought this would be possible. And it's going to this teeny tiny set of very brittle things that the robot can actually do in the real world. It's almost embarrassing for us roboticists. Like the language people have all this stuff and we're like, this little tiny little thing.
But
Peter?
Sure. Oh yeah, just going back to Jeff, in a sense, there's maybe some connection to where he said like end to end, right? And if you think about language, I mean, it doesn't have to be exactly the kind of language the way we look at it, but these notions, there needs to be some structure in these systems that has notions of what we have in language, right? Compositionality, and those different things that allow you to reason and to structure kind of the way you reason about the world and how you generalize to different things. I guess what we really need there is that these language constructs, some people might call them even symbols sometimes, or so, they need to be really tightly coupled to the perception action space, right? And how to do this jointly, we just haven't figured out yet, right? But I wouldn't dismiss this as something that cannot work, right? It sounds actually kind of intriguing as a contrast to the kind of manually designed, layered hierarchical systems that we typically build in robotics, right? That are very brittle, as we know.
Jeff, do you want to respond to that?
Yeah, I have two comments. One specifically on that, and then one a little bit more broad. Specifically on that, I think in my mind, the approach that's coming out of, say, OpenAI is kind of showing the path forward. And I think it's instructive to say, like, well, what's wrong with, like, can we spot, like, a reason why that won't continue to work? So there you see in DALL-E 2, it obviously knows, it has grounded all these language symbols into very specific concepts because it can draw and, like, basically depict all these interesting combinations that were not in its training set. So I think it really shows that it is tightly grounding the symbols in the visual world as it experiences it. And I don't see any reason why that wouldn't work and continue to scale into like robotic sphere in 3D, like moving around in a three-dimensional world, videos, et cetera. And then even more broadly, I also kind of think that the paradigm of deep learning and scale is working so well that it's instructive to say, like, why don't we think that will work? And I think one of the things that's really interesting, and again, I'll be kind of controversial here in this conversation and take an opposing view, is I'm hearing a lot of people say, well, ChatGPT is amazing, these big models are amazing, but they're not perfect yet. And so what we should do is then go and do the manual approach to try to fix the problems that they have. We're going to need to put in a lot of manual structure and a lot of extra stuff. But like the thing that got GPT-1 to GPT-2 was not extra, like recognizing that GPT-1 was a little bit broken and then like adding manual structure, it was just scale and data. And same with GPT-2 to GPT-3. And GPT-2 had all sorts of problems and it's way better in GPT-3. And once we have GPT-4, 5, 6, and 7, I think that these things will just go away and the answer will probably be scale and data and compute and not necessarily going in and adding the manual fixes. I think that, to my opinion, the writing on the wall is that, the thing that actually fixes all these problems that we're pointing out is just more compute, scale, and data. So we can just go on vacation and wait for more compute and data. It would be good.
Jackie?
Yeah, I think I'll tie together what I was going to say earlier and what Jeff just said, actually. It's like, so, roboticists are trying to do something quite different from building a dialogue agent. And a dialogue agent is trained very differently from how and you might say, like, well, maybe robotics people should just, do something more similar to what like ChatGPT is doing, right? Which is just predicting the next token with some other stuff, right? And so the reason that we're really impressed by dialogue agents and also by text-to-image generators is that their action space is both obviously a lot larger, but also more expressive and like evocative of things that amaze us, right? That, like, we think that we're talking to a human. We see this amazing art that's so evocative of these existing styles and new things. Whereas a robot's action space is often like 7 dimensions, maybe less. This is something that was amazing for me as a roboticist working on Gato, was something that has access to a robot action space, but also a lot of other things, a lot of other tasks, and it has like many capabilities. However, those capabilities aren't all in one world. They're in kind of many different simulated tasks and one real embodiment. And I think the difficulty that we face as roboticists is getting something with a relatively limited embodiment. Maybe, it'll get more complex as we work with things like dexterous hands or humanoids or whatever. But to show that it has massive capabilities that are, on a similar level, there's some analogy is like with dialogue agents at the level they're at now. But we have difficulty imagining what that looks like. because that means like thinking of all the capabilities that are in the physical world. And in a way, like what we do as humans is sort of limited. We do a lot with like what happens in our minds and what we communicate with each other and what we do as like a whole population, right? So it's just something to think about, like we have like the difference between the physical action space and then the like linguistic and mental action space as well.
Yeah, I think that's a really important point that, like, in a lot of the work I see is often is underappreciated, is like the high dimensionality of the spatial and temporal data coming in and coming out of the robot compared to other modalities. And I think that's like the big roadblock in the way of seeing these end-to-end systems really making something happen on a robot is to figure out the right way to put that structure inside. So we should finish up. So maybe I'll ask if anybody has any closing thoughts before I think everybody in New Zealand is going to lunch.
I guess it's one thing that sort of I maybe will push back on just a little bit is about generalization or generating images with fine-grained like compositionality. I don't think that we have diffusion models that can like just take a very compositional like sentence and just straight out generate an image that perfectly aligns with all the spatial relations and all of the like attributes and so on. There is work like in energy-based models that does something like this, but then it is actually decomposing the constituents of the sentence, which is taking into account this like linguistic inductive bias that we know, which is the structure over language. So I think even in these models that are really, really good, like they create very visually plausible images, and the images that they generate are artistically and maybe with some amount of intent in the caption, capturing what the user is asking for. They're not doing the same kind of like compositionality. They don't have the guarantees of that we might get if we have like separation in the model itself.
Jeff?
So I agree with that, although I would just say what's likely to fix that? I guess I go back to saying it's probably, I'm not trying to say that the current paradigm is perfect, that we don't need to change things. I don't literally mean we can sit back and just pour in more compute and data. But my guess is that the bet on to kind of learn it all and get the right loss functions and the right data sets, maybe even the right data generation, that kind of stuff, but mostly kind of an end-to-end learning system. That seems to me the path that's ultimately going to solve even the problems that you mentioned, including even if it meta learns the kind of internal symbolic structure that we have and we generalize well. And we think when we deconstruct these things and put them in, basically all the stuff that we want the manual path to inject, my guess is it'll end up getting learned, and it'll get learned in the system automatically from data, and it will figure out how to go from system 1 and system 2 style thinking and have some symbolic processing and kind of know when to switch between conscious thought and language to like muscle memory and model-based RL and model-free RL, and all the stuff will just kind of get learned if we give it the right environment in which it can learn from data, this stuff with a huge amount of compute. So just to clarify that I agree that all these problems exist. And the question is just like, what's going to ultimately fix them? And my money's on the end-to-end learning based approach to solve these problems.
Cynthia?
Just one thought. I'd like to, this is something Jackie said earlier that I'd like to kind of elevate a little bit to a point of conversation, is that we have been talking a lot about how we can get robots and robot language systems to do all these things that humans can do. And I think it's important to bear in mind that robots are not humans, right? There are sets of things they can do that we cannot. There are sets of things that we can do that they cannot. It's not necessarily the case that taking, an arbitrary task that humans are good at and saying, when will robots be good at this particular thing, especially language-based things, is the right path forward from a research perspective, especially because people have so very many language structures that have developed over a long period of time.
Makes sense.
I've been thinking about this idea for a long time. I don't have a good idea, but like in language, for the same exact thing, there's just infinite number of different ways to state that same command. And let's make an assumption that there exists the easiest instruction, like, or simplest or easier to understand. Then I'd like to see if all these complex or maybe noisy instruction can be reduced to that easy instruction to follow. Then that makes the job of understanding instruction a little bit easier for the robots. So like if there's a good instructor, robots will do better. So that's the idea. So can we do something in the language space first, so that even if I, like a person like me, I can never like say things in a concise way, but whatever I say is translated into a very succinct form, then maybe my robot can do better.
Awesome. Dieter?
Yeah, I'm actually super excited about these recent developments on the language models, diffusion models, in general, transformer capabilities. And yeah, we keep on seeing people say like, oh, but they have this limitation, that limitation. And I agree with Jeff that I think, yeah, we just gotta wait. So far, they've always come up with amazing solutions, right? And then of course you can find the next limitation they have. But I am feeling kind of bullish about the future capabilities of these. It's just in robotics, we still haven't, I think, really figured out how to train and do something at that scale, right? Because it's not clear what the right data will be. And there seems to be some real difference between, even in the vision space, between 2 and 3D. But then we see, of course, also amazing advances in 3D generative models and all of that. So I would certainly not dismiss these. We just have to figure out how to leverage them, because sometimes in robotics, we tend to be a bit on the side where we say, oh, but my robot needs to be able to learn it from 10 examples. And I think often it's just unreasonable, right? We humans also have a huge amount of training data over time, and we just need to see how we can transfer that to the robotic setting.
Awesome.
I agree with that.
Awesome. So thanks everybody. That was a really spirited debate. And it was really great to hear all of your perspectives. And thanks again to the workshop organizers. Let's give everybody, all of our panelists, a hand.
Thank you. That was
Cool.
fun.
Have fun, everybody there.
To the organizers. That's who I was applauding for. And thanks to the other panelists for a spirited conversation. Hope you don't mind extreme positions.
That's what we want.
Thank you, everyone. And thank you, Stephanie, for moderating.
Thanks, everyone.
Thank you, Stephanie.
Bye.
Thank you, Stephanie.
And next up, right before we head out for lunch, we will have 4 spotlight presentations. The first 2 are actually in person. We'll start with clip fields presented by Sumit. And yeah, you can just join the Zoom link. Webcam, that's the microphone. This is broadcasting, and this is the mic. The room's here, right? All right. It's a microphone. Oh no, just join the Zoom. Oh yeah, okay, that's right. It's present. Perfect. Hey, actually an in-person talk. So I'm Sumit. I'm the 3rd author of this paper. Mahi couldn't make it as the first author. So there's a 5-minute spotlight, so I'll be quick. We built this paper called Clip Fields, and here what we're trying to do is, if you think about Clip, which has been this multimodal embedding that has been pretty powerful, and neural fields in general, but NERFs have been pretty popular, and we focus more on neural fields. We try to like use these concepts, or like we actually use Clip and a form of neural fields. And what we do is we take RGBD images from RGBD cameras, RealSense or iPhones, along with odometry that we either compute or get from the sensors themselves. And then we combine them with pre-trained web models, web image, web text models like DETIC, Clip, Sentence Bird. And we kind of make all of this into a robotic memory. And you can use this in the context of robots, but also in the context of, say, AR, VR, where you can query what you want to do in semantically without specifying intent or ahead of time. And all of like what we've done in this work has no human supervision. It's all, I mean, the human supervision was whatever was from the pre-trained models, but like we ourselves haven't labeled any data as such. Like what we do is we create this like robotic memory in 3D where each point in space is represented semantically. And I'll talk a little bit about how we do this. But firstly, like what the consequence of this is, you can actually take a robot, it has an RGBD sensor with some way of getting odometry, and it can go around the space and completely unsupervised, like create a semantic memory using our work. And you can then give it queries that are semantic, either visually or text-wise. So you could be like, wash my dishes, and it'll actually go to the dishwasher. Well, we haven't worked on the part after that, but you can actually just map your you don't have to specify ahead of time various semantic things, including new tasks or task specifications. And in future work, you can even break, you can use a representation to learn new tasks without ever having specified or like having the robot understand certain concepts ahead of time. So coming to our method itself, we have what happens is you take XYZ spatial locations, which might or might not have some some points from your RGBD sensor, and then you map them to some semantic representations, visual representations, and one hot, which I won't be talking in this talk. And the way we do it is we take a multi-resolution hash encoding via instant GPT from NVIDIA. And then we map, so we basically take every XYZ point and that maps to a location vector. And then we build a couple of MLPs, each MLP for each kind of representation that takes the location vector and maps it to a particular semantic representation. So text representation, visual representation, and so on. And so we collected data with iPhones. iPhones have reasonably good RGBD and also give you odometry that is pretty accurate. And we collected it in a couple of environments, and we take these RGBD data, we use, and we have the odometry, we back project to 3D coordinates, and we get point clouds. And for each spatial location, you have an octomap. And on the other side, we take the RGBD image as is. Actually, mostly we just use the RGB. We ignored the depth because the web models aren't trained on depth. And we use a couple of models. We use DETIC, which is an object detection model. And the DETIC outputs some object outlines and labels. And the labels, we map it to sentence bird. And the bounding boxes, the images inside the bounding boxes, we map it to clip. And we get a visual representation, a text representation, and finally, for each XYZ, we get these. And so for training, we basically just use a contrastive loss that kind of keeps the close things together and mixes up the data, the batch where you have far things just contrasted further apart. So it's a pretty, like, it's an unsupervised game actually, and that's pretty much how the training works. And the results are basically you have this model completely trained without any human supervision, that has semantic values for each point in your point cloud. So if you ask a query saying, hey, like, give me all the points close to a microwave, it will actually highlight like the point cloud parts that have the microwave. But microwave, you can say, oh, that's an that's a label out of the object detector. But you can literally give an arbitrary sentence, and it will actually highlight parts of your point cloud that are most relevant to that. And so we actually tested this out in a few environments, but 2 environments so 2 environments I presented is a kitchen where you can actually, like, say, give arbitrary things, and also a library, and you can say, wash my dishes, go to the bookshelf. You can also do semantic things like go to the red coffee machine, or go to the blue book, and it kind of works. And that is ClickFields. You should go check it out. The code and models, and pretty much everything is available.
We'll join Q&A for everyone at the end. So, Carl, do you want to just set up that one?
All right. Hi, everyone. My name is Carl Parrish. Today I'll present. Closer to all right. My name is Carl Parrish. Today I'll present work with the joint authors you can see on the slide on scalable semantic policy pre-training via language instruction relabeling. To motivate this a little bit, we can look at some of the successes of RL over the past, I guess, couple of years, and we can see that they're, very impressive, but they're usually very sample efficient. I think that's like a very well-known fact. And I think the very well-known solution to that is to try to pre-train your policy, right? This is like fairly common nowadays, that you take some sort of offline data set you can use for pre-training, and then hope that you don't start training from scratch, so you can be more sample efficient. And I think a key question here is, where do the tasks come from? Basically, where do we get the tasks that we can use for policy pre-training? And there's a bunch of different solutions people have explored. One very popular nowadays is to do offline reinforcement learning. The problem with offline reinforcement learning is that you usually need rewards for doing reinforcement learning. And so you can either assume that your data somehow comes with the rewards, or you can have the designer of the algorithm, define a couple of analytic reward functions and then use them to relabel the data. But that's not really scalable, right? Because now I need to define all the tasks by hand. So how can we do better, and how can we get tasks at scale? There has been a paper, I think last year, from folks at Google Brain, I think Yevgen is here, on defining tasks more scalably, basically by just doing goal condition offline RL, and picking tasks as random states from your data set, right? And this is great because you don't need reward functions anymore. You just reward the agent for offline RL reaching that goal, and you get a lot of tasks because every state in your data set is basically a task now. A slight downside of that is that because you're picking random tasks, like random goals, these tasks are not necessarily super meaningful, right? You basically train your agent to do anything that it has seen in your data set. And then a third approach that people have explored, coincidentally also by Google Brain people, is to basically use language as a way to scalably define tasks that are also meaningful. So basically they take a data set, they crop out a subtrajectory from the data set, ask a human to label it with language, and then use that as their task definition, which is definitely much more scalable than trying to hand define reward functions. But you're kind of limited to the set of tasks that you have annotated by humans, right? You can't do this kind of relabeling idea that gave us so many different training tasks in the actionable models work in the middle. So what we try to do in our paper here is kind of combine these ideas and try to work in language space so that we can get semantically meaningful goals, but apply a similar relabeling strategy as we have seen in the actionable models work. And the core insight is that relabeling in semantic space or language space is basically similar to reformulating or aggregating different commands. And our idea here is that we can use language models, large pre-trained language models, to do this relabeling for us. So basically what our approach does is we start similarly to the right column I had just shown, with a data set that has language annotations provided by humans. And we can use that for pre-training the policy. This is fairly conventional. So we could just do offline RL with a sparse reward at the end of every subtrajectory and condition the policy on the task. But then in order to generate more training tasks and basically get a richer pre-training distribution, we now use our idea of using language models for relabeling and basically take trajectories from our data set, pass them into a language model, and have the language model generate a new task based on the annotations that we already have to expand our task set. And then we can feed that all into our pre-training loop. And we can also do that across trajectories, basically stitching different sub-trajectories from our training data set. And again, we can aggregate it with language model, or we can just concatenate. And then we end up with a very large set of pre-training tasks. We can do pre-training, and then eventually we can use our policy on a new downstream task by fine-tuning it. And hopefully we will be more efficient than doing it from scratch. All right, we will test this, or we did test this in an environment where we actually have access to a wide range of long horizon, kind of semantically meaningful tasks, because for the language model to actually aggregate meaningfully, you need meaningful tasks. And we use the Alfred environment. Conveniently, Alfred does have a large data set that has language annotations, so we didn't need to collect that ourselves. And then what we will test on is some like more challenging tasks, basically longer horizon tasks that the model hasn't seen during pre-training. And what we can observe is that by pre-training on these on this large set of semantically meaningful tasks, we end up with a pre-trained policy that can already solve quite a wide range of also longer horizon tasks out of the box. So this is zero-shot evaluation. And they can become fairly complex, so like up to 8 steps, I think is what the policy was reasonably able to solve. And then we have also evaluated the fine-tuning case, which basically is what we are most interested in, where we have had users formulate new tasks. So basically, we want to make sure these are unseen tasks. So we had users literally come up with new tasks, given a video of what the agent can do. These are fairly complex long horizon tasks. And then we basically fine-tuned both our representation or our pre-trained policy and some of the prior works on these tasks. And we found that by pre-training on these semantically more meaningful tasks, we could achieve a higher success rate on these new tasks. All right. So to summarize this, basically we have introduced Sprint, which is a scalable semantic pre-training approach that uses language annotated data along with language model relabeling to get a wider range of pre-training tasks. And then we have shown that this leads to better zero-shot performance, but also importantly, better fine-tuning on unseen tasks. All right, if you have more questions, I'm happy to answer in the Q&A, and also come find us at our poster later. Thank you.
The next speaker is Stephen. Stephen, I think you're virtual. Can you share your screen? That doesn't work with clear recording.
Can I share my screen right now?
Yeah, perfect.
All right, give me 1 second. Let me set this up. All right, everything all right?
Yeah.
Okay, I'll get started. Hi, everyone. So I'm presenting our paper, Arnold, a benchmark for language-grounded task learning with continuous states in realistic scenes. So this is a joint work with a group of wonderful people in our labs. Okay. And so humans actually normally specify task goals, not as discrete goals, but in a continuous spectrum. So for example, when actually watching some of the gourmet shows, the chef will tell you add 5 milliliters of water, add a scoop of butter. So those are some of the things happening a lot in daily lives. So we think robots should understand the same utterances to fulfill those instructions if we're ever going to have a cooking robot. So as robots operate in the real world, photorealistic things are necessary for task learning. So we know some of the current benchmarks basically set up a table and put everything in a tabletop setting. So to help with those problems, so we propose our benchmark. So the simulation environment, the things are actually from the 3D from dataset. So you can see it from the right, we are building our simulation environment on top of NVIDIA i6 So i6 uses some of the very advanced rendering techniques, ray tracing and path tracing. So the lighting simulation is extremely realistic. And because of the use of ray tracing, actually have some added benefits. The render image, different from other benchmarks like RL bench, like the image is actually not deterministic because this is the nature of the ray tracing because now this is because of lighting sampling procedures. So if the model can work in this type of simulation, it has the potential to transfer to the real world, as some of the other papers demonstrated before. So for next come to our tasks, here I show some of the tasks in our benchmark. pour water, pour a little bit of water, and pour all the water out of the cup, and fill water, and open the cabinet halfway, and also make the bottom upside down. So basically, you reoriented the object and raise the bottom 60 centimeters above the ground. So those are some of the demo tasks. So, but in order to facilitate learning, so to make learning successful, you need to collect data. So we are collecting some large-scale human data from. So normally people nowadays do it from VR device. So VR is kind of expensive right now. So we are open to use gamepad. So we use a Xbox or PS5 controller. You can basically use a controller to manipulate the robot ND factors. And so we collect like more than 2,000 data trajectories. And so some of the trajectory statistics are here. So on average, people spend 13 seconds. So here are some of the demos for the some of the tasks. So you can see like the human trajectories it's kind of slow and kind of noisy compared to other standard methods, like you use motion planning to manipulate the robot. So we further design a set of key point based motion planning planners to actually based on object features to manipulate those objects. So those are all included in the benchmark. All right, so some of the variations in the data set. So you can see the objects and also the lighting and also the things are different. They're all going to play some part in different split. And there's some also other variations for the goal. So pick up the bottle, I think it's only like 10 centimeters, maybe like this is a 20, this is like 60 or something, and different goal variations for open the cabinet, like 40 open, partially open like 20 a quarter, and fill the water, dump the water, like dump all the water, dump part of the water. So the continuous state kind of have impact the goal. All right. So for the observation space, so we provided like 5 different cameras actually, but here I only show 4. So, but you are allowed to, you can replay the trajectory to generate any arbitrary number of cameras as you wish. So arbitrary resolution. So by default, we give you 128 by 138. So we give you RGBD and also the segmentation mask. So this is all some of the utilities provided by iFixin. And the task goals. So here's the table for all the tasks currently available supported. We are currently working on adding more, but those are the ones are 100% supported. So pick up the object, raise it to a certain height, reorient the object, open the cabinet or close the cabinet, open drawer, close the drawer. So on the right, you can show some of the examples. Example of the language generated by our template. So the template is essentially specify 3 different things. So the verb, like the object, like what object to operate on, and the state, the goal state. All right. So stay tuned for our upcoming release and some of the updates. Thank you. I'm happy to take any questions.
Okay. You can stop sharing everything. One last. It's the audio side.
Recording in progress.
Sure.
Hi, thank you for the opportunity to appear at this workshop. I'm presenting Robo Report, summarizing a virtual robot's past actions in natural language. Our ultimate goal is to enable robots to talk to humans about their past actions. They should be able to tell us what they did in simple, accurate, natural language. If we task a robot to do a long, complicated job, such as cleaning our house, we would want it to report back what happened, but not in excruciating detail. We would only want the most important points, the quick summary. To that end, we develop a system to generate summaries and other descriptions of robot actions by repurposing the popular existing Alfred dataset. The dataset pairs video frames of various episodes of a virtual robot performing long horizon tasks in the virtual AI2 Thor environment with a one-sentence summary called a goal description in the dataset, along with the PDDL plan and lower-level action commands which generated the sequence, and natural language instructions describing the actions. We perform 3 kinds of language generation. First, using each of the elements of the dataset, one data type at a time, as input, we generate the natural language summaries. To generate summaries from video frames, we use a pre-trained ResNet 50 as well as further convolutional layers and an LSTM-based encoder-decoder model trained from scratch. When the input is text of some kind, such as PDDL, we use a pre-trained T5 transformer, which we fine-tune to generate the summaries. By manually annotating a selection of the generated summaries, we can immediately see that when starting with text of some kind, using the T5 transformer to generate summaries is very accurate, with up to 98% of the summaries having no errors at all. When starting with video frames, however, our system produces many more errors, mostly through misidentifying objects and places. Our second task is to generate PDDL, instructions, and actions from the video frames, using the same combination of convolutional and recurrent networks. We have a full table of automatic evaluation metrics in the paper, but the quick summary version is that the PDDL generation works surprisingly well, much better than generating the natural language summaries. We therefore create a 2-stage pipeline, which first generates PDDL from the video frames as an intermediate representation, and then generates natural language summaries from that PDDL. We find that this does better than going directly to summaries, making about 25% fewer errors. But it is still making errors about half the time, so there is much room for improvement. That would be the first limitation of our work. Other limitations, or dirty laundry, include the fact that we use a subset of the video frames selected by the Alfred dataset creators. Second, our LSTM encoder-decoder and some of the convolutional layers are trained from scratch, which is probably not optimal. Third, we are only testing this approach in one virtual environment, one in which some of the object appearances can be a bit quirky. Thanks to my collaborators, Iredi Akinola and Daniel Bauer, and thank you for listening.
Great. Thank you so much for the great presentations. We have some time for maybe 5 minutes of Q&A now. If you have any questions, feel free to post it in the Zoom. Otherwise,
Maybe I have a question for Harlan.
Great. Yeah, maybe you can come up and speak it.
Hey, a great presentation on Arnold. I was wondering if you could highlight a bit like what is the biggest focus of this data set? Because like you presented a lot of stuff and it was not super clear. Is it more that is just like the realism that is more realistic simulation environment? Or are you looking to learning like long horizon language condition policies, or just like a lot of policies? What is like the focus where you want this benchmark to work on?
Hi, thank you for the question. There are two focuses right here. One is to understand the continuous state. So that's part one. Another is to the realism of the things, so the lighting and things like that. Yeah.
Thank you. Any other questions? Justin?
I have a question for Cofield. Really cool work. I have a question about, since you're using both the object detector with sentence embeddings as well as sort of the embeddings of the image, do you have any intuition on whether the sentence or visual embeddings were more important for the performance of the paper?
Sentence or visual embeddings. Okay. It depends on the query, right? So if like clip fields get their purpose, like there's this general purpose memory that have all this semantic information and you can do a bunch of queries. If you're doing a query that's very deeply textually semantic, like go wash the dishes or something, then the sentence embeddings play an outsized role. But if you do a visual query, like go find the blue book or something, like the blue part, like there, like the visual embeddings are like more important. And detect, for example, gives properties of the objects as well.
Thanks.
Any other questions?
Do you have any online questions?
Don't see any right now. I guess I had a question for Sprint. I like the comparison you made to, for example, like image goal condition models, like actionable models. Do you have a good intuition on what's more scalable as a pre-training method, whether that's language goals or image goals, whether there's for trajectory training or just pre-training in general?
Well, so it depends on what you want. I do think that language goals are very scalable and they're also generalizable in a sense, right? Like if you get an image goal, basically your network, if it should generalize well, kind of need to like reverse engineer what's the actual underlying thing that you wanted it to do, right? Because if you take an image goal and you want to actually have your network do it in a different environment, then you don't want it to match the pixels. You want it to match the underlying latent structure of where you want to get to. And the language command gives you that much easier because it's already kind of a structured representation of a goal. Whereas in the image goal formulation, you need to kind of reverse engineer it. So I do think that language is very scalable and easy in that way. But it does require a human to, go in and give you that structured goal representation. Whereas an image goal, if you can get it to work, you can basically just take any data and like pop out an image and you will get it. But yeah, I do think that in terms of generalizability, it's much easier if you have language goals.
Thank you. Oh, one more. Yeah.
I was just wondering for the clip field takeover, how long does it take to train the network and you need to train the first team? And if it's first team, you still any way to maybe do it online in a manner, it's moving around to the robot having Can you repeat the question?
Yeah, so the question was, hey, how long does it take to train the network? And do you see basically like if you move the robot around online, like, what happens? How do you adapt to this? If I remember correctly, it took us a lot longer to train in early days while we're experimenting, but the final set of runs is pretty quick, like a few hours, but that's because we didn't really optimize for anything. So now if you really like wanted to like, so a bunch of stuff is like extracting pre-trained features, right? We just like took the code base as is and like used them. So now if you build out a really optimized pipeline, it should be pretty quick, maybe like a few sets of minutes or something like that. But at the same time, your question about online, to an extent, this stuff is not like a fixed offline training. Like you can actually extend it to online settings, because as you get new information, you can just treat that as continuation of training. So it's not going to be globally optimized, but at the same time, like your general neural network training is not globally optimized anyway. It's not like a probabilistic graphical filter. So I think in the online setting, you would start with some fixed, fixed large cost. And I would say like, even that would not be that large if you optimize it. But after that, the incremental cost would still give you substantially good results.
One last question before we head out to lunch. There's none. I guess maybe I had one for a robo report. I'm kind of curious. It was very surprising to me that the PDDL prediction was kind of like the best performing result. Do you think that's an artifact of the structured like template, distribution of your underlying Alfred data set, or was it because of something else?
That's a good question. So we did some sanity checks to make sure that it wasn't just memorizing, the distribution of the data set, so that it was actually looking at the environment while it was answering the questions. I think, it's because it's very structured. It's the natural language annotations that were made by people are pretty out there. Like some of them aren't even that accurate, and some of them, they'll describe a garbage can in one way, another person will call it a bin, another person will call it a pail. So just so much more diversity. Whereas, if PDDL descriptions have one word for everything that the robot does. And so I think it's really that like one-to-one correspondence of an action to a language description that I think helps, which I think like when we give instructions to a robot, we would like it to respond to any way that we describe a garbage can, right? But I don't think it matters if we end up training robots to tell us what they've done and always use one word to describe a garbage can if it's easier for them to do. So I think it's probably okay.
That makes sense. Thank you so much.
Thank you.
All right, then. Well, I guess any further questions? There's the poster session that will be a bit after lunch. But in the meantime, then we have about 50 minutes. I think lunch is in the main building. And I guess, Drew, if you want to post the schedule one more time, and then we can adjourn for lunch then. So yeah, thanks everyone. Hope you had a great lunch. Next, I'd like to introduce Jeff Clune. He is an associate professor of computer science at the University of British Columbia and a faculty member at the Vector Institute who works at the intersection of deep learning, robotics, and evolving neural networks. Previously, he also worked as a research team leader at OpenAI and a senior research manager of Uber AI Labs. Thank you so much, Jeff, and I'll let you take it away.
All right, thank you very much for the invitation. So today I want to talk to you about video pre-training, or VPT, where we're going to try to learn to act by watching unlabeled videos from the internet. And this was done with this fantastic team of people that were in my team at OpenAI, and I want to give them huge amounts of credit for all the hard work that they did. This paper was at NeurIPS this year. So in hard reinforcement learning domains, arguably the biggest Achilles heel is exploration. Many algorithms do not know how to learn to do anything, or at least the next thing, because of the exploration bottleneck. So an approach that we've tried for decades is intrinsic motivation, where you try to encourage algorithms to go to new states, and that works okay. So there was this kind of grand challenge game for many years in the field in Atari called Montezuma's Revenge, and most algorithms that basically had no intrinsic motivation got a score of 0. And if you did intrinsic motivation, you got a couple thousand points, and there was a lot of fanfare in 2018 for this algorithm that got over 11,000 points. Last year, we had a paper in Nature on an algorithm called GoExplore that really works quite well on these hard exploration challenges. And it gets basically arbitrarily high points and solves this game. It beats the human world record and gets, sometimes 18 million points on this game. It solved all of the unsolved Atari games at the time, and also solved really kind of hard exploration robotics challenges in simulation. For example, here the robot gets no reward unless it puts away one of its toys. And you can see that GoExplore in blue solves a task every time, and intrinsically motivated PPO almost never solves the task. So if you want intelligent exploration, intrinsic motivation doesn't really work that well. GoExplore, I think, works quite well and is very promising, but it's kind of a complex manually designed algorithm. It hasn't yet been proven in rich 3D worlds like Minecraft, for example. And I'm kind of somebody who believes in, lots of compute, kind of like a simple solution. And so I think there's a question, which is there another way to be solving this challenge of really hard exploration? And to borrow from Isaac Newton, AI sees further by standing on the shoulders of giant human data sets. I think that's the lesson of the last few years with things like GPT, Clip, DALL-E, AlphaStar, etc. And the internet is full of tutorials of how to do hard things. For example, learn how to use Photoshop or Gmail or play Minecraft, or even do things like assemble IKEA furniture. And so the question we had with this project is, could we basically harness the GPT playbook, but for embodied virtual agents to learn really hard things? And so we're basically going to first pre-train on noisy internet scale data. Then we're going to fine tune with RL and, of course, profit. So our hypothesis here is that pre-training should give us what we call a behavioral prior that allows learning tasks that are otherwise effectively unlearnable. So if you think about it, normal exploration is exceedingly dumb. It basically just takes random actions every once in a while, or samples from the action distribution. A behavioral prior learned from pre-training, which is what VPT gives you, instead says, in any situation, if I don't know what to do, just do what humans would do in this situation. And we think that's a much better solution. So the domain that we chose here is Minecraft. We did that because it's a hard exploration domain. It's very open-ended, and I'm very interested in open-ended learning and open-ended algorithms. It's got huge amounts of data from the internet. But I also want to emphasize this is a very generic method that has nothing to do with Minecraft. We just tested it here. For example, you could use this method to learn how to do anything on your computer. So we specifically, for that reason, chose the most general observation and action space, which is the one that humans use. So we're going to go from pixels directly to mouse movements, the keyboard presses, and act at a very high frequency. And that gets us a lot of properties. One is it means that every time you want to apply VPT to a new domain, you don't have to specifically manually design and debug a new action space. It's also lossless, which means we can model everything a human can do. If we see a human doing it, we should be able to do it. And also, it's just really pushing the limits of our algorithms, because it means that we're not simplifying the domain specifically for RL. We're really trying to learn to do what humans can do, which is one of the goals of AGI research. All right. The challenge with this approach is that videos on the internet are unlabeled. So unlike for text, music, and image, you don't get the next bit of label for free. So, in text, you get the next word, in music, the next note, and in images, the next pixel. But in a video of somebody doing something on the internet, you don't know what actions they're taking that produce that video. For example, in Minecraft, if they, what buttons they're pressing and how they're moving their mouse. So to solve that problem, we train an inverse dynamics model, or IDM, which just learns to predict the action that must have been taken at every time step, given the past and the future. And that's actually a pretty easy problem. For example, if you saw this little video here, you could tell that the agent must have pressed the jump button just by looking at the past and the future. So that gives us this IDM over here, and that allows us to go and label online videos once we train that. And then we can just do behavioral cloning at scale in the GPT sense. So you go from past video to the next action that should be taken, train out a whole bunch of data. We ended up using 70,000 hours of data. And then you can auto-regressively roll this thing out in a simulator by just doing next action, next action, next action. So we here trained a 500 million parameter transformer and ResNet to do that. All right, so one important hypothesis underlying this work is that, if you have a limited amount of data, then basically an IDM is an easier thing to train than a behavioral cloning model. So behavioral cloning is really, really hard, and that's why you'd expect it to be data hungry. It has to predict the next action from the past only. So in a situation like the one you see here on the left, it has to figure out, is the human going to build a house or a farm, for example? That means that the model has to model what humans' intent is, but also how to accomplish those very, very difficult tasks. An IDM, in contrast, gets to see the past and the future. All it needs to really understand is the physics of the game, which usually are general and apply everywhere in the game, which is, for example, that the jump button makes the character fly up in the air. All right, so the high-level view of our method here, you're going to collect internet data. We got about 70,000 hours. You then train the inverse dynamics model, which, to do that, we paid contractors up to play Minecraft for about 2,000 hours. And there we're recording the actions they're taking while they're playing it. Those are the labeled data we give to the IDM to train it. And it then learns, oh, given this past and future, this is the action that was taken. That then allows us to label all of the unlabeled videos we got from the internet, and then we can behavioral clone at scale. So here we can now look at the answer to the question of whether the IDM is easier than the behavioral cloning model to train. And you can see loss curves here. So, lower is better. And immediately, even at very low data, the BC is already worse off. And then look at the scaling laws. As you add orders of magnitude more data, you can learn the BC task, but its learning is shallow. It's very hard to learn. Whereas the IDM kind of quickly saturates and performs very well. And you basically are seeing roughly a 2 order of magnitude difference. So it would be far better to solve this problem, the IDM problem, take that solution and then go get the data that you need to solve the much harder BC problem than directly try to go get the BC data. And here's a shot of performance of the IDM on key presses and mouse movements. And you can see that after you get like the 2,000 hours, you actually get remarkably high performance at predicting what action was taken. All right, so that was all about training the IDM. Let's move on to seeing how we train the VPT foundation model. Here you can see how well it works. Here you can see the data. As we across training time, you basically see that the model starts to learn zero shot to do kind of the simple things that humans do in the game. So breaking that down, it does things that humans do in 2 seconds, like all the time. A little bit less common, but still with some frequency. It does things that take human about 14 seconds, which is to collect logs and planks. And it even starts to do things like make crafting tables, which take humans almost a minute to do in the game, which is almost 1,000 actions. So normally, if I had more time, I'd show you a video here of the agent going off and producing a crafting table, but I'm not going to do that because I'm going to show a similar video later where it does even more complicated things. In addition to just doing kind of crafting table stuff, we found all these interesting behaviors that we didn't expect on the zero-shot model because we're just, like GPT, we're just training it to do what humans do. So it learns to hunt animals here, which requires tracking this animal and hitting it multiple times. It learns to swim and keep its head above water. It learns to eat food, and it even learns to do this Minecraft kind of specific behavior that humans do all the time in the game, which is pillar jumping, where you jump up and you put a block below you to produce, to a really, really tall pillar go up in the air. So that's just pre-training on kind of generic data off of the internet. Another thing we can do, which comes from the GPT playbook, is we can fine-tune via supervised learning, via behavioral cloning, but to a narrower data set. So we said, we're evaluating on the full, we're training it to do things throughout the entire game, but really we want to see it do really well at the beginning of the game because that's what we're kind of evaluating it on. Our evaluations never get to the end of the game. So we ask contractors to do stuff that's very common to do in the beginning of the game, which is to go and build a house. And so we asked them to do that with basically simple materials. And then we fine-tune to that kind of very small 400-hour small data set. And what we see is this massive lift in performance, sometimes as high as 200% in some of the things that it's doing, like making crafting tables. So a huge lift when you kind of do this fine tuning. And this is known for GPT too, where you basically get much better performance if you fine tune to say answering math questions or answering just Q&A, than if you take the generic model trained on all internet data. So some of this, we also, with this fine-tuned thing, we start to see the first emergence of wooden tools and stone tools, which take humans over 2 minutes and like almost 3,000 actions to perform, which is pretty cool. So we're going to use this model, this early game model, this green model is our kind of basis when we go into RL training. One final thing to mention before we get to RL training is that it's not just the fine tuning to that small data set that's doing the heavy lifting. This is the effect of pre-training on the generic data set and then fine tuning on that data set across the amount of data you give to that pre-training phase. And what you see is you only start to get the emergence of the really impressive stuff when you've done a lot of pre-training on a lot of data, and then you do that final bit of fine tuning on the crafting table, on the house data set. Okay, so now we can also look at zero-shot behaviors that come out of this fine-tuned model, and there's some pretty cool stuff in here. So on the left is crafting a stone pickaxe, and you can see just like a computer, it's kind of dragging and dropping and using that interface. In the middle, it's building a rudimentary house, and on the right, it's actually doing a really good job of exploring a village. It's entering houses, opening doors, opening chests, like kind of getting all sorts of loot, and etc. Pretty impressive. So another way that you can get a small data set to fine tune on is not by paying contractors to do something, but actually just doing keyword searches. So, we just search for things like Minecraft tutorial or like Minecraft basics. And we take the first couple minutes of that video and voila, now we have 3,000 hours of very, very, very early game data. And that is the green thing here versus the red, which was that's the red versus the green. And so basically you get roughly the same performance. It's kind of a cheaper way to get there. All right. They also, now I want to kind of switch to the original goal, which is we've got the pre-trained model. It should have a behavioral prior. It should know what it's doing. Now, can we fine tune it with reinforcement learning to go and do whatever we want? And can it solve hard exploration challenges? And so the task that we set for ourselves was trying to get a diamond pickaxe, which is a very, very difficult thing to do in this game. It takes humans over 20 minutes to do that and 24,000 actions, which is a remarkably complex thing for a reinforcement agent to learn to do. And you have to do all of these prerequisite skills to get all the way to that diamond pickaxe. And so what we did was we just reward basically every time it does any one of these stepping stones en route to this diamond pickaxe. And if you don't do pre-training, if you start from random initialization, the exact same model, exact same architecture, but just randomly initialized weights, no pre-training, it doesn't learn anything. It's basically stuck on the ground. It actually learns only the first stepping stone in that chain. Whereas if you use the VPT method, you do the pre-training first, and then you fine-tune with RL, then you get all the way to this diamond pickaxe. And we are fine-tuning from that model that we fine-tuned to BC. So it's actually a 3-phase thing. I'll recap that later. So the TLDR probably of the entire talk is this slide, which is that pre-training on noisy internet scale data works to solve really hard tasks and that are otherwise unsolvable effectively with vanilla RL. So it's also really cool to see that for every task except for the diamond pickaxe, we ended up at the human level performance in terms of success rate when challenged to go get one of these items. For diamond pickaxe, we're about an order of magnitude lower, but we just still saw it, at almost 2% of the time, which is pretty impressive. So here is the long video of the agent actually going and getting the diamond pickaxe. So the agent has to start off going and getting some wood. It opens up this little interface here, and now it has to start dragging and dropping little icons, much as you would drag and drop icons if you were using Photoshop or dragging files around on your computer. It requires a lot of kind of fine-grained dexterity and coordination and a knowledge of the interface. It does that. It then places this crafting table. Initially in their work, it would abandon the crafting table after it used it. But when we cranked gamma up, it actually started planning for the future. So there it takes the crafting table with it. It breaks it and brings it because it's going to use it here. So it's gathered some stone. It's going to place its crafting table, open that up. It's going to use that to make stone tools with this interface. Once again, it breaks down its crafting table so it can take it with it. It's now found iron ore, which it needs to make iron tools. In order to do that, it first has to harvest the iron. Then it has to place a crafting table because it needs to make a furnace to smelt the iron. So it makes the furnace, places the furnace, opens a totally different interface. It then places fuel under the iron ore to smelt the iron, waits for a while, grabs the iron, grabs its furnace and its crafting table. Actually, I think it left its crafting table. Oh, no, it went back and got it. All right, so now it's off to the races. It goes and it has to explore. Diamonds are really hard to find, so it's learned to explore. Explores this, here we go. It's found a little stash of diamonds. It breaks them all up. And then it will open its interface. Once again, it will place its crafting table, open it up, and then it will use the diamonds it has achieved that it could only have gotten with all of those tools to make a diamond pickaxe right there. So I think that's pretty cool. I think it's pretty impressive that it can do something that is so difficult and it's never been done before with reinforcement learning agents. So now I want to talk about adding language, which I'm super excited about and is a theme of this workshop. So text conditioning gives us all these really nice benefits. It gives us steerability. We can ask for specific things, and that enables zero-shot performance of new tasks. It gives us generalization via compositionality that allows flexibility, so we can ask for basically anything. And we've seen with things like GPT and DALL-E that this is a really, really good playbook. The language is very powerful. So our hypothesis is that we should get the same benefits for embodied agents if we train at massive scale on effectively action given not only past, but past plus text. And so the cool thing is that data is already there. So all of these YouTube videos, or many of them, you have a human that's doing narration while they're doing tasks, saying like, oh, first I need to go chop wood, and then I need to go, bring up my crafting window, and like you drag and drop these things in this particular order. And so you're getting this running commentary about what you're planning on doing in the future and how to do it. And so all we do is take those closed captions and add them as input to the model when it's trying to predict the next action. And then let's see what happens. And so this work is pretty preliminary. We started it toward the end of the project, right before I was leaving OpenAI, and we were wrapping the project up. We always had it on our roadmap, but it took us long enough to get the normal VPT to work. And so I think the sky's the limit, and like you could get this stuff to work way better. But here's what we did in a kind of a quick rush. We took 17,000 hours of videos that had these closed captions, text narration. We tuned a smaller model where we take in 30-second chunks, we run the text through OpenAI's API for GPT-style embeddings. We then run that through 2 layers that get learned, and that then goes into the normal architecture of the ResNet. It gets combined with the vision information and goes into the transformer to make the prediction. So we didn't do a lot of tuning here. I think we could get much better, but even the preliminary evidence is quite encouraging. So when you ask it to, for example, dig dirt or go build a house or get wood, it doesn't explore very much. But when you ask it to explore or go find water or seeds, which are usually far away, then you get much more distance traveled, statistically significantly more exploration. When you ask it to get seeds, you get seeds, or when you ask it to get wood, you get more wood versus asking it to do other things. And the same is true for dirt, where you also get digging if you ask it to go get dirt. So I do want to emphasize it didn't work in every case. These are kind of like the best cases that we saw. But I think with a lot more data work, tuning, et cetera, that this thing would really work quite well. So I want to share a couple analyses of things that we learned along the way. One thing that really mattered was that behavioral cloning fine-tuning step in the middle. So if you just go from the original foundation model where you did the entire data set one, not the one that's focused with that second step of behavioral cloning to the house building data set, it didn't work very well. We got this kind of flatlining performance here, but that kind of getting it unlocked and getting those skills dialed in really helped. I have a feeling that with more training and more data, more compute, better optimization, you actually could not need that step in the middle, but if you're on a project and you need it, that's a nice option to have. Another thing that I think is really essential and important is that we needed a KL penalty during RL training to the foundation model. So we start in this case with the model that got fine-tuned with behavioral cloning. And if we don't do a KL, if we just start doing RL, you get this orange line here. So it learns a few things and then it stops learning anything else. But if you do the exact same model, but now you do a KL to the starting model, the model at time step 0 here, then you get this nice green curve. And why is that happening? Well, think about it. While you are learning to do the early stuff, you are not using the skills that you will later need in the Iron Age. And so you will catastrophically forget them while throwing all your resources at learning these early tasks. But if you do a KL to the original model while learning these early skills, you're basically preserving the information of the skills you will need later on in learning, such as like the skills that are necessary in the Iron Age. And then once you get to the Iron Age, those skills are still there to help you kind of learn the next rung in the skill ladder. All right, so data scaling, I want to quickly show you some things. I've showed you this plot before. It's kind of interesting to look at the effect of how much data you need to train an IDM in terms of the downstream performance on the behavioral cloning model. And one thing we noticed actually is we could have, if you look over here, performance doesn't really increase between about 100 hours of data and 2,000 hours of contractor data. And so we probably could have gotten by with this lower level of accuracy, which just means it's cheaper to get the original data you need for this process. Another thing we thought was pretty interesting is comparing what happens if you just do behavioral cloning on the data from contractors versus using that data to train an IDM to label noisy internet data and then train behavioral cloning at much greater scale. And that's what you see here. So focus on the right plot here. This is after fine tuning. What you see is you only start to get really complex skills like stone and iron tools if you are using the internet data. If you just use the contractor data and BC from it, you don't get a lot of performance in those things. In fact, you never see stone tools. Okay, a little bit of discussion before wrapping up here. So one thing I think is really interesting is we're all kind of, I think, probably sold on self-supervised learning if you can get it. It's a pretty good idea, we know that. But I think self-supervised learning usually gives you what I would call a representational prior. It helps you see and understand the world. Like if you did like pixel prediction or video prediction or something, then you might know that these are chests. You might not know the word for it, but you might know basically what they are, but you wouldn't know what to do when you see them. Because you just know how to see the world, right? You've just done pixel prediction. But behavioral prior that comes from VPT tells you what to do in this situation. So instead of just knowing that these are chests, you know those are chests and I should go open them and how to open them. And so you don't have to learn that. So it's like a next level kind of leveling up via pre-training in terms of learning to act in the world versus learning to see and understand the world. Another cool idea that we had throughout the project actually was that we were hoping that we could train a general IDM in like a feature project that would not just work in Minecraft, but might work across different domains. We actually saw somebody take our Minecraft thing and have it watch some other game and was decent at making predictions. But this work from Venuto actually confirmed our kind of wildest dream, which is that you can actually train a general IDM. So this work followed up on VPT and showed you can kind of train a generic IDM. And then when you give it the next task, you only have to give it a little tiny bit of data on that next task, and you can quickly fine tune it to do well on that task, which is pretty cool. All right, so to conclude, VPT can learn to act directly from vast, noisy, unlabeled online video. It does that by learning a behavioral prior, which we think is likely much better than a representational prior. It would be cool to go do that as a specific study, compare it to other techniques that just give you the representational prior. We didn't do that, but my money's on the behavioral prior. We also think that, and have shown really, that VPT is much better than doing behavioral cloning if you have a small amount of data. It's much better to take that data, train an IDM, and then unlock the internet's data rather than just be seeing on that small amount of data, which is really cool if you think about it. You can take like $2,000 worth of contractor data and unlock the millions and millions of dollars of unlabeled data that's on the internet. That if you had to pay for that, pay contractors to produce it, would take something like millions or more of money, hundreds of millions. So another cool thing is that VPT can use the human interface directly, mouse, keyboard, and act at 20 hertz. And like GPT, it has really nice zero-shot behavior. But it also gets much, much better if you start fine-tuning it in a pretty simple and efficient way to take advantage of with small targeted data sets. So you can kind of turn that nice generic prior into something that really works well in a targeted situation that you care about. And finally, or not finally, but finally for this slide, the three-phase thing worked surprisingly well for us. Pre-training on generic data, then BC fine-tuning, so supervised learning, behavioral cloning to a narrow targeted data set, and then doing RL from that. That was the best combination for us. And then the final slide of conclusions is that I thought it was really interesting that this KL penalty to the original model helped maintain the skills that were necessary for later learning by combining catastrophic forgetting and allowing exploration to persist for a really long time, basically to protect that behavioral prior until you need it. We saw all the kind of classic things you see out of OpenAI papers in terms of scaling, helping data. More data helps, bigger models help, and longer training helps. And in the end, the most important result is it learned to do a very, very difficult task that takes skilled humans over 20 minutes on a computer. And I want to think about that. Like, I think this method will work very well for computer using agents that use any software on your computer. And just think of all the things that you can do on your computer in 20 minutes. If you had a virtual assistant that could do that, I would be pretty happy. And I bet a lot of people would as well. So that's kind of really exciting. And then the final thing I just think is tremendously exciting is combining this with text, where you can tell the agent what you want it to do, and other options that you can do with text that are super exciting. And we showed kind of with preliminary work that allows steerability, it allows you to zero shot, do some things that you weren't trained to do. And I think the sky's the limit in terms of creating open-ended algorithms that take advantage of that to go off and learn an arbitrarily large and growing set of interesting skills. So with that, I want to thank all of my collaborators on the project, this fantastic team of people you see listed here, the organizers for the invitation, the reviewers at NeurIPS, and all of you for listening. Thank you.
Thank you so much, Jeff. I think we have time for maybe 1 or 2 questions from the audience. Quite a few. Thank you, Drew.
Yeah, I just wondered, it was a great talk and amazing work. I just wondered if you could say a bit more about your attempts to get the text conditioning to work. So why do you think why do you think it was effective, and maybe what do you think would be necessary to kind of get it to be even more effective and maybe take that whole approach to the next level?
Yeah, thanks for the question. So, I think the biggest thing you need to work is just time. We really kind of, we wanted to do it so badly that as the project was wrapping up and we knew we only had a couple of weeks left, we said, let's just go see what we can do. So basically one person, Adrian, for the most part, tried it for, a couple of weeks. And so we didn't have the time to really make it sing like we think it could. So I think, more tuning of all the choices that you make when you kind of make like how you get the text into the model, what size and what amount of time you're chunking the text over, things like that could really have helped. Another thing that I want to point out, which is kind of interesting, is that when you're adding the text conditioning, you're basically combating the text conditioned, what you want the model to do when you give it some text versus the default prior. So for example, if you put an agent in a situation where 99 times out of 100, a human is going to say, pick up a very valuable thing that it sees in front of it, like a diamond, but instead you tell it to break the diamond or turn around and jump in the fire, it really doesn't want to do that because its kind of default behavior is one thing, but now you're asking it to do something else. So we saw that tension where if we ask it to do, any of a set of kind of obvious things that humans would do, it's pretty steerable. But when we ask it to do something that a human would probably never do, it becomes less steerable. I think that's probably just about data. It's probably the same thing that you see with ChatGPT and GPT, where like in the low data regime, it kind of had these default priors and kind of wasn't as keyed into exactly what you were saying in the prompt. But once it had a huge amount of data, then it started getting better and better at kind of modeling these kind of corner cases and saying, oh, you really want me to pay attention to the text? Okay, I will do that. We also thought about, and I think it would be interesting to try to synthetically generate data. So it'd be pretty easy to say, go to a situation and say, all right, humans normally do this thing, but I'm going to synthetically kind of create a text prompt and then ask you to do something else and then show you what that other thing is. You might need RL or something like that. There's some techniques we had thought of to create that data, but that's another thing that might help in that situation. But maybe you don't need that. Maybe you just need better optimization, more data, more scale, more compute.
Thank you, Jeff. I think maybe one last question.
Thank you, Jeff. I do have a question about what you were saying in one of the slides that the IDM, there's some indication that you can extend it to other domain. So let's say you guys took 70,000 worth of this video, which is a computer game, right? But could you in theory take, let's say, tens of thousands of hours of people, let's say, driving, you know, from the driver perspective? I'm talking about real life driving on YouTube, right? And of these people just live streaming that drive in trucks and in cars. Do you think that that model can be extended to real life, you know, video footage like those? Or do you still have...
I apologize. I'm having a hard time hearing the question. Could you try to summarize it really quickly? Or maybe that, yeah, maybe you could, the microphone up front is better. Maybe you could summarize it.
I can try to repeat it really succinctly. Basically, yeah, for the other domains for the IDM, could you, for example, apply this to, let's say, videos of driving, tons of unlabeled video? How does that look like there?
Yeah, I think that the challenge to things like robotics and driving is that the action space, you know, like if you wanted to do it on different robots, the action space of different robots is literally different. So what is the IDM supposed to do if it's trying to predict actions that different robots could consume? And so I think it's a fascinating future research direction to try to have the IDM predict actions in some kind of abstract action space. And then individual robots or cars would have to then convert that to kind of whatever actions on that robot or car affect and accomplish the abstract action that is being produced. But if you basically had all the same car with the same action space, then yeah, I think, you know, like I can watch somebody driving a Tesla and I can know, oh, you must have turned the steering wheel to the left. You must have hit the brakes. You must have hit the gas just by the video. And so I can basically predict that. And then the question is just how do I map that back into the specific model vehicle? And if I was trying to do it just for one car, I probably could, it would be pretty easy. I think an interesting challenge is how do you do it across different robots and different cars.
Great. Well, thank you so much for the wonderful talk, Jeff. And I guess if you have further questions, yes, please reach out to Jeff offline.
Okay, and thank you once again to the team who did the work, who are awesome, and all of you for listening, and the organizers for the invitation.
Some brief logistics. So I guess we'll all maybe walk over to the main building now for the opening ceremony speech, and then we'll come back here at 2:30 for the poster session.
Yep.
Okay, cool. So yeah, thanks for joining and welcome back. I'd like to introduce our next speaker, Elaine Sir. Is an incoming assistant professor at UC Berkeley. She received a PhD in computer science at Cornell University in 2022, advised by Yoav Artsy. Her research spans natural language processing, machine learning, and computer vision. And she works towards developing learning algorithms for systems that can learn language through interaction. Thank you, and I'll let you take it away.
Yeah, sure. Thanks again for the invitation. Today, I'm going to talk about sort of a high-level research vision and motivation, and then one work that's currently in preparation that sort of fits under this high-level goal. So the title of this talk is Interaction-Driven Continual Learning for Instruction Following. My affiliations here, I did the work at Cornell, but now I'm at AI2, so I just put both of them. Okay. So my high-level research goal is to build learning natural language systems, and these systems must complete two goals. They must interact with users through natural language. They also should continually learn through those interactions. So as our computing systems become more ubiquitous and more complex, they're also becoming more opaque to users that don't have expert backgrounds in computing. Now, the expressivity of natural language could expand access to these systems, and allow us to create these accessible and expressive interfaces to things like mobile devices, robots, and databases through natural language interactions. I'm going to go through quickly a motivating example. This is in this scenario, a user is interacting with a robot, collaborating with a robot to build a radio in a workshop environment. And their collaboration will be effective through a natural language conversation. So the interaction begins with the user asking, can you build the amp while I add the volume control? Here the user is sort of dividing the high-level task into subtasks. They're going to take care of some of those tasks. They're going to assign some of those tasks to the robot. The robot responds with a clarification question of which speaker should I use? And the user responds with this referring expression, the smallest one in the rightmost bin under the bench. Now, here we see an example of our first challenge of this robot, which is that it needs to be able to understand how language is grounded in its visual and situated environment. So here, the robot has to take into account this really visually complex and cluttered workshop and identify the rightmost bin under the bench. And then it actually has to manipulate this bin, open it up, look inside, see all the speakers, and then identify the smallest one in the bin. So both of these are grounding problems of grounding elements of this referring expression to visual observations and actions in the environment. So a little while later, the user asks, are you done? And this is after, the user's taken care of some tasks and maybe the system's done a bunch of work as well. So despite many things going on in between, the system has to still recover the meaning of this ambiguous question of, are you done? And in particular, in order to resolve the meaning, it has to take into account what the user said earlier and what the system was working on just now, which is the fact that it's building an amp. So this is a second kind of interaction context, which is that the language meaning is dependent on what's happened so far in the interaction, what common ground has been built between the user and the system. Now, being able to address and generalize to a wide variety of environments, including really cluttered environments, different kinds of language use, different ways that interaction history affects language meaning, really stresses our existing systems, especially when we're relying on a huge amount of training data that might not have examples of interactions and things users might ask for like this. But we don't just have bad news in this scenario. Also, our system answered yes here. We don't just have bad news here, we also have a lot of learning opportunities. Or many opportunities, but particularly a learning opportunity. So one key thing that we can get from interaction is user feedback. So for example, our user asks the system, can you grab me a handful of 10 kilo ohm resistors? The system maybe hasn't seen the word handful before. It looks up the closest word that it knows about in the embedding space, and that's like a pack of resistors. So it grabs a pack, hands them to the person, and says, here you go. Well, this is more than the user wanted, so they will correct the system using a natural language feedback. And they'll say that's not a handful. A handful would be 5 or 6 resistors, not the entire pack. So the first thing I want to point out is that despite the system making this mistake, because we're in this interactive back and forth setup, not all is lost. The interaction doesn't just fall apart. We can continue on. The user's probably just going to grab the amount they need and then maybe ask the system to return the rest of the resistors. But what's more than that is the system could actually derive a learning signal from this feedback and update its understanding of the word handful to mean 5, at least in the case of resistors. Another key challenge in this scenario, which is really prevalent and really arises when we have these back and forth interactions, is that it's extremely non-stationary. So the system's behavior is obviously going to depend on the user's behavior because the user is going to ask it to do various things throughout the interaction. But the user's behavior also depends on the system's behavior. So the next day, our user returns to the workshop and says, I need 5 220 microfarad capacitors. Here, the user has deliberately changed the language they're using to go from handful, this really vague term, to a more precise term of 5. And they do this precisely because they observed the system's mistake the prior day. So rounds of interaction where the user is updating their model of the system and the system is updating its model of the user. And we have this non-stationary dynamics that are really very, very hard to capture, if not impossible to capture with large static corpora, like examples of 2 humans interacting with each other. And the reason we can't capture that is because we just don't have examples of humans interacting with our system. But we actually have a really good opportunity here, which is that as we deploy our systems in interaction with people, we can use those interactions to continually train our models to adapt to the user's adaptations. So the scenario that I'm going to focus on today is a collaborative interaction, which is sort of an abstract scenario that gives us some nice features with which we can study language use. So in this scenario, we have 2 agents acting in a shared world towards a common goal. They have to coordinate their actions toward that goal. They do so through a natural language interaction. This exposes two core natural language problems: language understanding and language generation. So for language understanding, we want our agent to map a user's utterance and its observations of the world and the interaction history to some actions. And for language generation, we want to learn this function that maps a high-level interaction goal, a world state, and an interaction's history to an utterance, which is then sent to a user. So a nice aspect of this kind of the kind of dynamics that this interaction setup supports is dynamic delegation, where as the user's interacting with the system, they can dynamically decide who should do what or what kind of language they should use throughout the interaction. So here the user says, "Can you take the pliers?" And the system sort of retreats to the corner of the room, obviously not what the user asked for, but again, because we're in this interactive scenario, the user can just sort of adjust to the system's mistake, say, "I'm just going to do it myself," maybe issue a simpler task to the system, and then just continue on with the interaction. So this is nice because this interactive setup supports more streamlined collaboration, because we can have this back and forth error correction feature, but it's also just one form of adaptation and change within interactions that supports continual learning. So continual learning is very core to natural language use. We use explicit and implicit feedback to drive our own language learning. So for example, if I could see people in my audience right now, which is a little hard, I'd get maybe head nods or maybe weird, like, "I don't understand what you're saying" faces, and I can use that feedback online to adjust how I'm giving a talk. That's just one very small example. We also expect our human interlocutors to adapt their language use to the feedback that we give. Maybe we'll repeat what our friend says if they say it to us as sort of a confirmation feedback. There's just a huge amount of ways that we give feedback to other human interlocutors to sort of shape the language that we use with each other. And if we build systems that transform these very natural feedback cues into learning signals within interaction, these systems are going to better support collaboration with their users, and they'll also learn really efficiently because they'll basically be making the most that they can out of an interaction with a user. We have a variety of different kind of feedback, but some of the feedback we might get in human agent interactions includes explicit feedback. So here our user says, "Hold this for a second," and the system moves over and grabs the pliers. It gets some positive feedback, but then it again retreats away from the user with the pliers in hand, and it gets some negative feedback because obviously the user didn't want it to do that. We might also have implicit feedback. So for example, where a system learns by observing the user's behavior, and we actually explored this in a work a year ago in Tackle. The citation is Kojima et al. 2021. So for example, our system might have an intent, which is that it wants the user to bring it a hammer, but it erroneously maps this to an instruction, "Bring me a saw." Now, our collaborative and cooperative user, of course, will bring a saw to the agent, right? But this is not what the system intended the user to do. So they can derive a learning signal from this, which is that because the user did something that they didn't intend to convey, they probably didn't convey this intent correctly. So just to summarize this scenario, we have two agents acting in a shared world towards a common goal. And what's very critical is that they use natural language to coordinate effectively. And through this, we can study two language problems, generation and understanding. We also have nice aspects of dynamic delegation and other features that allow more streamlined collaboration. And then we have opportunities for continual learning with our users. So today I'm instantiating this scenario in Serial Bar, which is a situated collaborative environment with sequential natural language instruction. So every interaction in Serial Bar takes place in an environment like this one. These are simulated worlds, but they're all like randomly generated with some kind of environment generation process. So we have paths laid out in the right way. We have a variety of props for the users to refer to, like we have windmills, houses, tents, plants, and stuff. We also have different kinds of terrain. So the agents can walk on the path or the grass, but the pond and the mountain act as obstacles. And then finally, we have a variety of colorful cards scattered around the board. Now we have two agents here, and they have distinct roles. So the leader's role is to plan who should do what towards their shared goal by taking into account the entire world, essentially, and then divide that plan into what they should do and what their followers should do. execute their own part of the plan, and then write an instruction telling the follower what they should do, right? And then the follower's role is really just to follow instructions to the best of their ability. The shared objective is to pick up matching sets of cards where you have 3 cards with a unique color, shape, and count across the cards. So for example, in this particular game board, as the leader, I might choose to first get myself the 2 pink stripe card, and then have my follower get this 3 red triangle card, and then this single orange square card. And this makes a valid set because we have 3 cards with 3 different color shapes and counts. Now, if we were to pick up the set, we would earn a point, and we'll be able to keep picking up sets until the game ends, until we run out of turns, essentially. And at the end of our game, we'll have a final score, which is a measure of how well we collaborated. And critically, it's a measure of how well we collaborated by using language. So we really designed Serial Bar to require natural language coordination through, in this case, the use of natural language instructions. So we designed multiple mechanisms to further encourage collaboration in Serial Bar. So we have a observability gap where the leader can see the entire game board, but the follower only sees a first-person view. So first of all, this encourages the follower to follow instructions as closely as possible. So if they decide to go off in some random direction or pick up a card that the leader didn't ask for, that's going to be just detrimental to their collaboration, and both of the players are going to earn fewer points if they do that. But it also encourages leaders to write followable instructions. So if I just told the follower to get the red triangles card, they're going to be a little confused because they don't see one in their view. They're going to wander around in a place that I don't know where they're going to go. So I really have to tell the follower here to turn around so that it can see the red triangles. Same goes for references to props. Maybe I'll say, you know, move towards this tent and then turn left, head toward the tree. Then you'll see the pond and your card is on the right, or something like that. We also have a capability gap where we allow the follower to take more steps than the leader per turn, which means that they can move farther. So this encourages leaders to actually make use of their follower as a partner by giving good instructions. If the leader just tells the follower to just wait at every turn and not move at all, they're not going to get hardly any points, maybe 1 if they're lucky. So it's really important that they write high quality instructions to the follower. This also encourages leaders to delegate longer and more complex paths to the follower because they just have simply more opportunities to move around. So I want to take a quick look at what it's like to play Serial Bar. I'm actually going to be collaborating with a model. This is in instruction. I think I'm there. Yeah, this is an instruction following model. So it's going to map my instructions as the leader and its observations of the world to actions. And this model was actually trained on data that we collected from human agent games. So I'm going to start by getting this 2 pink stripe card as the leader. And then I'm going to write 2 instructions for the 2 cards. I'm going to say turn around and get the red triangles next to the mountain. And then I'm going to say then get the orange card. So these are the 2 cards that I mentioned earlier. I'm not going to move anymore because we're only going to get 1 set. So I'm just going to end my turn and let the follower move. Okay, so it's moving, it's turning around. That's great. It's heading toward the red triangles. That's exactly what I was looking for. But there is a bit of a problem because down in the right-hand corner here, you can see there's actually another orange card. Oh no, okay. You can see now we have an invalid set because the cards are highlighted in red. And that's because the card that the follower is standing on now is a triangle card, the same as the one behind it. Okay, so I made a mistake as the leader, but it's not that bad because we can recover. We're in this live interaction. I can issue just another instruction. We can get over this little mistake and continue in the game. So I'm going to write 2 more instructions. The first is deselect the card you are standing on. And then I'm also going to say turn left and get the orange square past the windmill. Okay, so I'm going to end my turn again and let my follower move, and hopefully we can recover from this mistake. Okay, so the follower has deselected the orange triangle. That's good. And now is moving left, kind of getting stuck behind the windmill, but still okay. Yeah, all right, it's going past the windmill. And let's see. Yay, okay, so we picked up our set and we got our first point. I'm not going to get any more sets, but that's just an example of the game and one of the models that we trained through continual learning. Okay, so like I said earlier, this scenario is an instantiation of this broader collaborative interaction scenario. So we have a leader and a follower acting in this shared world towards this goal of picking up matching cards, and they coordinate through the use of natural language instructions. So of course we can study two language problems by building systems that generate instructions or that follow instructions. We can study, or we have this nice aspect of dynamic delegation. You just saw me dynamically delegate tasks where I ask the follower to deselect a card because it selected the wrong one. We also have opportunities for continual learning. So the model that I just showed you was trained with explicit binary feedback provided by users in interaction, but we can also consider learning from implicit feedback. So as an example, I learned as a leader, I shouldn't be so ambiguous in the instructions that I write because maybe my follower will select a card that I didn't intend it to select. Okay, so now I want to move on to work that we're preparing for submission, which is continual learning for instruction following. So in particular, we're studying the task of instruction following. Like I said, this is exactly the task of the model I was just interacting with. We want to map user instructions and observations of the environment to actions. And our goal here is to actually learn and improve the system's language understanding through live interactions with human users. So during interactions, users will write new instructions, and then as they observe the system executing their instructions, they will provide binary feedback. And the way that we learn from this data is casting it as a contextual bandit learning problem. So the learning signal that we use here is provided by leaders as they observe instruction execution. In the interface, we have buttons that they can press, like positive and negative. They can also use keys on their keyboard. So it's binary feedback. They can also reboot the follower if it's doing something really bad, just in order to not make the game just completely fall apart. That just halts the follower and resets all of the instructions. And really, this feedback is very intuitive to give. They can give it at any time during the follower's turn. There's no restrictions really that we place on what kind of feedback people give our system. So this is pretty noisy data. I'm just going to go through a quick example of the kind of feedback we're getting here. So here our user wrote, move forward and slightly to your right until you see a card with 2 black squares, pick it up. So here our follower is, we want it to get this 2 black square card. It's by this yellow tree right now. So the follower is moving forward. So it's sampling and executing this action, moves forward again, moves forward a 3rd time and gets a positive feedback. Continues moving forward, and then it actually looks like it's going to step on this orange star card, so it gets some negative feedback. And then it is evading this orange star card and gets a bit more positive feedback as it's clear that it's going to get the target card. Okay, so that's the kind of feedback that we're learning from. I'm not going to go into depth in this talk right now, but we apply some heuristics to densify this feedback. You can see that only 5 of the 12 actions have any non-zero feedback. We also have some noise present in this data as well that we fix with heuristics. Okay, so the kind of data that we get from interactions is for each action that we've executed, we have access to the world state in which the action was executed, the instruction that the user wrote, the action itself, the probability that was used to generate this action. So this is from the policy that we were deploying. And we also have feedback, which is binary, positive or negative. So our objective here is to maximize immediate expected reward, which forms a contextual bandit learning problem. Our gradient is the feedback F times the gradient of the log probability according to the current policy parameters. So for positive feedback, actually, just to clarify, we're actually learning in an offline setting here where we're collecting data in interaction, and then we're applying training in multiple epochs offline to get new model parameters, and then redeploying the newest model parameters. So when we have positive feedback, this is actually really easy to learn because essentially we're doing supervised learning. But there's a problem that comes up when we are training with these negative examples, because as we continue to train on a negative example, we continue to push the probability of that example close to 0, which is good. except that the gradient, except that the log probability is being pushed further and further to negative infinity, and our gradient is exploding and we don't learn. So what we end up doing to address this problem is we add a coefficient, which is derived from the inverse propensity score. So the IPS term, inverse propensity score term, is this one in the middle, where we have the probability of the action that according to the current policy divided by the original sampling probability. So that's the IPS term. We also clip this value by 1 at the maximum so that we're not overfitting on positive examples. And this addresses our issue of training on negative examples, because as we are continuing to decrease the probability of those examples, the coefficient of this term also decreases. So one of the nice things about casting this as a contextual bandit learning problem is that it's relatively data efficient, especially when compared to general RL. This is especially important in the large and complex state space that is instruction following, where our policy has to represent the space of all possible environments and all possible tasks, because tasks are specified in natural language. It is especially crucial in our training regime where we are collecting data online from human interactions. And each interaction is extremely expensive, both in time and in money, to collect data from. So we really want to make the most of the data that we do get. So as a high-level overview of the learning process, we begin by initializing the model using some supervised data. So these are recordings of human-human interactions. So it's basically gold standard demonstration data. We basically do the minimal amount of supervised learning needed in order to get a regularly decent policy, or a generally decent policy, because if our policy is just kind of randomly wandering around the environment, we're probably not going to get any positive feedback from the agent's actions. So when we actually deploy our model, we will sample actions from the policy conditioned on user-written instructions and the state of the world. And you can see also parameterized by theta R, where R is the current round index. So we're doing this training and deployment in cycles, where we have a number of rounds that we do this process for. So during interactions, we collect both the instructions, agent executions, and the feedback data that our users provide. And this allows us to construct new training data sets that we aggregate and then use to do contextual bandit training to get new model parameters. So in practice, we end up initializing our model with about 456 human-human interactions, which is almost 9,000 instructions. The main evaluation metric that we want to use is instruction execution accuracy. For every instruction written by a user in a particular round, how well did the model follow that instruction? But we can't do this automatically, because as our users are interacting with their system, they're adapting the language they use, and we're getting completely new instructions each and every round. So we don't have demonstration data to compare against. In practice, what we'll do is we'll sample some instructions written by a user during the rounds and ask other users to provide us with judgments of whether or not the system was correct. So we did a long-term study as one of the studies in our work, where we ran this process for 11 rounds of training and deployment. We had about 250 to 350 interactions each round. And we see that this instruction execution accuracy is improving significantly over time, from 67 to 82% accuracy. We also see that the interaction score, so this is the high-level metric showing collaboration success, is also improving significantly from 3.3 to 5.3 points, which is a very big improvement in terms of the serial bar scoring system. Now, you might be wondering, because users are adapting their language and their behavior when interacting with the system, are the adaptations users making just making it appear like this model is performing better? So you would think, maybe this model is actually really bad, and the reason we're seeing improvements up here is because users are just issuing simpler and simpler instructions that they know the model can complete. And the story is actually a little mixed. So we actually perform an experiment where we deploy the very first model trained only on human-human demonstrations, again after user adaptation, alongside this final model that we trained, which also has access to these continual learning data. And we see that, yes, actually, this model is performing better after user adaptation, even though these are the exact same parameters. And when we investigate the language people use, we do see that there is a bit of simplification, some convergence on the kind of tasks people are asking for. People are becoming better at their strategies in asking the system to do things that are going to be better for the score in the end. But this doesn't explain all of the improvements. We still see a really big gap between this initial model parameters and the ones that are constructed from the data we get from continual learning. We also see that the feedback itself that people are providing is getting increasingly positive and decreasingly negative over time, which is what we would like to see. But we also see that there's still some negative feedback at the end. The model is not perfect, it's still making mistakes. We hypothesize that this is just due to a modeling limitation of the actual architecture. And then finally, we also asked users for their impression of the system after each interaction takes place. So we asked them whether they agree with various things like whether the system completed the tasks they asked for, whether they only did what was asked, and whether the system was efficient. And we see significant improvements over time as users interact with our system. Okay, I suppose to conclude, I think we should really study these collaborative settings where humans and systems are interacting with each other, especially when users have a chance to adapt their behavior to the system's behavior. And I think continual learning is going to be a really important part of that equation. And there's a lot more we can do with human feedback and interaction. And I want to thank my collaborators and thanks again for the invitation.
Cool. Thanks so much for the great talk, Elaine. Are there any questions from the audience? Maybe to start off, I guess I'm quite interested in, the themes you mentioned with continual learning and like how the human interaction and human follower interaction kind of seeds all of the good behaviors, interpretability that follows. I'm kind of curious if you see a way to kind of guarantee that kind of alignment or human interpretability when you have increasingly human out of the loop scenarios, whether that's self-play or other kind of learned language scenarios.
Yeah, so I personally haven't done much with self-play before, but I know of existing work in like emergent communication and things like this, which also find that regularizing your self-play or emergent language model by an existing language model, for example, will keep it closer to human language use. I definitely see opportunities to do sort of like self-play between the rounds in this setup where you deploy the system, you collect some data, you train not just an instruction following policy, but also an instruction generation policy, you do some self-play, but then you really do have to regularize it against your human players, because you really want the system to be usable for humans. So I definitely think that there's opportunities for self-play, but ultimately, if we want our systems to interact with people, people should be part of the learning process. And one way we can do that is just by regularizing with models of people.
Thank you. Any other questions? I think I had a, sorry, I'm very curious because this line of work is quite new to me, but I'm wondering if you saw any qualitative differences in the kind of last work you mentioned when you're kind of starting with human interaction and then you're like going over time and you pose the question, is the agent just kind of learning to kind of like predict like lower, like shorter horizon instructions that are simpler, easier to understand, easier to follow? I'm wondering if you saw any other kind of qualitative like emergent behavioral changes as like the agent switched from learning from human interaction to having more agency and like determining its own data distribution. Are there any like insights you can provide?
Yeah, so I will say, yeah, the language people use when interacting with their system off the bat is going to be, it's already very simple compared to what they use with actual people. One of our hopes was so that the people would use increasingly complex language as they began like trusting the system a little bit more. We actually saw that the biggest change in how the humans adapted was, so when users write an instruction, they can choose to issue like 0 target cards, 1 target card, or 2 target cards, like get both of the cards in front of you or something like that. We found increasingly that people were issuing instructions with a single target card. So I do think that their instructions became a bit more formulaic. So that's probably the main human adaptation. In terms of the agent adaptation, so our exploration policy was essentially just sampling from our policy. It wasn't anything that interesting. We weren't like seeking out action sequences that might be more informative for the learning process. I think that's definitely like a way to go further. But in terms of like the policy itself, it was sort of just refining the alignment between like the instruction and the execution and the environment. Yeah, I don't know if that answers your question, but.
Yeah, I think that does. The humans selecting only one card is quite interesting of a trend. Thank you. Great. I guess thank you so much then, Elaine, for your time and great talk.
Yeah, thank you.
I'll pass it off to Mohit now to introduce our next speakers.
Okay, cool. Next up, we're excited to have Jonathan Bisk. Jonathan Bisk is an assistant professor at CMU, where he works on modeling the semantics of the physical world and connecting language to perception and control. Jonathan is one of the pioneers of convincing NLP people to do more robotics and vision. So it's excited to have Jonathan here at a CoRL conference. Let's see what he has to say.
Oh, is that working? That just works. Cool. All right, sweet. So thank you, Mohit, who will get cited several times in this talk. I kind of was thinking like there's sort of two versions of talks that I can give. There's like the talk where I say, here's something cool and new that we did recently, and I'm sort of promoting it. And like, there's definitely some of my citations in this. But the other thing that I could do, which I thought might be more fun, is to basically take a little bit of a step back and then complain a little bit about the field. Partially to spark some conversation about where we are, which I think is sort of a maybe unique moment, and then also sort of what the implicit limitations maybe are. So some of this is like a little bit provocative, maybe more so than I actually believe, but just sort of for the sake of laying stuff out. All right, so let me start with the title. Can we really connect language to robotics? And you might be like, well, we just came from like a keynote that maybe said that. You might also be like, duh, like Cynthia and Stephanie did this like a decade ago, like solved. We know it's up. Yeah, but we're not all as cool as they were or are. And so like, we're still trying to catch up and figure out if there's a place for us in this space, right? So the first thing I want to do is take a step backwards, speaking of a decade ago. So a lot of papers in this space tend to cite this work here by Chen and Mooney, and then also the stuff that Ben Kuipers had done previously on sort of instruction following and in this simulator. Most people have never actually read this paper, and most people have definitely never seen the simulator. So that's one of the things that we're going to talk about very briefly. The other thing that was happening about the same time, and I like to juxtapose them, is the stuff that Manuela Veloso was doing on sort of navigation in the wild with these sort of cobots. And the reason I like juxtaposing these are happening almost exactly at the same time in the literature is that what we have on the right is a real robot with all of the problems that entails. They're sort of using Wi-Fi for localization issues inside of the buildings at CMU. And the trade-off was, in order to get any of this working, the language is incredibly simplistic. And so it's very sort of like, you know, move from this office number to that office number, things like this. And on the left, what we had was this incredibly simple simulator, which we'll talk about more in a second. But the trade-off, but the flip side of that was that we had more natural language, we had more compositional, more complex things. So let's sort of dive into that a little bit. And then we'll come back to what I think for most people was like the sort of most recent interesting middle ground, which is the stuff that Peter Anderson did with vision language navigation. So that was sort of like this new environment that I think was really fun for a lot of us because it meant that we were getting a little bit, it felt like we were getting a little bit of the best of both worlds. So we'll come back to that. All right, so the simulator. So the way that this worked was that you had these maps of these environments that you were navigating through. You had segments, and there was something unique about each of the segments. You see this in the colors here, and you had landmarks, which were literally images, hat racks, lamps, so on and so forth. This is the first person view of those things. So super high fidelity graphics. And what you were doing was you were trying to sort of, you would do these instructions. There was like, turn right at the lamppost or go past the butterfly, so on and so forth. And so here it is. I got their old Java code running. So we're about to be this agent that you can see with the cone. That's our direction of facing. We're in this map. And then what's happening here, which I'll go into this more in a second, because it's a little hard to read, I think, from your perspective. But there's a natural language instruction, and then there's the parse that's coming out of it. All right, so let's play this. All right, so we have this agent. You're going to see its perspective changing as it's moving through this environment. And we're getting these instructions. Turn left turns into just turn left. And takes us a second for it to move. Go forward along the pink flowered carpeted hall, 2 segments to the intersection with the brick hall turns into this travel with a verification step, where something that's sort of a post condition to guarantee that we've achieved what we're supposed to. Anyway, it's not the most exciting video in the world. So like, we'll move on, but this is what we were doing. And this is what this meant in terms of the instructions. Take your first left, go all the way down to the end of the hall, hit a dead end, go towards the code hanger, turn left. These are simpler than VLN, but I don't think they're fundamentally that different in nature. I think the other thing that's important is that this is a reasonably short path. VLN was also, I know there's been work since then, we'll get to that, but like was also, basically a 6-hop kind of thing through a house. And so if you had an instruction like this, what you were trying to do is turn it into this symbolic representation. You were trying to turn it into this parse. And so this is what the language community at least was doing in terms of this kind of grounded navigation space, is that we were making this assumption that fundamentally the right way to approach this is semantic parsing. I have a symbolic problem. I have symbols on the input. I'm going to produce high-level symbols on the output. And then I have a simulator, or I have something on the other side that can just execute those. And that is a great paradigm. It's very convenient as language people to do that. And so therefore we can kind of think this is sort of our grounding API. This is our sort of intersection between where language meets, we'll call it robotics for the moment. Is basically, if you could implement all these primitives for me, then I can do all this language processing for you. And so now we have sort of an agreement of like how we're going to have the two communities interact with each other. And so then when we moved to VLN years later, it's definitely now a richer environment. We've got, these real images. Still have a sort of discrete set of paths, more complicated than the grid, but it's sort of still that kind of Google Street View hopping around a grid kind of, around a graph kind of setup. And so we can ask a similar question, which is sort of, well, what is the API boundary, or what is the contract that is implicit in this formulation? And so we have kind of this language to view API, which is sort of what we kind of settled on in the community. So I'm assuming most people are familiar with these things, but just as a quick aside, the basic idea here was that you have an instruction for how to move through a house. You had real scans of real homes. And then there was this decision at some point that the best way to model this was to take every single possible view, turn that into an action. And so what you were now learning was an alignment. I had a linguistic encoder, I had a visual encoder. Do they agree on whatever the, which of these is most similar to the current state? And that tells me what I'm doing next. So that gives us an interesting and actually useful API. So we had this nice sim to real work that came out later that Peter did. And then there were some other groups, I think Zolt had some stuff in this space too, where basically like, okay, well, if I can do waypoints prediction in an environment, if I can do, I'll run SLAM in advance, I'll map things, maybe I'll do it online, and I'll be able to do some amount of basic navigation between those little 2-meter distances. Then I can sort of get this nice situation where you make more sophisticated language stuff on this side. And as long as I can get you an image that you can do an alignment to, then we're sort of good. The robotics side is sort of siloed. We have this API boundary that we've agreed on. So then Mohit comes along and says, what if we make our life a little bit more complicated? And so here we have sort of the Alfred setup. We're in a simulated home. Now we don't have just navigation. We're doing some amount of interaction, but the interaction is still going to be constrained by something, right? It's going to be constrained by something that we defined, either because the simulator itself has some set of primitives that it's comfortable with, or because we as engineers of a data set came up with something. So what did we decide on? We decided on a discrete set of actions here and this sort of mask API. So within Alfred, if you're not familiar, you have some high-level language task you're supposed to achieve, rinse out the washcloth, look at a book under the lamp, stuff like this. And the agent is going to move around this environment. The moves are from a small fixed set of navigation primitives, and then you're going to interact with objects, and the interactions are going to also take a reasonably small set of primitives, and then can you basically get a good mask RCNN model or something like this to actually predict the object that you're interacting with. And so now we have a new API. We have language to action plus mask. And so we can ask questions at each of these stages, which is like, at what point are we actually doing like embodied language or language to robotics or stuff like this? Because what it kind of seems like is happening is that in each one of these different data sets, we're kind of saying like, our community, whichever it might be, whether it's the language community originally, for instance, the stuff that Chen and Mooney were doing, whether it's the sort of vision community with VLN, I don't know what community I am, but whatever we are with this, is that we're sort of saying like, this is about as far as I'm comfortable going. And then I'm going to assume that you on the other side, whatever your field is going to sort of take care of the rest of it. You're going to sort of meet me at this point. And so we don't actually have information really flowing between those two things. We're just sort of, and we're not even necessarily doing it collaboratively with the sort of like larger community that I think we're all kind of have several toes in. But instead, we're kind of just sort of saying like, here's kind of the boundary that makes sense. And there's good reason to do that. I'm starting this talk on the downer side. So since Moby's here, I'm going to just like really, bash on him. So you might be like, okay, but what about when there is a real robot, right? You were showing me a bunch of simulators. What if there's a real robot? Well, there's still an API. It's maybe a more reasonable API, but there's still an API boundary. So in Clipport, we now actually, Dieter already, talked about it this morning. But basically now we have language and we're trying to give some sort of a goal. And that goal is then, some image or something, some representation that's going to tell us what we want configuration of the world to look like. So what is our API? Our API is now basically, it's impossible for you to see this back there, but basically like where our manipulator is supposed to be, let's say at the start, and where the manipulator is supposed to be at the end. I would argue this is definitely a better API than what we had up until now. It's grounded in the real world more so than, for instance, the masks were. But it is still basically assuming that there's like a bunch of, whether it's inverse kinematics or motion primitives or whatever else, that are just sort of going to happen between these things. Language does not need to interact with those. Language does not need to know about them. They are on the other side of this. And so you could, continue to improve things here in isolation. So here's kind of what I'm speccing out at the moment. I'm basically saying I've got a bunch of stuff that was happening previously, like let's say 10 years ago. Stephanie had this really great stuff, which was running, if you haven't seen those old demos of like actually talking to a forklift and having it move stuff around. I think the reason that, she gets to have this sort of OG title is that if I was going to have a language controlled robot, I would not start with something that could kill me. But like she was, you had this discrete sort of graphical model of symbols that you were grounding into this thing. Here we had these semantic parsers, again, a bunch of symbols, but it's not really the case that these are not doing that. It's just that these are now incorporating different amounts of sort of the perceptual space.
I'm not sure I understand.
Yeah, Siri definitely doesn't understand. Okay, so now I'm going to be really, like throwing shade at people. Where do we put SayCan and ProgPrompt? Do we put them over here? Do we put them over here? Does it even matter? So the main thing I want to point out is not that there's anything wrong with literally any of these works. The main thing I want to point out is that basically what is happening partially out of necessity historically is that we have had to define some sort of boundary for what we're willing to or can work on. Sort of there's only so many of us working on any given project. And so one of the things that I think is nice, but then also we can use the same lens when we're discussing this more recent stuff is basically like, okay, well, For example, this morning, or I guess early this afternoon, and this talk was sort of like, what's the definition of a task? How many tasks? You know, like what is that sort of API that we're saying that the robot is going to implement? And then how much sort of generalization is going to happen as a function or composition of those tasks? And at what point does language play a role in defining a new task or defining the way you actually execute a task and things like this? And so I mostly want everyone to just sort of see the community has this kind of structure or this landscape where we're all making some of those decisions, and then decide for yourself sort of where you think is most impactful or important to be sort of pushing those things around. So another way that I might ask a similar question is the progress that we're seeing recently in terms of all of these models and in terms of changes to that sort of API boundary, because visual representations are, let's say, getting more abstract. So maybe part of what was happening is that now we have visual representations of scenes, for example, if we're in like a navigation setting where we can talk about, oh, I want the thing that, you know, holds water. And I have a good representation of all kinds of receptacles that might contain that rather than simply the labels for cup and mug and whatever else. And so I have these better visual representations. So that's allowing me to do this kind of generalization. So maybe vision is kind of rising to the occasion in this kind of cool way. The other sort of question might be, is it actually that the language side is in this cool new space? And so the reason that we're in a kind of fun moment with these large language models is that they seem to just have a bunch of knowledge in them. So all of a sudden I have this thing where I can ask it a plan, I can ask it for more details, though I realize we started this morning off with Jacob basically saying, don't use large language models for planning. But you know, maybe what's happening is that now I don't just have the sort of old simplistic distributional properties in my language representations. I now have things about affordances, size, other stuff like this. And so that's kind of the new trick, the new tool that we have, which is enabling new stuff. It's possible that also just robotics is like maturing and is like better at a bunch of stuff. We have cheaper platforms that are more readily available. We have more shared libraries than we used to. And so that means that we're able to build more complicated sort of APIs and more complicated functions to be referenced by these other systems. Some combination of all the above. So the way that we also maybe you're thinking about this is that maybe planning was always sort of symbol manipulation. It was just in terms of sort of goals and kind of a task and motion planning kind of setup where we're saying like, oh, the tasks are always going to be these abstract concepts. Now we have something that's very good at manipulating those symbols in kind of novel compositional ways. And so as long as you can take care of the motion plans, we're all happy. And I think the most important question is, am I just being a real bummer? Because like I'm basically just up here like picking apart every single thing that we've done in the community. So I think we've had massive progress on all of these. I want to talk about what we are sort of maybe able to do now and what I think are some of the kind of interesting challenges for us to maybe try to address next. So as I said at the beginning, I'm supposed to be promoting a paper. I think when you give like a workshop talk, you're supposed to be like, oh, like, please go read my whatever. And I'm pretty sure that Vivi, my student, would kill me if I didn't say she does have a poster that you can go check out. But that's not the point of this talk. Okay, so here are the things that I'd like to argue that we should think about a little bit. So one is I want to think about maps a little bit more. We did some stuff here. A bunch of other people, this top one is Valtz's work. 2, languages and action space. We just heard Elaine talk about serial bar, and then also the teach data set as sort of possibilities there. I'm going to plug Valtz one more time in a language to control setting. So I'm going to talk very quickly about these as sort of interesting spaces that I think are somewhat underexplored in terms of the landscape of what we've been doing as a community. So why maps? So the thing I like about maps is that they're basically a spatial memory. And I think this is a nice transition for us. And I think it introduces a new dimension for thinking about those grounding problems that we had a second ago. So when we were thinking about like in the navigation setting, what's the image, what's the pixels that I want to see next, stuff like this, there's something kind of off, I think, about that for me in terms of like the way that I think about space. The fact that I have a sort of maybe abstract representation of how this building is laid out, and then I sort of work from there. The other thing that I think is interesting about maps, which is what this error analysis is to discuss, is that when we worked on Alfred, and so this is just the errors from film, the most interesting thing to me was some of the trends when you have sort of improvements on things like segmentation and depth. Now, I think naively that seems obvious, right? Of course, if you don't have a bunch of sensor noise, everything's going to be better. That's not actually what I think is interesting here. The ground truth segmentation experiments and the ground truth depth experiments that we ran are unrealistic. You will never have sensors that are that good, and you will never have vision models that are that good. What do I mean by that? If there is a handful of pixels, if there is a small piece of an object in the distance, there's no world or universe or timeline where a vision algorithm ever figures out what that object is. It's too small. It doesn't, there's no information for it to use. And so if we have strictly modular approaches to things, and we sort of say like, well, I'm just going to get better and better visual backbones, I think we're hosed. Now, if I told you in advance, I'm looking for my credit card that I lost, now all of a sudden a handful of pixels that have like sort of the right coloration or slight difference is a really good place for me to do exploration and probably to search for something. So there's this like tiny bit of context, which now means that something that even as a human I would never actually be able to detect, I now have a very good estimate of what the possible objects are, right? And so there's this argument that says that like that it's not that you shouldn't have a perceptual stack. We obviously have V1 and V2 and stuff like this before anything maybe interesting happens. But there's some point there where those goals or that language or something like this sort of needs to sort of weave in and then be like, actually, I want to kind of condition the way that you're viewing the world to have this sort of extra information. So that's one of the things that I think is sort of interesting there, because we can't ever actually predict from just a few pixels. And then sort of similarly, I don't think we're ever going to have sort of perfect depth estimation sensor or sensors and stuff like this. So there's a limit to what we can do there. So that's not a problem because again, we have all kinds of priors on the world, right? So even if I can't quite see something, I have very good estimates of what I think the natural shaping of an object is. And so this is why you can put a human in an environment and sort of blindfold them, and they can probably do pretty decent open loop control kind of tasks. And so there's this question for me, which is sort of like, what are the heuristics or what's that world model that we're using to sort of to get past those things? The other thing that I want to talk about, and then tell me when I'm running out of time because I forgot to start a timer. The other thing I want to talk about really quickly is what is involved in actually learning from sort of dialogue settings or more naturalistic data of this kind. So I think it's really exciting to be able to say like, hey, language is this action space, like that we should include as sort of one of the possible outputs. But this is just a random sample that I pulled from Teach. And we can start to break down what we see on this slide. So we have an instruction, which is like, please boil a potato, which I think is what we think of in an instruction following setting. Maybe this extra one about filling a cup of water, there's some sort of help there. But the majority of what's on screen, I mean, like done, smiley face, awesome, things like this, are basically, sort of social context kinds of things, right? So they're confirmations, they're being friendly and things like this. And then also we have stuff like information seeking queries. So then we have this question of like, how do we build models that know when they should be sort of asking for more information? In other words, going back to the original prompt, at what point I have some option, I have some setup, I have some API that I know I can interact with. How does the model know that the thing it wants to do is not possible in its own API, its own action space? And so we sort of need to know that before I think we can then get to that other interesting question of what does it mean to sort of learn new tasks or teach an agent something new, right? It's sort of, there's this kind of prerequisite requirement. And when you actually have traces from humans, so anyone who's done experiments with LFD and stuff like this knows this is a thing, but when you're actually getting real traces from humans doing things in an environment, which is what the Teach data set did, you have like a bunch of new sort of noise that you have to sort of reconcile. So on the dialogue side, You have to sort of figure out why this person is asking a question or when are they asking that question. You have to understand what makes that a useful question. You have to sort of figure out how to produce, who is it the thing that was provided back a useful answer. And then did they actually take correct actions? So the instruction following is sort of like only one part of what the complexity on the language side looks like. But on the action taking side, we also have a bunch of complexity. So when we analyze the percentage of actions in, for instance, validation seen and unseen on that data set that humans take, what we find is that like 40% of state changes were irrelevant to the goal. Like 20-something% of the navigation was irrelevant, interactions that were irrelevant, unrelated objects that we interacted with, no alignment with the text at all. Okay, that's not actually bad, but it does mean that the paradigms which are common, which is this sort of like, oh, well, here's a teacher and they're giving me sort of a ground truth, is not at all the paradigm in which we learned to do things. And so it's also not the paradigm in which our models should. So what's actually happening in all these things? Well, I think if you think about it for a second, it's exactly what you would do in any natural setting. If I put you in a kitchen environment you've never been in before and ask you to do something, what are you going to do? You're going to like look around. You're not going to sort of magically go to the exact right cabinet where the thing is that you need. What you've never interacted with, there's some sort of weird looking tool or something like this. You're going to kind of poke at it and stuff like this. So there's a bunch of that stuff that's happening. It's a bunch of that stuff that presumably a parent is doing and a child is observing, which doesn't actually align to sort of to the goals. And so how do we then build models that have some sort of, again, going back to this kind of prior, perhaps about like what the appropriate things are to do. Okay, as in like I should stop talking? Okay, that is totally fine. What we're gonna do is we're gonna just go like this on the next arrow a few times. So this is just basically saying it's really hard to know when to ask for help as a model, in part because when you build a model, or our experience is that when you build models that ask for help, they may generalize better, but then they will do worse in previously seen environments. So it's, if you can memorize an environment, that's obviously the right thing to do. Okay, so there's way too many slides here clearly, so I'm going to stop talking. The last thing I'll say is that one of the things that I think is interesting is that when we talk about language going to agents, language going to robots and stuff like this, we don't actually specify who the person is. It's just sort of this very generic notion of what a person is, right? And so that means that we don't actually like think about what prior knowledge they have. If you were giving an instruction to a child, it turns out you give very different instructions, which include things like how to, do something slowly, do something carefully, which tools to use, stuff like this. And we're sort of not accounting for that in our discussions. All right, sorry, Mohit. So our goal, I think, as a community is incredibly ambitious and incredibly difficult. So we want basically like as realistic an action space, as realistic sort of maybe egocentric vision, and then all this complexity in language as possible. And that's super hard. And so the conversation I sort of want to spark is basically like understanding where we've made these sorts of assumptions throughout all of our existing infrastructure, and then which of those are ones that we think are important to keep or are reasonable for the next decade, let's say, and which are ones where we think like that's actually sort of hindering us in terms of making progress towards that goal. All right, sorry, I'm done.
All right, cool. Let's get started. So we're excited to have Andy and Faye do a live demo. So just a quick introduction in case you already don't know them. Andy is a research scientist at Google, and also Faye is a research scientist. Andy works on vision, language, and robotics, and he's pioneered several contributions in picking, singulating, and tossing objects. Faye has also been known for working on simulators like Gibson and also the SEICAN stuff. So one thing I really like about Andy's work is that it actually works in the real world. And I came up with this line a long time ago, but he's actually doing a live demo of it. So take it away, Andy.
Cool. Thanks, Mohit. It's great to be here today, everybody. And I'm excited to, with Faye, do a live demo of Palm SEICAN. So just some context, we'll do the demo sometime at the middle of the talk. And before that, I'm going to talk a little bit about language and robotics and why I'm very excited about it. And I think that it's going to take a little bit of a stance, a little bit in contrast to Yonatov's stance, which is just, I think I'm very excited about what large language models can do. We're very excited at Google about one day building robots that can be around us, helping us in human-centered spaces with everyday tasks. And my colleagues and I, we work a lot on manipulation, getting robots to pick stuff up, put them down, move them around. And part of the hope is that with machine learning, taking a data-driven approach to ultimately train a bunch of models that are taking in pixels as input, actions as output, and over time, interacting with the physical world to gain the experience that you can ultimately learn some notion of bottom-up common sense. So as I like to put it, this is essentially learning a version of how the world works. The hope is that over time on the quest for shared priors, as we have many different tasks that we're training on, then the cumulative data that we need in order to collect over time starts to asymptote. The hope being that you have a bunch of tasks and you have the shared priors that are shared among the tasks, and over time, the amount of costs that you have to put up front for the amount of data that you need for each new task becomes subsequently less and less. And I think that the challenge here has been that in reality, this curve has been much more linear than we expected, and in part because there's just so much complexity that's packed into this bottom axis here. In the course of over the number of tasks that you do, there's a lot of complexity in the environment, the nuances in the way in which you set up your robot, the embodiment, the robot action space that you choose, and over time, the different types of contact dynamics that you would have to work around with. I think that we will still be able to see over time a logarithmic curve in the future, but I think that for now, it's likely going to be much more far out than we originally anticipated. Over time, I think that my colleagues and I are also realizing that deep learning at the end of the day is really a box, in the sense that it's really good at modeling the data points that are inside the box, but not necessarily as good outside. So in that sense, and I can't tell you how many times we've created this sort of plot where if you take the training data that you have and you draw a convex hole around the training data, then you look at the test time examples where you perform well, and you'll find out that most of them lie inside the convex hole of the training data. And so for those text examples that are outside the convex hole, they don't perform as well. And in those instances, you're usually testing extrapolation. And so you can kind of pick out and see what sort of algorithmic choices that you can make or some model architectures that you can tweak in order to get better extrapolation, because at the end of the day, what we care most about in robotics is the capacity to generalize. As a roboticist, I think it's also healthy every now and then to pop up a level and look at what other people in other fields are doing in NLP and vision. And I think that something that's really interesting to see in the NLP community over time is that they decided that it's a good idea to stick your entire universe inside the box. And so now every extrapolation problem becomes an interpolation one. And this is kind of, it sounds crazy, but it's actually working quite well. When you train a model on the entirety of internet text data, you can get effectively large language models that soak up all that data. And what's interesting is that in the training data for these models, on the one hand, you have newspaper articles, recipes, code. And on the other side of the data set, you have books, articles, and dialogue. And what's interesting is that you can take examples from either domain or different domains here. You can pick out two of your favorite and combine the two at test time to be able to do new tasks that you essentially recombine known constituents. Very interestingly. So this is something that you can do yourself. You can go online and go to your favorite large language model website and go ahead and ask things like steps to brush teeth with peanut butter in the style of Shakespeare. So yeah, take a spoon, fill it with peanut butter, place the spoon in thy mouth and start brushing thy teeth. It'll take the style and try to apply it to the list of steps. And it's absolutely mind-boggling to me that you're capable of essentially generating new training data points that live inside of this box, but at the same time combining known constituents. So I think that it's interesting to see these capabilities arise naturally from these large language models, and presumably steps to brush teeth and peanut butter in the style of Shakespeare didn't really appear in the training set. A quick primer on large language models, and in the interest of time, I'll go through this quite fast. Main idea is that your inputs and outputs are tokens, so these are pieces of words, and usually people use byte pair encodings. What that means is that you take a large unstructured text data set, and then each token is essentially a a piece of word and you cluster characters together based on how frequently they appear next to each other to construct these tokens. On the modeling side, you have transformers, and at the heart of transformers, you have self-attention. So ultimately, what's magical about the self-attention mechanism is that upon computing a feature transformation to Y, you're taking features that are coming in from all of your other tokens, X1, X2, and X3. And so, for example, the amount of feature contribution that's happening from X2, that contribution that goes into Y is weighted by the distance between X2 and Y. And likewise, the contribution of the features from X1 is weighted by its distance to Y. So the thing that makes self-attention so expressive is the fact that the thing that computes the distance and determines the weighting of this feature, X2 to Y, this lives on a metric space that's different from the features that are on X2 themselves. So your Q and K actually work together to construct a metric space, which is your feature distance, and then your V is your actual feature values, your actual payload that exists on X2. So the fact that these two are distinct and separate is actually what adds to the expressive nature of self-attention. So you can actually think of convolution as a special case of self-attention in the sense that the distance here, the weighting, is actually determined by spatial locality, so pixels next to each other. Okay, cool. So if you take the self-attention mechanism and you have feature representations or transformations interleaved, then you sort of interleave them together and you get transformers. And then ultimately, bigger is better. And I think my most favorite or most visceral example of this actually comes from a talk from Noam Shazir in We See NLP. And the task here is that you have, you train a language model on Wikipedia articles, and then you take out the article on Abraham Lincoln as a held out test validation set. So the goal here is to be able to, at test time, reconstruct the article of Abraham Lincoln by piecing together what the model can find out from other articles. So this is strictly a task of interpolation. And if you have a model trained with 33 million parameters, you can construct an article, but it doesn't make any sense. Abraham Lincoln was an American voodoo activist, former alcoholic. It's just nonsense. You scale that up to 97 million parameters and all the syntax errors start to iron out. But at the same time, the article content doesn't actually make much sense. You scale that to 320 million parameters and you start to get some formatting correct, the dates look roughly correct, but the dates aren't actually accurate. And all of the content that's inside semantics aren't actually accurate either. Scale that up to 1.1 billion and you can start to actually see an article appear that looks like as if it was written by maybe a junior high student. And once you scale this up to 5 billion parameters, boom, you have actually an article that looks like it could actually be an article of Abraham Lincoln on Wikipedia. So the interesting thing to see through language models is essentially in language space, one hypothesis that we have is somewhere in the space of interpolation, you might be able to find robot planning, some notion of visual common sense, and maybe a little bit of robot programming as well. And I think some of the works that are coming out from our group is sort of touching on different various points from this angle. So today we're going to be doing a live demo of robot planning Palm Saycan. Some of the other works, for example, visual common sense focuses more on if you're in a living room, what are typical objects that you would see, activities that you would normally do, and using that to improve recognition accuracy. You also have robot programming, which is realizing that you can give a system a bunch of APIs that can operate off of and have it be able to chain them together, given natural language instructions in order to do robotic tasks. So with robot planning, Palm Saycan, just to give a little bit of context as well, take your favorite public off-the-shelf language model, and you can, one of the interesting things is that if you say steps for a mobile robot to fetch a Coke can from the refrigerator in the kitchen, what's exciting is that you get a bunch of lists of steps, and these lists of steps seem like you might be able to find some way in which you want to ground them onto a robot system. Locate the refrigerator in the kitchen, use sensors to detect the presence of a Coke can, move the robot towards the refrigerator, etc. So one question that Palm Saycan really looks at is how can we take the outputs, the planning outputs from these large language models and be able to take them onto a real system and make it actually do the task at hand. With that, I think that I'll pass the baton over to Fei Xia, and we're going to do a live demo of Palm Seikan. Just to give some context here, I have a chat window that we've set up where we're directly connected to a robot that's on the other side. Fei, if you can do a thumbs up or something to let me know that things are okay.
Yeah.
Okay,
can
perfect.
you hear me?
Yes,
Yeah.
I can hear you.
Everything
All
go.
right. So the first thing that we're going to do is have a call sign.
Hello, Meta 107.
This is just a handshake exchange to make sure that we have a direct connection or a direct line to the robot. And then we're going to go ahead and type in a command. We're going to tell the robot what to do. So we can say roses are red, violets are blue. Bring me the rice chips from the drawer and a napkin too. So this will go ahead and send the command to Palm. Palm will generate a list of steps, and Seikan will take it from there to ground it onto actual robot policies that it can execute. Let's see if the robot responds.
So here I want to show that there are two views. The top one you're seeing is more like a panoramic view of what is happening in the kitchen. It's a real kitchen in the Google building. And there is a bottom left, there's another view, which is a close-up view of the robot. So we will show this, we will show the robot manipulation in that view.
So the MKBot says, on my way, I will bring the rice chips from the drawer to your desk and a napkin. I am going to the drawers. We have Tomas, our camera guy, following the robot. I will be able to hopefully get a close-up view of the robot in action.
Andy, it seems that the close-up camera is higher quality. So if you can pin that, it will be even better.
Sounds good. So this is running a visuomotor policy that is closed loop. It is spitting out actions at 3 Hertz, and it's taking in images as input and visuomotor control commands as output. And part of what Palm Seikan does is that on the one hand, you have a decoder architecture from Palm Seikan that's outputting probabilities out of a list of known skills that the robot can execute. Those are the probabilities at which the decoder feels that it should be a reasonable next step to execute. And then on the other side, you have the affordances of the robot policies in which you want to essentially, based on the current observations, how likely you can actually execute the skill at hand. You multiply those probabilities together, and ultimately you can be able to re-rank which steps are actually executable on the system. So here, the robot is outputting each of the individual steps that are also being executed. I'm going to the drawers. I am going to open the drawers. I am going to take the rice chips out the drawer, and I'm going to close the drawers. So these are individual steps coming out of the plan, and each of them are, oh. Oh no.
So what happened is a robot finger falls off, and we did a live repair and attached the finger back up. The finger falling off is a safety mechanism that we built into the system, so it doesn't exert too much force. So like we have a system, we have safety system in both the software and the hardware level. Another thing that I want to highlight and also answering question from the audience is that this is an unknown kitchen for the manipulation policy. So the manipulation policy is trained in robotic classroom and also trained in collect some data in the other kitchen. But manipulation policy has never seen this kitchen before.
So it's purely generalization. It has never seen this drawer before. So the fact that it can open the drawer is quite amazing. Regarding how does it know the position of the drawer? So this one is actually, we label important locations of the environments and then put it in the planning algorithm. So the planning algorithm knows where to go. That is to answer the audience question. Here, the robot is grasping the napkin, which arguably is a quite difficult problem, manipulating deformable objects, which is quite challenging for traditional robotics. But here, the underlying manipulation policy can do that. I also encourage everyone to take a look at our robotic transformer RT1 release. So that is also what powering this demo and our SayCan runtime. Back to you, Andy.
Cool, thanks, Faye. I think one of my favorite parts of this as well is that a lot of the capacity to be able to react to the different visual nuances and all of that is baked into the policies themselves as well. And so, as Faye mentioned, this is a new drawer. The texture of the drawer is wooden, so that's also textures that the system hasn't seen before during training time, and it's sort of capable of adapting that on the fly, and I'm really excited about that. It has a little basket on the side, so it's putting everything there and bringing it over to Faye.
Yeah, basically the robot delivers here and we are able to receive it. Receive it from the robot. Robot says, it's a pleasure assisting you, and it's finished.
Yay, nice. Thank you, Faye. We do have time to try one more. Faye, do you, maybe we can try the call sign again?
Give me 1 second. I need to wait until the lights turn green. So maybe maybe a little bit.
That sounds good. Cool. So as the screen is turning on green, I just wanted to show a couple of visuals of the actual paper itself. You have a Palm going in and doing the decoding and then being able to compute out of the list of potential skills that you can execute on the robot, providing a score for how likely it thinks that that would be the next step. And this is a constrained list, so effectively, and Brian puts it very well, which is speaking the language of the robot. And then you have the affordance, task affordances with value functions on the right side. So you're combining the two scores together to be able to decide that ultimately, although that maybe a task is to, the next good step would be pick up the apple, but because you don't see an apple in the scene, then maybe the next best step is to find an apple. So that's how it does this reselection criteria. Code is available. So if y'all go onto the SayCan website and you go to the bottom there, you'll be able to find open source code that you can download. There are collabs everywhere, and there are also variants and buildups, follow-ups on this code base as well that you can download as well. So you can click the tabletop SayCan here. And just to give you an idea of what that should look like, you'll be able to see, for example, asking a language model how to output the steps, and once it's given those steps, you have affordance values coming in from clipboard, Mohit's work, and being able to string those commands together to be able to do complex pick and place tasks on a tabletop setting. We also have a follow-up work called Inner Monologue, which is trying to incorporate more closed loop feedback. The idea being that you can have language feedback come in to the planner so that you can have the planner replan based on what happened actually as a result. And that language feedback could come from a visual language model, or that could come from humans as well. So we're very excited about this as well, and showing that you can artificially inject noise in your policies so that if the policy struggles, you can still be able to recover over time. We also have code as we also have code as policies as well, which is looking at SayCan generates a list of steps, for example, and code as policies expands that to the full expression of code. So if you have things like wait until something, then you could write a while loop, for example, to handle that case. There are also open source code that's available here for folks to play with and download, and also a Hugging Face demo as well. Cool. Looks like the robot is
Yes,
ready.
it is ready.
Perfect. And we can do one more.
Yes, I think we can do one more.
Okay. Hello, Meta 107. What's interesting about large language models is that you have the capacity to speak to a robot in more figurative terms. For example, you have your preferences and you want to express those to the system, you can. So for example, we could say something like, I do not like caffeinated soda. Can you bring something else to drink from the table to me at my desk? And I think that from the perspective of bringing robots to have more utility in the real world, I think this opens up lots of doors for us in the sense that we can be able to communicate things, and maybe the way in which we communicate is roughly figurative and not exactly very precise down to the detail, but ideally we can use the capacity of a large language model to help us fill in the gaps.
Is this latency because of the language model, or is it just latency with the communication?
It is with the language model, yeah.
So you seem to be quite careful to provide quite a lot of context in that when you're talking about like avoiding the necessity to be so specific. So could you have just said something like bring me something to drink without caffeine?
Oh yeah, I think
that would work fine. I mean, or is it a little bit what ways that you're trying to avoid turning the amount?
Yeah, I think that for the most part, you can say things in different ways, and that's part of what language models can also bring to the table, and it still captures the same semantic meaning. Specifically for language models, though, I think that depending on the data distribution that they trained on, there are particular mistakes that they might make that are particular to the language model, and I think that we're hoping that sort of we can ride the scale of progress in the sense that as people come up with better language models over time, those things will start to iron out.
I missed this. Which language model are you using behind this?
This one is using Palm, which is coming from Google. It has.
It's a bit old.
Oh, it's not too old. It actually just recently came out. It's the largest large language model that we have, which is trained with 540 billion parameters.
Oh.
Yeah, I guess, so like, I don't know, one of the reasons why we're so explicit here is because this chat is actually like, if you aren't explicit, it will ask follow-up questions. So if you, yeah, so if you, yeah, well, yeah, if we had asked like, I'm thirsty, it'll say, well, what do you want to drink? I have these things. And it will like keep disambiguating. So I think just to like, just short circuit that part, we give it like these more clear queries, but it's the bot actually running a large language model first for dialogue and then for typing. It looks like it's in some sort of.
Yeah, yeah. In this case, it seems it doesn't work. So Andy, why don't you type in stop and try something else? Yes. So in this case, I think it end up in a loop. I'm going to the table, so this one doesn't work. But we can definitely try something else.
Okay. Should I run the call sign again?
Just 1 second, maybe in like 30 seconds, I will let you know. I also want to take a moment to answer the audience question, like for what the examples of the important locations you need to label of the scene. Can you give some example of that? So in this particular scene, by the way, it's ready now, Andy, so you can try something else.
Okay.
In this particular scene, we have like a close counter, far counter, trash can, drawer, like these are the important locations. So we need to let the robot know where these locations are. And also, we have some follow-up work. One is called NL map, which is open vocabulary scene representation. So with that type of representation, we no longer need to annotate these locations. Like the robot can just query it from your map, for example, and then it's a more flexible with the planning framework. Yes.
Cool.
Was this a failure that it didn't know where the table was, or is it a navigation failure?
I'm going to ask Faye that question. So Faye, was this a navigation failure or a planning failure? the getting stuck at I'm going to the table?
It's not a navigation failure, it's more a planning failure. So I think for this to work, you need to like let it know like what are on the table. Like maybe we haven't updated that, and so it doesn't know what is on the table. So what is on the table is a 7-Up, a Pepsi, and a Coke. So the correct answer would probably be Pepsi, but the robot doesn't have enough information to figure that out. Maybe it should ask a user in this case, which like in a monologue will be very useful in this case.
That makes sense. Cool. I'll ask one last one. Do we have a query that somebody wants to try? These are the objects that are on the table, something that folks will want to. We can say, I am thirsty, for example.
Ask it to eat the apple.
I think that we could say, bring me something healthy.
Say I'd like to eat an apple.
Don't bring me those jalapeno chips. You can't buy them in New Zealand. One thing on this about
Let's try that. Something healthy was your YouTube demo, right? Yeah, I think we know that works. Yeah. Bring in healthy and chips in other words still.
So if you ask something that you started with, what happens in this case?
I think because PalmSaycan has the fixed set of list of skills that it can execute, then it'll just constrain it to be one of those things. So it's going to try to reinterpret in terms of that.
But it will always be clear, or will it fail to reinterpret sometimes?
If it's uncertain enough, it's possible. So if some particular combination of the scene configuration makes it so that the affordance model is also confused, then there will be some confusion.
The highest probability ends up just being like something like that, and so it just cancels. But I guess one really nice thing is that it's all very fast when you just add in a new skill. So a skill could be like, I don't know how to do that. That probably ends up being the highest thing. But we don't have that. It's nice. It's interesting.
Nice. Yes. Yeah.
So earlier you said the scene information is known to the planner, right? But there's almost no way the planner knew there's jalapeno chips on that corner. It probably knew there's chips on the table. The table's big.
Yeah, so there's various different ways to approach that. So specifically with Saycan, you have a policy which is to find the jalapeno chips. And so it'll navigate around and try to find it. There are other versions where, for example, if you're building a map, you're explicitly putting where the object is inside of the map and providing that as context to the policy. Or, for example, if you're getting that from some other means by a visual language model, passing that context to the planner itself.
So in this case, it was probably just going around the table looking for the chips.
That's right.
Okay.
Yes. Thank you, Faye.
We can also take a moment to appreciate that we are doing this demo like across this hemisphere, and like Andy is operating the robot using a chat interface, communicating with the robot in natural language. I think this is really cool.
Absolutely. Very excited about that. And also thank you very much, Thomas, for giving us the best view of the robot. Cool. Great. So I think that a lot of the things that we're looking at, there are also limitations of language as being an information bottleneck. And these are things that people have pointed out over time as well. It loses spatial precision. It's highly distributionally multimodal. There's various different ways to say the same thing. Not as information rich as in-domain representations like images. And there's a question, is it only good for high level? What about control? And I think that also just to call out that language for robotics has been around for quite some time. And I think that these are all things that are the main questions that are still left unanswered. And I think that we do have some data points that are suggesting potential solutions for some of these areas, but I think much of it is still an open research problem. So I think that one thing is that scaling robot learning today is relatively speaking quite hard. In particular, for example, you can take your imitation learning algorithm with 50 expert demonstrations. You can do pick and place tasks, 500 expert demonstrations. You can start to do more combinatorial tasks like pushing objects around, 500 expert demos, and you can start doing more contact rich tasks like scooping particles and putting them into bowls. I think that in terms of how much data we can get in order to reach the caliber that large language models have, I think we still have somewhat of a ways to go. And in particular, because we're just in two very different regimes. With robot learning, we're stuck with the number of robots that we have and the time that we can spend with them. Whereas with language models, you can just spin up thousands of web crawlers and boom, you can collect data in parallel. To give an idea for how much data went into training Palm, there was 780 billion tokens with a 256,000 vocabulary, token vocabulary with a word embedding size of 18,432. So if you wanted to achieve the same level of data to train a language like a palm-sized robot data set, you would probably need about a fleet of, some napkin math suggests that you need a fleet of 100 robots collecting mostly diverse data for 24 years. But I do think that there are ways in which we can start to narrow this gap by thinking more ways about how we can find other sources of data like simulation or maybe YouTube, or also trying to improve data efficiency in ways that are as general as possible, but including some notion of prior knowledge. But I think another potential route to think more about in the coming years, I think, is also just directly using language models and language itself to help us potentially close the gap in terms of providing some more common sense to help us fill in the gaps. And I'm very excited about this direction in general. So just to conclude with two final thoughts, one of the things that I started this talk off with was an analogy, and this original analogy actually came from Tomás Perez from MIT. And this analogy is something that I've only come to appreciate more over time, which is that machine learning is a box. It's good at modeling points inside, but not very good outside. Whereas in robotics, we have a line. The number of problems in robotics stretches infinitely outwards in both directions. And along this line, you have multiple different problems. You can take a box and you can try to fit it on some part of the line, but there's always going to be that other problem that is an edge case that which you have to try to expand your box to cover. And I think that over time, this is challenging in the sense that it's kind of difficult to make the machine learning box try to fit the encompass of, or the entirety of the line. But I think that there is also a solution, which is to embrace compositionality in the sense that we have a bunch of small boxes, for example, in perception or control. And for each new problem on the line, try to find ways in which you can compose those boxes together to do the task at hand. And I think that this is essentially the story of infinite use of finite means. And I think that to do this, there's really just two steps. One is, how do you build those boxes? You can use deep learning, you can use reinforcement learning, or manual engineer it. And then the other question being, how do you compose them autonomously? And I think that you might think that, you know, compositionality is something that robotics has been focused on for a very long time. But I think that the key thing that has changed just in the past 2 years is the fact that these large language models are giving us the capacity to be able to do the composition autonomously. Previously, this was the biggest bottleneck. You needed a robot expert to be able to compose the boxes. But now we might be able to use language models as a way to put them together for us. So I think it is worth thinking a little bit about compositionality, yet again, to tackle the kind of generality that we're looking for in robotic applications. The second thought that I have is language as the glue for intelligent machines. In any robot system, we have perception, planning, and control. And it just so happens that, for example, in the computer vision community, people are also looking at ways in which you can ground things onto language, not just because that's the cool thing to do, but mostly because language is an inductive bias that vision people have found out works very well in terms of generalizing transferable representations. So for example, red pixels, red t-shirt, the concept red very much gets grounded to pixels that are of 255, 00. And I think that there was this blog post from our colleague Eric Jang that I really like as well. And in that blog post, he writes various different points to different pieces of literature to suggest that we have some reason to believe that the structure of language is also the structure of generalization. And he looks at different pieces of work, including the Sapir-Whorf hypothesis, which is that at least for humans, language seems to dictate cognition. So I think that if we think about towards grounding everything in language, each of our modules, we do have sort of this manifold of language that can help us define the scope of generalization. And in part, I really like this picture of whenever we have a control module or a vision module or even a tactile module, finding ways in which we can ground it onto language. And in part because language is the space in which we have the most data. So for the other modules for which we don't have a lot of data, we can at least ground them onto language and lean on language as a way to fill in the gaps. Cool. And with that, I'd like to thank all the collaborators. This demo here was powered by the work of many. So, and there are many folks who are involved in getting this demo up and running. So huge thank you to the folks that got this to work.
Yeah, thank you, Andy, for the live demo and the talk. I think this is the first time you had like a live demo with a robot virtually.
All right, so I'm Knuckle. As Mo just said, I'm an assistant professor at Arizona State. This work has been done in collaboration with lots of people from places like Brown, Georgia Tech, JHU, John Hopkins, and a whole bunch of other places like WITS in South Africa. So a lot of people have helped make this work happen. What I'm basically going to talk about is sample efficient learning for tasks that we want to teach our robots or agents. And the way that I think about these problems is by providing more structure in this problem. And also what's more fashionable nowadays is just to use pre-training with large language models, as has been stated previously. So previously, the way I've thought about this work is I collect some trajectories and natural language data and generate what I would call structure, symbols that you can plan over. So you can generate symbols that the robot can literally plan over. So you could just hand this to an RT planner and you learn symbols like these that you give to a planner that the planner would just plan to and execute them in sequence. Those symbols are relatively cheap to learn. You can learn them with about 70-ish demonstrations and you can get some generalization. So the trajectories that we're talking about are thousands of time steps long. And the generalization that we're talking about is the robot still managing to solve this problem in different corridors in the same building. Apart from that, I've looked at how people actually teach tasks to robots, whether people are capable of teaching abstractions to robots or not. And the thing that we have found is that people are generally not good at teaching these symbolic abstractions to robots. The reason why I think about these problems is because I spend a lot of my time using machine learning and reinforcement learning to learn abstractions so that I can hand them to a task and motion-based planner. And that's a lot of work. So I was wondering if people just know the solution to these types of problems and whether they could just hand a robot some abstraction that the robot could use. What we have found is that people are not good at this. And even if when they do teach abstractions to robots, they are not teaching the robot correctly. There is a mismatch between their understanding of the robot state space and the type of tasks that they need to teach the robot so that the robot can actually solve these tasks repeatedly. Apart from that, I've also looked at representation learning, where you think about what type of representation should an object have in 3D so that you can actually recognize this object and with partial view given some natural language command. In this talk, I would specifically talk about ways in which we can reduce sample complexity so that we can actually get to some way of interactively teaching robots. The issues that we'd face when doing such a thing is sample complexity. People don't have patience. We just can't give as many demonstrations to robots as robots would need. And the proposed solutions that I would have today is just giving structure by separating the language understanding problem from the policy solving problem that the agent itself has. So in the contents of the talk, first I'll talk about visual policy reuse for language grounding. Next, I'll talk about compositionality for language grounding. And then I'll just conclude and stop the talk. Great. Okay. So visual policy we use for language rounding. So previously, when I tried to solve the same problem of instruction following, I had to go and collect a lot of data on the robot. We had to do it at 5 a.m. when there are no students in the campus of Brown, because otherwise you just can't collect demonstrations of robots continuously. So the motivation for this work was basically to reuse policies that have been pre-trained. And one way that we thought about it was just to separate the policy learning problem from the language rounding problem. And we did this because there were already great neural policies for pick and place. For example, we already had the transporter network paper by then. So we knew about these policies that can actually pick and place objects. And so we thought about how to map language to these deep continuous policy representations. So our collaborators from GHU already had these deep policy representations where given a 3D representation, given a 3D scene that the robot observes on a tabletop, you could generate pixel-wise Q values for the agent to basically decide where to pick an object or where to place an object. And given those pixel-wise Q values, the robot would just take the highest Q value action by picking up the block that has the highest Q value. So this has no language input right now, but these are just pixel-wise Q values to perform picking and placing, given some sequence to the robot, like pick up the blue block and then pick up the green block. So we chose this domain specifically because it was a block arrangement task and it's a traffic planning domain, and we had robust pre-trained models for this. And we wanted to see how to map natural language to these continuous policy representations. And it required reusing learned policies. And what we specifically did was set up the problem in an interactive way where you can actually provide instructions to the robot one instruction at a time, where you say stack the blue block on the yellow block, and then the robot does that. And then the next command would be stack the red block on top of the blue block. So these are stepwise instructions for solving the problem of row making or column making. So there's tons of related work in this area, starting with Clipboard by Mohit over here, where Mohit has looked at using image and using mapping image-based representations to policy spaces directly using transporter networks. When we started working on this, the only related work that we knew of was the vision and image transformers that came out in 2021. So our work was specifically looking to learn a transformer model that had both image and language data on it from scratch, basically, to predict pixel masks to pick and place objects. And so we used two types of data sets. One, we created programmatically 3D generated data ourselves. Secondly, we ported the 2D Bloxwell data set from Jonathan Bisk over here onto a 3D simulator called Copella Sim, where we basically just stole all the natural language commands and just converted into a 3D data set. But then we could learn the policies on a realistic simulator before we ported those policies onto the robot. So you could actually say the Mercedes-Benz will move right until it's above the Twitter, and the robot would actually plan that stuff. So if you can see, there is a Mercedes-Benz logo and there's a Twitter logo, and in the resulting image, the Mercedes-Benz logo is above the Twitter logo. So our pipeline looked like this. We had an input image. We had both RGB and depth data. And we said stack the red block on the blue block. Now you'd have two separate heads on the network itself. First was the spot Q network, which basically predicts the pixel-wise Q values. There are lots of blocks to be picked over here if you were just making a simple row. So all the blocks that you could pick would be lit up, basically. But we specifically asked for the red block. And so we basically learned this transformer model, which would predict a patch-wise mask on which block should be picked. So when you say stack the red block, then the red block would get a patch, basically. It's basically like a mask prediction problem where you're predicting a mask over the right object to be picked up. And then we ground that mask to the object that's actually underneath that patch, underneath the mask that we just predicted. And then we basically do an element-wise multiplication, like a hot mark product, to basically realize which object actually needs to be picked up underneath that mask. The thing to note over here is that we have got two separate transformers, one for the picking problem and one for the placing problem. So when you say picking the picking up part, where you say pick up the red cube, is solved by the grass transformer, and the place transformer then puts out a location mask of where the object needs to be placed. And this will be important. The mask prediction itself, we used a simple binary cross entropy loss to predict which location should, where in a 16 by 16 grid, where should the mask actually, which mask actually is over the right object that is being referenced by the language command. And we added more structure using an auxiliary reconstruction loss, just so that we can predict the right block reconstructions, that this block has this ID. So this is just an auxiliary classification tasks of like red block, blue block, given the image of the block themselves. So our results in simulation, at that point in time, we could only compare against UNIT, which was a masking mechanism. So which is a UNIT is a cool paper which generates masks using low amounts of data. And what you can see is our transformer-based approach actually does better both in row making and stack making tasks. It predicts colors more accurately, and also it takes a small number of actions to actually get to the goal. Apart from that, because we trained all of the models themselves in simulation, we showed transfer onto the real robot using actual images.
Can we get that stuff?
I'm sorry?
Working stuff, please. Sorry to interrupt.
Sure.
There are working stuff in here.
No worries. So what I was talking about was we trained the models in simulation, but we actually had to show that we can transfer this onto the real robot. And the way we did this is that we actually collected actual image frames on the real robot. And what this plot is trying to show is that as you add more and more natural images onto our pipeline, the error rate goes down on the real robot. So there are efficiencies to adding actual images to the pipeline itself. Apart from that, we saw we have results that are on the BISC 2018 data set. We could actually solve those problems in simulation. And besides that, we were thinking about compositionality in these results, where we wanted to know whether our pipeline actually generates compositional results. So what we specifically mean by that is, let's say that I show you pick up the red and place in blue, and pick up the black and place in green. Can I now say pick up the red and place in green, even though that combination has never been seen before? And the reason why you would assume that this problem could be solved is because our grass transformer and our place transformers are different. So if the grass transformer has seen a grass happen somewhere on some color, then it could probably assume to, then it could probably always remember that you can grasp that color. And the place transformer can basically remember that this object has been placed previously. And so that kind of gives us this like compositionality result where you don't have that much loss of accuracy for unseen stacking problems and unseen row making problems. So the largest amount of loss that you can see is the unseen row making problems, where it's basically lost about 4% of accuracy, which is not that bad. And again, as I said, the compositionality itself is coming because it's basically built into the pipeline. So this is our video that we made where you can basically say stack the yellow block on the green block, and the robot does the right thing. It would have predicted the masks on all colors that would have been true would have been lit up by that thing. the highest Q value would have been picked. Again, because this is a visual motor control policy, it can actually recover from errors that it makes. So if there's a slip in the grasp, it's a visual motor control policy. It'll keep on going from that given state. Great. Cool. So now let's specifically talk about compositionality for language grounding. And this is a problem that I've been working on for a while. Previously, the way I thought about compositionality was by using parsers, where parsers would basically give you compositionality, and then you just ground the parser onto your visual frame of reference somehow. And for this, you need like object detectors. For this, you need a grammar specification, which is horrible to do. But you did get amazing results. You could get zero-shot results of picking up a red chair, even though a red chair as a concept was never seen together. And so we've been thinking about this problem for a while. Besides that, it's been also stated that neural networks are just struggle is the right word to generalize compositionally. What's very clear is that language is compositional. It's not just compositional in specifying object types, it's also compositional in specifying temporal specifications. Do this and then do that, that's also a compositional specification. And we have looked at that for LTL reasons and things like that. But what we do have are, we have these large language models that probably have some compositional information in them. And we have a series of papers on compositional policies in the reinforcement learning community. So we were just trying to think of how to use these large language models with compositional policies together. And this whole series of slides is about compositional policies that were developed by Gerard, Stephen, and Benjamin at WITS in South Africa. So what they did over here was basically, rather than just have a reward function that's based on state and actions, they also provided a goal specification. So you have another variable in the reward specification, which basically says which goal the robot's heading towards. And they decided to penalize the robot, or not the robot, the agent, if it enters a state that is another goal state than the goal state that it's actually targeting. So if you're asked to go towards a red thing and you went towards a blue thing, you would get a penalty. The penalty is basically the minimum reward that is present in your domain. And then they show that you can have, that you can provably compose these value functions together under a Boolean task specification. So it supports and compositions or compositions and not compositions. Rather than go through this map, I'm going to try to show this visually to you. So let's say you have two types of reward functions. One reward function is going to the left of the wall, to the left of the room, and another reward function goes to the bottom of the room. You can think of an and composition, a disjunction, an or composition really trivially. It's just the maximum reward that's possible in any given state. So in any given state, if you just pick the maximum reward, the max of the left going reward and the right going reward at any state, you'll just basically get a disjunction. To do a conjunction, it's harder. You have to pick the minimum of the two reward functions. And so the minimum of these two reward functions at all states would basically be 0, except over here, where the minimum between those two tasks is just that particular state. And finally, if you have negation, if you just say, don't go to the left room, the only thing that you have to remember is that this domain basically only has two tasks. So not going to the left side of the room doesn't mean that you can just stand around where you are. It means that you have to pick the other task to basically end the episode. So there is a way to specify that. It's basically the R min of the domain plus R max of the domain minus RL. If you do that, the math basically would end up so that the reward for the bottom would always be lit up. So using those compositional policies and a pre-trained T5 language model, because the T5 model was available, we thought that we could combine the compositional policies with the T5 model to generate compositional language rounding. The domain that we chose was the BBI domain by Maxime. So the domain itself has got objects that only have two characteristics. Like a key could be, so you have objects like keys, which could have different colors. So colors and shapes are basically the specification that you can specify in this domain. So you can say red key, blue ball, and things like that. So previously what we had done in this world was basically take the language command and translate it to an actual symbolic space. So all we could do is say something like pick up the red ball would go to pick up red, and then we would guess which operator it is, whether it's and or not. And then we'll spit out pick up ball, which is the second object type. And then we would just compose this two value functions together. This pick up red token and pick up ball token are completely symbolic. So it's basically like a translation problem. What we have done right now is we have come up with a neural modular value network, which can basically combine these two value functions, using soft attention. So what we're doing over here is we've got the pre-trained base value functions. And we've got the T5 model. The T5 model specifically does not know how to reweight the compositional value functions at all. What we do is we use soft attention to basically learn how to compose the value functions together by setting this problem up as a reinforcement learning problem. And to do that, we have to figure out a way to pass the gradient back all the way because we're basically sampling which compositional value functions are we operating under. As soon as you sample, you've broken your gradient backward pass. So we basically got a soft, a straight through estimator, which is from Zhang et al. 2016. And so we were able to pass the gradients back to our language network and to our compositional value functions. So this thing is completely end-to-end differentiable. And then we were able to show that if you do learn tasks compositionally, you do save on the number of learning steps that the agent has to perform. So one way to think about this is, so our base tasks themselves are using DQNs. So our tasks are learned using DQNs. The DQNs require about 1,000 steps of data in their buffer. So the orange line in all of those plots basically shows you the data that's been collected in the buffer. The actual learning of the agent starts after the buffer has been collected. And the tasks themselves are being taught from left to right. So the task on the left, which in this case is the blue box, is taught first. So you can see that blue box requires more number of steps in the world to learn. Green key requires fewer, and blue key, because it can predict where blue should be and the composition with key, it's able to predict blue key well. What's really cool is that it can do zero-shot solving of problems like yellow ball, a composition that it has never seen before, and gray box and gray key. So what we want to do next is we want to explore things like negation and temporal compositions. Like I want to say, don't go to the kitchen. There's fire over there or something like that, which takes into account like temporal problems, that temporal specifications that you can give to a robot, and negations that you can specify to a robot. Besides that, we want to work on realistic robotics domains to move this, because right now we're basically based in a simple grid world kind of setup. And we want to remove the dependence of the DQNs and basically put in continuous policy like PPO or TRPO or something instead of that. So in conclusion, I think about adding new concepts or tasks that are required for the robot. For this policy, reuse might be a promising direction. Compositionality itself helps us solve some of these problems with basically no new samples that are collected from the environment. We're still far from solving these problems in clutter and partial view, so there's still a lot of work to be done here. Thanks a lot.
Cool. We have some time for questions. There.
The question because that was.
Sure.
Why is compositionality such a hard problem? Like, I don't think it's like large language models solve it for you.
So I would say, so the question is, why is compositionality a hard problem? And I would say that the problem isn't generally on the language side, the problem is on the side of control. So one way to think about this is that like you can teach a robot to walk, and you can teach a robot how to, I don't know, juggle fast. If I suddenly ask a robot to walk fast, that's a problem that the robot can't really do because it doesn't really know how to translate. It doesn't really know how to decompose that fast isn't really something that's attached to juggling concretely in the policy space. So it's easier on the language side. It's much harder on the visual representation side and on the control side to basically decompose things.
Yeah. It's sort of a related question, and it's also related to this question of grounding on language. So the information that you just gave sort of suggests a lack of connection to a language or a lack of symbols in the thing doing the manipulation or the vision corresponding to the language. It doesn't necessarily suggest that the language is incapable of doing those calculations. So fundamental, I guess in some sense, the fundamental question is, do you think it's possible that a paper can be written about robotics saying that language is all you need? Right? So that in fact, all of this language data over constrains the problem with respect to even the manipulation data or the sensing data, so that you can infer those methods.
So are you saying that the language itself is constraining the control problem?
It says that maybe it's enough constraint in the language so that there's only one solution to one correct solution to the control problem, given all of the available language. Right, so that the only coherent interpretation of a scene, for example, is one which is coherent with all the scene descriptions and all the language that exists.
Right. So the question was basically, can language be used to constrain some sort of task solving that the robot is performing because language.
Exactly. You just have to show it sort of a bunch of samples from your sensor, and once there's enough to do that mapping, all the rest of it.
Right. I think that I believe that hypothesis that language could, in fact, like Andy's paper just shows that you can actually do that, or you can actually pick up value functions that are actually necessary to solve a particular task. The real problem is, how do you tell the language model that the chips are in the drawer, right? That still has to be specified from somewhere. Like there has to be another source of information that's actually telling you that. So there's still this problem with like partial observability, or like things that are right in front of you, like my gripper fell off and my robot's still trying to pick up this object, right? There's this embodiment question that's still missing there.
There's more contingent thing about the task that the robot's going to perform. That applies to us too. Right? There's nothing special for robots. We can't see into the drawers, and robot probably can.
Right. I'm not talking about that. I'm talking about this problem of we're still providing the agent more information than just. So all I'm saying is that the language model is not enough to provide those constraints. You almost need another like a spatial map like history. You need a map of the world that basically performs as a database to tell you what things are possible in this world. Does that?
The question I'm asking is whether that's true or not. It's something, but I think that it may not be true, even though everyone assumes it's true. And certainly for people who are fans of embodiment, believe as a matter of faith that it's true. I'm not sure it's true, given the amount of language
take the risk, but we can talk about this offline.
Sure. All right, cool. I think we're out of time, so we're going to move on to the panel and then thank Nicole again. So, next up, we have a panel. We apologize for not having more of the speakers on the panel. This is mostly folks who are in person. So if we're just showed up here, it's going to be in the panel.
Zoom just died. So
we also have Lara.
Yeah,
virtually.
Great, I can just dump those.
Should I move this?
Yeah, that's enough. I think it doesn't go any farther. But they can see the from all the way up. Also, that's actually not the camera broadcasting. It's not the yes.
And can we get her, Laura?
We spoke about that, but
Yeah, but can you hear us, Laura? Okay. And
are you able to hear me?
I guess.
Yeah, we can hear you.
All right, cool. All right, thanks, everybody. Thanks for the great talks. I think since not everybody gave a talk, I figured maybe we start with like really quick introductions. We just go down the line, but I'm Brian. I'm a research scientist at Google, and I work on planning and language and foundation models and all things like that.
I'm Jonathan. I'm an assistant professor at CMU, and I did my PhD in syntax and now work on vision and robotics. And so I'm sort of a hardcore language person who made a shift.
Hi, everyone. I'm Doris Asadi. I'm an assistant professor at Stanford. I don't really do language. For the longest, Noah Goodman really wanted me to like work in language. And finally, I'm doing a little bit of work around like this based on what language and robotics. Most of my work is in robot learning, human-robot interaction. We are trying to use language as a way of communicating, coordinating with humans. We're also interested in foundation models and learning from language, large language models for robotics. So that side of it is also interesting.
I'm Andy. I'm a research scientist at Google, and I'm generally interested in vision and language robotics, and we're very excited about taking robots into real world environments.
Hey, I'm Nakul Akogopalan. I'm an assistant professor at ASU. I generally work on hierarchical planning, language rounding, and reinforcement learning.
Laura?
Hey everyone, I'm Laryl. I'm an assistant professor at NYU. I work on robot learning in general, but more focused lately on imitation learning, learning from high dimensional observations, and trying to make things work in realistic environments.
Great.
Oh, and also I don't do a lot of work in language. Most of my work in language is to use language supervised vision models to help robots.
All right. I guess since so many people don't do work in language, maybe we'll start off with I kind of want to get everyone's impression on what are sort of the limitations you see with language. Like how far can we go if this is like the language and robotics workshop? What problems are sort of like outside our scope that maybe we can come up with ways to handle? But I guess what do you see are sort of fundamental challenges that we can't address?
This question for the non-language people or for the language people? Again, sorry, I didn't catch it.
For everybody, so.
Part of the reason that I was not that interested in language, like, was that when you're trying to use language for human-robot interaction, you're assuming that there is that modality for communication, collaboration, coordination, and the moment your robot asks you to do something and you speak back to it, it doesn't really like respond well to that. So it is pretty limited in terms of like a communication channel. And part of the reason is that it's often not very grounded, right? So because it is not very grounded in the real world, it's not a great like language. I don't want to do it. It's a no caring channel for coordination. So that was part of the reason that I wasn't using it, but I think with like all the advances that we are seeing and kind of like advances of like vision language models and trying to like ground these systems better, I think it could be a potential, it could be potentially a good like channel for coordination and communication. And we can also learn from it for other things, right? Like training like a robot foundation model in a similar way that have large language models.
Yeah, I think for language, one of the pictures that comes to mind is, for example, you're playing tennis and then your instructor says, as you're swinging your hand, make sure that you do it in a little bit more of a C shape. So there's kind of a disconnect, which is in terms of instructing a robot what to do, how do you connect language to that degree of control or fidelity? There's also a lot of common sense that's packed into that statement to make it a little bit of a C shape. How are you going to get a robot to be able to picture that and be able to do that kind of spatial coherence and to be able to execute the task? And as you swing and you have, for example, a tennis ball flying through the rain, and you have all of the particles of water flying off of it, and as it rolls through, just how do you model and even describe that in language? I think there's still a lot of open questions. So I think language has its limits in terms of what kind of, there are other modalities that people work off of, and I think how you can exactly connect that to language is still an open question.
Yeah, I'll just piggyback on both of those things. Dialogue is just inherently challenging, especially visual, especially grounded dialogue. Well, we don't have enough like data sets basically like teach, except like on the real robot, where the robot is actually trying to pick up an object and failing, and then still managing to try to pick up the object. That sort of stuff is just inherently hard to do because we don't have good models of people. We don't know how to collect this type of data where you basically interact with the person to teach things to the robot. The other is this dilemma between like the high level state space and the low level state space of the robot, right? The low level state space is where all the control stuff is living. If I want to say to the robot, do this faster, that's a low level control specification. We basically know how to map language to task and motion planning based problems, where I can say, put this cup on top of the table, which is a task and motion planning based problem because you're going and manipulating the cup and then you're placing it on top of the table. We really don't have a good handle of actually manipulating low-level things on the robot using language, giving low-level feedback, do this faster, slower. And do this faster, slower is not just, it's not like, oh, you go and solve the adverb problem and then come back to me. How do you solve the adverb problem in a generalizable way? And then how do you get the robot to understand that there are so many things like adverbs and prepositions? Language is just messed up.
Yeah, it is. You go ahead, go for it. Go for it. Were you gonna start?
Yeah, Laura, you go ahead.
All right. Yeah. So I think I agree with everyone over here. I think a sort of maybe like a different viewpoint over here is that I think language is very high in the stack of human intelligence, right? Like if you look back, if you look at our ancestors maybe 200,000 years ago, the language they had was probably very, very primitive compared to the language we have now. And so I think if you think about robots of this age, it's no way close to the intelligence stack at which we would need language. At least that's how I see it, right? So once we do have robots which can, effectively or like intricately interact with the environment, I do see how language can help in sort of stitching those behaviors and, trying to communicate what to do. But I think in terms of a priority as a roboticist, I feel like we still do not know, for instance, how to grasp objects well, right? There are still so many papers trying to figure out how to grasp object 99 out of 100 times, right? And so I think maybe we should first try to figure out solutions for that, and then stitch together these behaviors using language.
I'm trying to figure out if I'm like being adversarial or if I'm gonna like So I feel like I'm in this argument very regularly. So like I was telling somebody like I'm limiting the number of conferences I'm going to per year. So I did my one NLP conference, my one vision conference, and now I have one robotics conference. And in each one of those, I have to argue why you do or don't want language. And so I have to decide which hat I'm wearing right now. On the one hand, language is meaningless. That's kind of the problem with language. There's no inherent metric space. It's complete, total social construct garbage, right? And we know this because if I stop using the set of phonemes that we've all agreed to in this room, as like what's the point, right? Like I can just like there was semantics conveyed to maybe somebody in this room, but like basically nobody else, right? And that's because language has no meaning. It borrows all of its meaning from the world model that you built and so forth. So that would argue basically an extension of the same point, like we got to build ourselves up. But there's this flip argument, which is that the vast majority of the knowledge that you've acquired in your lifetime, you acquire through language. So almost everything you only know because it was built by language on language. And so now the question is sort of like, well, how far down does that go? But conversely, how high up in abstraction do I go from the other direction? And where do the two meet? And I have no answers to any of it. But that is my sort of split the middle comment from both directions.
Yeah, I don't know where to go with it. I guess one of the key parts that we're talking about, we haven't solved grasping, say, but clearly there is some level where language seems to work pretty well. So I guess I'd be interested in hearing where you guys think sort of language should live on the stack. What is like the right level of abstraction for the robotics problems that we go and face? Clearly, there's certain ones that have different challenges, and some are really interaction based, and really, you have to understand the environment. But really, like, how should we go about determining where that line is? Should we choose it? Should we learn it? Yeah, I don't know. I'd be interested in general thoughts on that.
Fine. Okay, so I guess one comment is that I do think that, and this goes back to your adverbs example, I do think that language basically permeates everything in the sense that we have, like, it needs to be present all throughout all of motion planning. That doesn't mean that there isn't motion planning without language, but it does mean that language could condition or change everything about your entire play. And so that's what I think makes this so hard, is that the answer to your question, I think from my perspective, is everywhere and nowhere all at the same time. And so you need to make sure that there's this way that you can expose those primitives so that they can be modified or informed. And so I think we're going to just sort of have this process of balancing, maybe sort of back and forth for a while we sort of figure out where and how to do that. I don't know.
Yeah, so to me, it feels like language is a good way of like mention, a way of like referring to things, and for a robot to actually do something well. I don't know, I have a hard time like thinking like language is like absolutely needed, right? Like if you don't know how to do grasping, right? Like we could kind of like figure out how to do grasping like with imitation data or with other types of data, and we can refer to it as like whatever we want, right? Like blah, like it doesn't need to like actually like say, oh, that is grasping, right? And the only reason that we have a way of referring to it is it's like easier for us humans to like refer to that behavior as grasping. So it feels like language is super useful for human learning, right? Like we use it for human learning. For anything we have learned, we have probably like have a way of referring to it with language. But that's because like our own like suboptimalities of like having like a nice way of like referring to like C shape, like do this in a C shape, because that kind of like helps us to focus on that particular behavior and what does C shape mean, and that has particular meaning to us. That is why we can like do that behavior in like a C shape way. But I don't think a robot needs to like do that motion in a C shape way. Like maybe I have other ways of like teaching a robot to do that task without using any language. I think a language is useful if you are thinking about interaction with humans. And then people are lazy, so they don't want to like specify that as like left, down, right. You want to refer to that as C shape, and that's again like a convention, a high level abstraction that makes it easier for us to actually communicate with a robot. So I think it's useful for that, but
I argue slightly. So I think, so I totally get that argument. I think that there's another context though, which is that, what if I am in a situation where exploration is so expensive that I can't let the agent try to do that? So for example, I've got some very fragile thing. And so I can't let you I can't risk you trying to figure out how to do that grasp. And so therefore I need some mechanism for communicating that directly. So I think you might argue, well, then maybe I have some recording of me, like a video of me having grasped it previously, and you could learn from that. But that's a very sort of information dense and sort of expensive way to convey that information. So yeah.
So in some sense, that is getting at like somewhat like abstractions like being useful for exploration, but abstractions don't need to be language, right? Like it could be like skill like X, and Y, right? And I could use skill X, Y like as part of my grasping strategy because I don't want to explore everywhere in the same space.
Yeah.
And that's I completely agree that that would be a useful thing, but it just doesn't need to be like what we call as natural language.
Can I take that? Okay, so first of all, I agree that robots don't need language. It would be stupid to think that they do, because I have a dog. I could whistle and tell my dog what to do, and my dog can do task and motion blocking. I've seen him do it. You don't have to worry about this. So yeah, like you don't need robots to understand language at all if the robots are working by themselves. But I don't think that I want robots that work on themselves, because we already have companies that have figured out how to attach bolts to cars, right? I want a robot that can work with a nurse. And if I want a robot that can work with a nurse, my nurse is not going to sit around trying to figure out how to program this robot. That's not her job. So in some ways, I need language understanding just for the sake of working with people. So that to me is the most important factor. And apart from that, like where does language sit? It's like everywhere, as you said. It's kind of weird because Stephanie would give this example. She would say there's a speck of dust problem. She'd say that, okay, there is a speck of dust on that table, pick it up. Right now, I did not know there was a speck of dust in that table until she said that. And now I would go and look for it. And so it's almost like in my visual field, I suddenly have to search for the speck of dust and then clean it up. And I did not even know about it. I hadn't thought about it, but then I could refocus it based on language. So I could like change my visual field of reference. It works on your action space. It's just very powerful as a specifying mechanism. And we don't quite know how, where in the stack would you put it? You can't just put it up in the top. You can't just put it up in the bottom. It needs to have some sort of conditioning mechanism.
Yeah, I agree with all these points here, particularly on the role of language for human robot communication and interaction and being able to communicate. I think my opinion of language has shifted quite a lot just over the past couple months in the role of how much you can do with it. And I think that part of it is with language, one particular aspect of it too is code, and code being a part of language as well. And that kind of struck me as a wild card because during the summer, Jackie, who had worked with us at Google, was playing around with code writing language models. And one day he was showing up and saying, hey, guess what? These language models, they can write SciPy code and NumPy code. And they can do all of these arithmetic and complex function callings. You can compute the convex hull of things that you see. And it's like blowing my mind in terms of the amount of expression that could exist, even as code as a medium, which is supposedly just a subset of language, but the power of it is quite substantial. And so I think like all the examples that we've given in terms of style commands, things like doing things faster, doing things slower, is you could actually get a language model to say set velocity and be able to set and modulate those commands. And so the feeling that I have about language and its scope just feels like it's expanding over time, and I feel quite optimistic about what's going to happen in the next couple of years in terms of more exploration on what language can express. I think in terms of specifically on large language models, they've also read your robotics textbooks too. And so you can actually ask them to write your PID control and impedance controllers. And that was absolutely mind-blowing to me. I think the question though is that you still can't quite modulate those gains to a particular task. And I think there are still somewhat like open questions of how much low-level common sense and intuition you can actually express with these models. But I think that it's just, I'm fairly optimistic about just how much we can express with language.
CoRL, any thoughts?
Yes, so I think there have been a few thoughts on using language as a medium of specification, right? So you can use language for as sort of an interface between humans specifying what a robot should do. But I feel like there is a very clear and obvious limitation of this, right? Because in language, we cannot express how much torque to apply on our joints when we are making, like, 5.5 newtons of contact force with an object, right? So I think the sort of view that language is somehow magically going to come in and try to solve these sort of really hard manipulation problems is, I mean, it could do it, but I'm just not seeing what the steps for that process is. I think we still, like, if we still don't have a good model for how to grasp or to push objects, even if you specify it, like, even if the robot knows that it needs to, hold a screwdriver and like screw or to tighten a bolt, just by knowing that it's not going to actually be able to do it if it's not able to figure out how to grasp the object and bring it to the point and actually apply force and turn its hand. So yeah, I think it seems sort of clear that it can be used as a specification tool, but it's really not clear to me if it can actually solve what is missing in robotics right now.
Yeah, thanks. I guess first I'll open it up to the crowd and see if there's any questions. Yeah,
I would love to ask a question. That's really
I'll just repeat it in once you.
Yeah, okay, great, interesting. So I was wondering, so the language models, I see they're really more like a reasoning, or they extract a lot of stuff from language, and they have sort of reasoning capabilities and common sense. But in humans, they are totally tightly coupled to the embodiment, and that's why they make the human can make all the sense out of it. And what you said, that sort of whatever we build later up is always grounded in these experiences. And I think our language models, they completely lack that, right? They have only the mind model and no grounding. And my question is, how do you see a way to ground them, really, like using them as we have trained them now, but couple them to the robotic system to ground them? And what do you think, how far you can ground them until they suddenly have this effect that everything else suddenly makes sense, right? So how much do we need to ground until everything they say is sort of clear?
Yeah, so the question is basically, given the capabilities of language models that we have right now, how should we go about grounding them in interaction in the world, in their embodiment? And basically, how far up the stack do we have to go to be able to ground them effectively and get everything out of them that we, dream?
And solve it.
Yeah, and solve AI.
Yeah.
I killed it.
It's gonna pass this.
Yeah, I think what's exciting to me is that with language models, from both the things that they generate to even the input spaces that through backpropagation and gradients, they've managed to construct word embeddings that you can use. And something that's interesting to see is other work in computer vision and NLP making use of that word embedding. So something specific is that through learning autographically trying to complete all of these text corpuses that you find online on the internet, you construct this word embedding, and on this word embedding, there's this work called textual inversion, where you can, in this word embedding, find continuous points inside of that word embedding to represent concepts that you can't necessarily express in words. And that was a data point for me, which is that you have this grounding, you have this manifold by which you define language. And in that manifold, there exist points by which you can, for example, train encoders to map some particular texture, like a Louis Vuitton bag texture, map it to that continuous embedding space and pass that to a text to image model to generate a car made of that pattern, or some other doll made of that pattern, which is absolutely mind-blowing to me. So I think that the way in which we eventually potentially approach mapping more things that we cannot express in language, maybe taking an approach like that, where we have this language space that we've constructed through training on internet text data, and then finding ways in which we can take concepts that are, for example, from a tactile sensor and still mapping it onto that learning vector space. Not necessarily being able to express it fully in words, but at least being able to map it onto that space. It'll be useful. I think that has been a compelling data point for me. Whether or not that will actually solve AGI, I don't know.
But the question is, where do we get that data from? So, right, the language models, we have them because we have the internet and all the data, right? Otherwise, we couldn't have them.
Yeah.
And so, and the cool thing there is they work because of this autoregressive or like self-supervised learning. You don't have labels for this. I'm wondering, is there a way we can get the grounding without the labels? I would like to essentially have a robot playing around with the language models, and it's sort of language models that tells the robot, you're by the way doing this. You're by the way doing this. And then the robot can essentially learn what it was actually doing. And then sort of, it doesn't really, I think, work yet in the way what we have, but.
I think that's a great point. So specifically, the textual inversion work uses self-consistency, where the input space and the output space is the same, and then making sure that those are the same as the way that provides free supervision to find it that way. Space. So I think that, for example, if you learn some tactile signature and you have a couple of different ways to describe it, or being able to use that same particular embedding space and being able to output a reconstruction of the tactile signature. Maybe there are ways in which a robot can just through self-play still be able to grab the language.
Yeah, and just one point that I want to add to that. Yeah, so it would be interesting to also like do generation here, right? So like, for example, if you have that mapping from language to sort of behavior, then if you operate in the language embedding space, right, like, and actually like try out like other types of, like there was a paper, for example, that was looking at like RGB colors and like generating like the name for each one of these colors. So if you have seen like all shades of blue and the RGB colors corresponding to them, now you could potentially like generate like all shades of red, like the names corresponding to them. So you could actually like operate in the embedding space of language and in the generation of data that you haven't seen before, like in the tactile space, for example, or in other types of like modalities. Like as long as we have some data that are similar.
Yeah, I think the example that I typically use for why this is interesting and hard is a table setting. So I think that there's really nice examples of, like, for instance, if I do self-play, I'm going to learn how drawers work. I'm going to learn a bunch of basic sort of kinematics of the world or whatever. And that those are concepts that do have terms. And so now I've built that concept sort of alinguistically, non-linguistically, and I'm now going to learn the sort of alignments and stuff like this. And there's some very cool work, for instance, in like doing machine translation through images or stuff like this, which sort of relies on similar kinds of consistency things where it's like, I don't know how to translate from this language to that language, but I do have maybe visual groundings in each side, then I can use this interlingua from the vision to sort of connect these terms. So there's a sort of a similar thing here, which is like, how do I learn anchors that allow me to connect these concepts? The reason I bring up a table setting is because that's one of my, like, it doesn't matter how much self-play I do, I would never know that there was any significance to putting the knife and the fork and the spoon and stuff like this in a specific arrangement, because it's just a social construct, right? And it's a social construct of a specific culture and so forth, right? And so we then have this kind of, we don't have an ontology of these, but I think as you sort of move around the built world, you quickly can start to enumerate this set of things where there's no reason that a self-play, it's like, I do need to know motion plans and task plans and stuff like this to do these things, but there's no reason I would ever learn them by myself. I would need an instructor sort of to be present, to be making these linkages for me. And I would love to know sort of when and where that's most sort of effective. And I don't have an answer for it, but I do sort of like look for them sort of as we wander around, sort of like, you know, kind of culturally, all the places that I've made an assumption that are like sort of not, you know, that don't hold when you change. Yeah.
Laura, any thoughts?
Yeah, you
I mean, the way I would like to use large language models is somewhere where you can actually generate reasonable responses from the agent itself. So I would think of using language models in a dialogue setting and grounded dialogue, but that still means that I need interaction data with humans in some ways. And that would go back to that kind of like self-play kind of thing where like the agent can't just play with itself, the agent would have to play with the human so that it has some sort of consistent understanding of what this object is and how it's handled. With respect to a person, because our embodiments are mostly learned by us, but now we're asking this robot that's basically like an alien being to match its embodiment to ours. And that data needs to come from a human somehow.
Right, making an sort of orthogonal but kind of related. Sorry, I'm realizing that one of the things that maybe is worth stating in this discussion is that there's like a difference between the scientific question of where does meaning come from and how do we build this eventual system, and should you use large language models? Yeah, just use, of course, use them. Like, you know, like there's a ton of them, they're online, they're very easy to use, go download them, they're great API and stuff like this. I think it's an issue of sort of understanding there's some interesting questions about the limitations that are there, right? And so let's just pretend that there's no reasoning going on at all in the language model. We can argue as to whether or not there is or not, and it's just the most sophisticated large-scale nearest neighbors model that has ever been built. So you have an insane amount of human written text, and you now have a very efficient way to query for a nearest neighbor. That's an amazing resource. Just use that, right? It's every instruction, it's every recipe, it's every, you know, like whatever, those are clearly going to be very useful, right? But what we've been, I think, discussing right now, I just sort of want to separate slightly as like this philosophical question about like, oh, well, is this sort of a weird modern incarnation of the Chinese room experiments and like where the robot isn't actually understanding and like, which is, I love these questions, but I just sort of want to separate those for a second.
Any questions? Yeah.
Yeah, I'm curious, could you guys comment on like what would be an ideal data set that you guys don't have yet but would love to have? Let's say, you know, let's say you 100x the amount of like research budget that you could, you know, that you currently have. Like how would that data set look like, and what would that data set do?
Yeah, so the question is, what would your ideal data set look like, particularly a massive one?
So there's a related question that I get asked somewhat regularly, which I have an immediate answer for it, but it's not quite the same, which is basically, if this massive research budget and you were like sort of allowed to do whatever you want, what I would do is I would probably try to get whatever your favorite mobile manipulator household robot into literally as many homes as possible, in the same way that open source and like Raspberry Pis and stuff like this have been this massive boon where we've sort of crowdsourced the kind of knowledge and the hacking and the sort of data that's accessible. We have this problem, which is that there's no amount of robot data that any of us can ever collect that will be comparable to that. And so what I really want is just like very low cost, very, you know, capable robots. And then I think that means that all of a sudden, like, we'll just start to get that data sort of almost for free, because like people will like, you know, maker spaces will be like, hey, I want to build like my favorite sci-fi character, and this robot platform is at the base of it or something like this. And so like, I'm now seeing people at Comic-Con in like a totally different like perceptual space that I would have ever seen before, or something like this. And they built out libraries accordingly. So I think that's like not actually the answer to your question, but that's like the piece that I sort of wish that we had.
So maybe adding on that, I think if we can standardize the robot across labs, it will also be a really great way of sharing data, right? And so it's like instead of every paper where I have to, you know, recollect so much of data on my robot, I can just use all of your data, right? I think that really scales well. It scales well in vision, scales well in language. And if you did have a lot of budget, I would totally be for this. So yeah, if anyone has an infinite budget and they want to keep on spending it, please let me know.
Yes, I agree with everything that's, and I totally agree with like trying to like get robots and like multiple, like a lot of like hopes to get like diversity of like data. One other thing just to add is in addition to, I would need a lot of like robot data, multimodal, like that's what we really need like in this field. But one other thing that I think would be helpful is having some measure of like data quality, which we don't really like have today. So like, do I want the same like picking up type of behavior, like same over and over, like a lot of that, or do I want like diversity of data? And what does diversity actually mean? So I feel like, yeah, like one other thing that's missing is like good measures of like what is good quality data. And I want that in addition to that data.
Yeah, I think I agree with the sentiment here, which is that we want robots out there collecting lots of diverse data out in the world. And I think that if I'm going to take a little bit of a stance that's a little bit different from, in academic labs and deciding that all robots in the academic lab should be the same, because I think that still the caliber of that data might not match the amount of, or like the caliber of data that just comes from, for example, scouring the internet and being able to take casual conversations on Reddit and being able to have activity with this. I think what we can do is think about the robots that are already useful today in industry. Particularly what I would do is walk into an automation trade show. They have robots everywhere, thousands of them working all across the globe, and asking them to basically collect their data and be able to ground them onto language, for example, or some common API that we can all use. Because these robots are already doing useful things in the real world, it's just that nobody wants to share the data. And so if you talk to thousands of automation companies that are already collecting data, they have all the sensors as well, even the most expensive ones like tactile sensing and force sensing. All of these are incredibly expensive, but if we can get that data, then we can potentially train a foundation model. So I think I would funnel that money towards potentially the lawyers.
Yeah, I think I agree with most of what has been said. Like also talked about multimodal data, and I think that the multimodality is really important. It also has to be interactive, where you can actually, where you actually get data, the robot actually interacting with people around it and not just functioning on its own. And I actually disagree. I think that there should be different types of robots. Basically, if you have a car, that's basically a robot, and then you also need one. And then you have a drone, that's also a robot, and then you have got your mobile manipulators, they're also robots. And I think that it's interesting to have those different types of platforms, and then you combine their language together. Sorry, not their language, but combine the representations together to get something that is more complete, more than the sum of their parts, basically, rather than just a single type of platform that does the same thing over and over again.
Just one other use of that money would also seem to real to sim. Like I think like simulation can play a huge role if you have like better simulators and actually like would be able to like collect good data and generate good data in simulation. They're just not that good right now. So like having a good way of like improving simulation, I think would also be a good use.
Good. Are we since we done at 6 and that Moby's on the edge of his I think I guess we can probably wrap up there then and let people go. Thanks so much. We have about 5 minutes of statement left. Please don't leave. Yes. It's 5 minutes. Closing remarks.
Like quite some time.
Oh.
Okay, we'll do a quick. All right. Yeah. We still quick closing remarks. You want to do the walk first or walk first? Yeah. Okay. Yeah. Can all the organizers come up?
Brian. Can you also maybe like get the picture to them?
Patricia is, maybe she can. Yeah. So first, we'll do this.
Great. Thanks to all of the speakers today, and also all of the submitted papers. I think the finalists were the talks you heard today, and I think it was a very hard decision at the end. But drum roll. Congratulations to Clip Fields, weekly supervised semantic fields for robotic memory, and with Nur Mohammed, Mahi Shafulia, Chris Paxton, Laurel Pinto, Sumit Chintada, and Arthur Islam. Congrats, and well, very well deserved.
Conveniently, we have Laurel on the slide, so.
Yeah.
Yeah, okay, he's fine.
Wonderful. Congrats, guys.
Okay, well, great. You should go first.
Yeah.
Those who don't know, on the ClipField's work, once it worked inside simulation, it transferred to real in like a week or two, right before the deadline. Maybe Mahi can comment more on it. So
I have exact dates. It took 3 days, and one of this was Sumit and I sitting there debugging the robot and why it's going backwards instead of forwards. So
Right at the deadline. Very nice. Cool. Well, thank you all for coming. Thank you all for attending our workshop on the intersection of robotics and language. It's been a great day filled with exciting talks, presentations, and debates. We've heard very strong opinions and interesting perspectives on the role of language in robot learning. It was particularly valuable to have representation from different camps and to foster discussion between the robot learning and NLP communities. We hope that this workshop has provided a platform for sharing ideas and making progress in the field. Thank you again for your attendance, and we look forward to continued collaboration and exploration of the forefront of research at the intersection of robotics and language. Thanks a lot. That was generated by ChatGPT.
Can we get the panelists?
Yeah, speakers. All of the panelists come to the front, please.
Yeah.
Photo.
Oh, photo.
Or both, or all together. Maybe, yeah. Maybe someone can boss. I took pictures of. Oh, got it. For us. For the members. Yeah.
Oh, yeah. Maybe we'll all come here.
The smaller than I think it's all like 2 million. Okay, yeah.
And
What
Brian,
does that mean? Is there-
how like that was balanced. So basically. Thank you so much. Thank you, everyone. Thanks to Dorsa and Zarel. Yeah. Thank you for joining us.
Yeah. I guess.